the day, we have another keynote at 4 p.m. by Professor John Urschel, so please look out for that as well on the schedule. As like yesterday, I mean, the official program is split between two buildings, so I believe 4 rooms, 4 tracks are happening in this building, and 3 tracks, as opposed to 2 tracks yesterday, there are 3 tracks today happening at the Cathedral of Learning. So it's G24, 324, as well as 332. So an extra room in the Cathedral, you'll see that in the schedule as well. We also have a poster session at 6 p.m. So, and we'll have light refreshments there, so please do join us for that. We have some amazing posters this year, and they would all, it's a great chance to not only interact with the poster presenters, but interact with other members of the community as well, and serves as a nice little networking session. Lost and Found is also the registration desk. If you've lost something, please approach the registration desk with some ID. And finally, well, actually, I have one more. So please, also the mini organizers need to be sessions of their own chair. So if you're a mini organizer, there are a lot of mini symposia happening today. If you're part of that, if you're one of the organizers, you need to be the session chair of that mini symposia. The conference is not giving you a session chair. That's, we only do that for the sort of the non-minis in the program, so please be mindful of that. And we've also obtained a few arrangements with a few nearby restaurants to help attendees save money on lunch. There's Pimante Bros, Colombian Spot, K-Town Snack Bar, Hello Porch. There are coupons available at the registration desk. Please do use these coupons that supports the conference, as well as some of our sponsors and partners. And finally, I'd like to thank the sponsors of JuliaCon 2025 for making this conference possible. It would not be possible without them. With that, I would like to introduce, firstly, Kino Fisher and Lilith Hafner, who will be the first presenters of the State of Julia 2025.
Thank you. This is what's been happening and what's maybe going to happen. So in this talk, we're going to talk about recent technical developments that have happened in the last year, largely 1.12, so that's things that'll come out with the next stable release. We're going to talk about the impact of AI on Julia, use of Julia, and on how Julia interacts with open source. And we're going to talk about, just real briefly, about how Julia language development works. Like what caused us to do these things? What goes into what we'll do next year? We'll see. And we'll speculate a little bit about the future of Julia language development. So jumping right into the past, things that we've seen a lot of progress on last year are Julia C, which turns a Julia script into an executable, which is pretty cool, but isn't actually what you're looking for unless you also have the trim option, which is another thing folks have been working on that makes those executables smaller. Going with that, we've got main entry points, and the julia.m flag will launch Julia and automatically run those main entry points, and that helps standardize for various ecosystem tools that want executables and entry points. There's a talk that already happened, State of Trim, that you can watch the recording of, that'll say a lot more on this. And one of the tools that uses that main entry point is PKG, which is a tool many of you may be familiar with. And it now has an apps section, feature. And that allows you to install a Julia package app, and that is just makes it a little bit friendlier to deploy a Julia package as a user-facing command line application. And there's also a sources section, which lets you specify dependencies that are not in a registry, or not in a registry your users will have. Also there's a workspaces feature, which lets you specify workspaces for your package. Yeah. All right. I'm not that tall. All right. Good morning, everyone, first of all. So I'm sure most of you
have seen one of my talks at JuliaCon before, but for those of you who don't know me, my name is Kano Fischer. I've been working on Julia for more than a decade at this point. Been at every JuliaCon, and this one is no exception. I'm very happy to give the State of JuliaCon talk with Lilith this morning, or as I like to call it, Julia core developers do slide karaoke. We'll talk about it a little bit, but these slides are the product of many, many people putting in some late hours last night to put together some highlights. So, you know, we hope that you get an idea of what it is that people are working on, but certainly it is not everything that people are working on. And I also want to make sure that I express that this is the work of many, many people who are putting in enormous amounts of time into any of these features. So with that, let me quickly run through the rest of the new things in PKG. So there's version manifests now. So if you're running multiple versions of Julia, you may have run into the problem in the past where one set of packages only works on one version of Julia, the other set of packages only works on another version of Julia. That can now be addressed by appending the version of Julia to your manifest files, and Julia will automatically pick up the manifest file for the correct version. Very helpful if you're using multiple different Julia versions simultaneously. Does this video work? Yes, okay, excellent. There has been a fair bit of improvement to parallelism during package installation. In particular, artifacts will now download in parallel, so if you have a big package with a lot of binary artifacts, installation of those should be sped up by downloading them in parallel. In addition, as of Julia 1.12, we will be compiling on multiple threads. So we were always compiling packages in parallel, so if you had a lot of packages, that helped, but if you had one very big package, it could get stuck in LLVM compile time for quite a while. So that is now threaded. So hopefully the overall experience should be a faster installation experience when you're installing packages. Compat will get automatically set on Julia 1.12. So when you add a package, it'll automatically install a compat entry. We hope that this will result in slightly more accurate compat bounds and making sure that when you install a package on new Julia versions, you actually get a working environment. And then there's a few minor extra flags, but oops. Okay. In non-package world, I think one of the really big features that we got into 1.12 is something that I worked on, which is binding replacement. I have a full talk on that, I hope, if Claude is done writing it, at 10 a.m., so in about 50 minutes, we'll see. But I'm very excited about this, so please stick around, unless you want to go to one of the other talks, which is fine too. But if you want to hear about binding replacements, they'll be here in 50 minutes. I don't know who added that. Okay, lots of cool new things in threading. Distributed.jl was made thread safe, so if you want to combine threading and distributed, that is now safer. I already mentioned multi-threaded compilation. There were a few new improvements to the concurrency API, in particular, wait any and wait all. So if you're waiting on multiple things, including threads, you can now do that. I think one of the big new 1.12 things, which also came out of the trimming work, is these new once per thread, once per process, once per task initializers. And these are very useful to replace dunder init methods, which can be incompatible with trim, as well as declaring exactly what your intent is with respect to one-time initialization of variables. And so if you're using Julia 1.12 and you were using dunder init for some initialization work, we encourage you to look at once per thread, once per process, once per task, and pick the appropriate one for your initialization work. And lastly, there's now an interactive thread by default on Julia, so you don't have to ask for it explicitly. Okay, in architecture news, RISC-V has seen a lot of work over the past year. I think Tim Bassard and Alex Fan deserve a bulk of the credit there. So RISC-V is now considered tier 3, which means that tests may fail, but things can, it's generally expected to build. Tests may fail, there may still be issues. It's not a particularly widely supported distribution yet. We also don't run it in CI yet. We just don't have any CI machines for it. But certainly there's been a lot of progress on it. You should now be able to start experimenting with it. And we look forward to seeing RISC-V adoption continue and the Julia support for RISC-V continue to become more stable. And Tim, do you have a talk on this as well? No talk. Okay, great. Next year. All right. You do have a talk on this, though. Okay. So Tim has a talk on OpenCL. So it's revived, modernized, integrated with the GPU stack. I think most people know about the Julia GPU experience, but I just want to emphasize that it's really excellent. Obviously, we have vendor-specific support for CUDA, for AMD, for Intel, for Apple's graphics cards with Metal.jl, and now there's another option for going through OpenCL. So that could potentially bring Julia's GPU stack to even more vendors. So I encourage you to check out Tim's talk on OpenCL.jl. All right, code gen improvements. C function and C callable now properly participate in the invalidation mechanism with appropriate performance. So that's very useful if you're interacting with native code that gets callbacks in Julia. There's been some optimizations around memory, which was added in I think, Julia 1.11? Memory was in 1.11? Exactly. That's what I thought. So memory was added in 1.11. Now in 1.12, we gained some compiler optimizations for these. We upgraded LLVM, so you get all the latest and greatest with new scheduler models for all the latest CPUs and GPUs, all the support for all the latest architectures. Though 1.12 is on Julia, 1.12 is on LLVM 18, Julia Master is on LLVM 20. And a huge shout out to all the people who keep upgrading our LLVM. It sounds trivial. It sounds like you just need to upgrade the version number in the make file from 18 to 20, but that's not how it works. Every LLVM upgrade is a significant amount of work, and thank you very much to everybody who works on making that happen. I'm very happy that we have volunteers who go through that and track down every single issue and file them and fix them and do all of the work that's required. More vectorizations as usual, more optimizations for atomics, which again is part of the threading improvements. Okay, I think we have some, yes. Okay, I think this is mostly just intended for shock and awe, so bad code in 1.11, good code in 1.12 for this particular example on summing this particular array. So this is, you have an array with with the same value in it twice. Obviously, the correct fast implementation of that is just to add them. But in order to be able to do that, Julia needs to be able to align all the memory accesses, all the array allocations, all of that. And what this demonstrates is that basically we've added enough optimizations, we've added enough annotations to the generated IR that LLVM can look through this and align, where legal, all of the array allocations, the memory loads and stores, everything, and turn this into just the sum of x with a self. Cool. Were you going to talk about this, or?
I can talk about it if you'd like.
Go for it.
The test suites are a little bit nicer. This matters mostly for folks who are developing JuliaLang/Julia itself. We track individual tests. We've got labels and stuff. It's just a slightly better user interface or developer interface. And Windows CI is working as of, I think, yesterday.
We had an emergency workshop, the first and hopefully last emergency workshop on Windows CI on Tuesday, where we basically locked all the core developers in a room for like 6 hours until Windows CI was fixed. So hopefully it's better now. We'll continue keeping an eye on it.
Yeah, we'll see. And Kino, do you want to talk about this?
Oops. Okay. This was a little bit of a last-minute addition, but I think it's important to talk about. So I was joking that AI was writing my talk, which, it kind of is, kind of isn't. But unfortunately, I do think AI is here to stay. So, we need to think about it. And I think we need to think about it in two different ways. One is, as a community, how do we interact with contributors using AI to create pull requests, to write contributions, to make changes to the language. So there is a contributor guide in Julia now that asks you to disclose if you're using AI tools to create pull requests. So we're generally happy with people doing that. However, we want to know that you're doing it. So, you disclose it in your pull requests. And B, you are still responsible for anything that you commit to the repository or submit as a pull request. So if you use AI to write pull requests, we need you to understand what it is that the code is actually doing. So if you do not understand how to fix something, ask the AI to fix it, and then don't understand the output, please do not pull request it, because that wastes reviewers' times. So that's the one aspect. I think the other aspect, though, is potentially more interesting, and that is, how does language design have to change if the majority of our users are using AI? So for those of you who are keeping close track of the repositories, there have been several pull requests that we have merged specifically to improve error messages that were confusing the AIs. As an example of that, Claude likes to hallucinate UUIDs for packages, and package, when it saw a UUID that was complete nonsense, was kind of giving a bad error message. The issue was when you had a UUID that didn't match the package, that the name of the package, basically it told you, oh, I don't know what that package is, when the issue was the UUID was wrong. So now package will check if you have a package with a particular name and a UUID that does not match what Julia knows the UUID of that package should be, the error message has an additional hint that will say, hey, maybe the UUID is wrong. And this extra hint in the error message allows the AI to recover, figure out that the UUID is wrong, look up the correct UUID, and continue. So that's a particular example. There was another example like that I forgot in Julia itself, of just improving the error messages to make the AI better. But I think this kind of thing will be a big theme over the next year and maybe the next couple of years, is thinking about what does it mean for language development that a lot of our users will be using AI. So I don't think we have any answers yet, but I wanted to put it here because I think it's an important topic. I don't think the AIs are going away. And I wanted to make sure that everybody knew about the policy, that you have to disclose it. All right.
So Julia language development, Julia is not like a project owned by a corporation, developed by a corporation. Julia and Julia Hub are a little bit different. Not everyone who works on Julia works for Julia Hub. In fact, only a small fraction, although a lot of core developers do. And so there is not, there's not like a a group of people who sit in a room, in an AI-generated room, and decide what the future of Julia language development is. And there's also not a big pot of money that's community allocated. So there's individuals, volunteers, or companies who want to do things, who are interested in doing things and do them. And that's how a lot of Julia language development happens. There's also, and this is another huge chunk, companies that see Julia as a useful tool and want to improve it in a specific way to help that company do what that company does. And that's what Julia Hub's doing, that's what ASML's doing, that's what Relational AI is doing. All these companies that sponsor JuliaCon or pay people to contribute to Julia, or to pay people to contribute to packages, what they're doing is whatever they want that the upstream maintainers will accept. And so we don't have, there is no we that has control over where the future of Julia is, where resources for development are allocated. Core contributors can gate features if they're bad. If someone's like, oh, here's an AI-generated garbage, we can be like, oh, actually, no, thank you. But we can't say oh, and you have to do this, and you have to do that. So there's no centralized, well-funded plan. And that can lead us to give unsatisfactory answers to what's the business plan of Julia, or what is the future of Julia. But we can try. So as a little bit of an example of the decentralized nature, this is a screenshot from last night editing this very presentation. There were 12 people editing it at once. And that's traditional for State of Julia. And the reason for that is because it's not just us, we didn't do all this stuff. It's a whole bunch of people who did a whole bunch of things, and this is highlights. And there's also not a PR team with people to make the slides for us. Yeah, unfortunately. Also, huge part of Julia, when people say Julia, a lot of what they're talking about is packages. SciML is not in Julia Lang Julia. It's not the language, it's not the compiler, but it's a big useful resource. Maki, all these packages that people use, and more core packages like Revise. Revise is not part of Julia. That's strange. And so lots of packages, lots more packages. Thank you to all the package authors. Okay, now we do want to speculate about the future. Because some folks expressed curiosity about what is to come. So there's two parts of this speculation. One, we're going to talk about things that are already happening. And those you can kind of trust us, although who knows when they'll get here. And then the second half of the speculation is things that we haven't really started. And those, maybe trust us, maybe don't. Take it with a grain of salt. So in the works, Julia lowering. This is a really cool thing. There's another slide on that. Pluggable GC. That is, Julia has a garbage collector. What if you wrote your own garbage collector? That's better. You want to use it? That is now an option. So the pluggable garbage collector interface is done. I don't think it's marked as stable yet. And MMTK, which is a non-moving garbage collector, not the Julia default, is also available. Moving garbage collector, that means when it's collecting garbage, it copies the data around, moves it to reduce fragmentation. Still work in progress. We've got some task scheduler updates in the works, and the Jet language server is also in the works, and there was also a talk about that previously. So Julia lowering. Just going to take a shout out about Julia lowering. How the compiler works, you get code, you parse it, you lower it, you compile it. Pretty simple, right? It's only about 5 lines of code. That's a joke. There's a lot of lines of code. Provenance is where did that code come from? And Julia syntax keeps provenance. Our current lowering does not, but the new Julia lowering does keep provenance. And having that provenance information means we know where compiled code came from. And that means revise can be more robust, aka correct. Just Thulu can be more robust. And JetLS can give you exact line numbers and column locations for type annotations. An important note, right after lowering is type inference, so any sort of tooling that uses types will now, once Julia lowering is ready, will have the exact location in source for those type annotations. So that's super useful, faster debugger, maybe more. Julia lowering is a keystone part of this. JetLS, there's a talk for that. It's in the past. You can watch the recording. It's cool tooling. Pluggable GC. Do you want to talk about this?
I think I will talk about it briefly. I think in the interest of time, I won't talk about it deeply, but there is another talk about that tomorrow. But as Lilith mentioned, there is now a GC interface. The first consumer of that is MMTK, the Memory Management Toolkit, which is a externally developed Rust-based code base that has implementations of several traditional GC algorithms. As was mentioned, the currently working one is non-moving IMIX, and moving GC is in progress. But basically, this is of interest for people who are running long-running Julia processes. Relational AI has been sponsoring a lot of this work. You know, they have long-running Julia processes that serve their queries, and then you start getting concerned about things like memory fragmentation, about the performance of your allocators, and things like that. Some other people don't care. If you're doing lots of simulations, or you're spinning up something that only runs for a couple of minutes, you probably don't care about this. But if you're running long-running Julia processes, I think this is very exciting work that you should keep track of. Okay, and just to save some time in about 5 minutes, we're going to do Q&A panel with Julia committers after this, which I will moderate. So if you're a Julia committer and you are in the room, be prepared to just come up to the front as soon as the Q&A slide goes up. And then I will moderate it. I'll start taking questions as people come up, and then have whoever is the best person to answer it answered. Okay. So there was a request to speculate about where Julia might go, and the challenge with that is that none of this has any timelines on it. But I'll do it anyway, and if it's not done in 5 years, sorry. Okay, so I think a general theme that we're seeing in Julia right now is that Julia has come to a point of maturity. So there's a lot of organizations that are maintaining large-scale Julia code bases and are running into the challenges that come with that. I think I mentioned it with the GC, comes if you're running a large-scale long-running one. But there's also organizational things like, oh, I actually want to enforce certain, features that are more interactive. I want to enforce that they're not being used in my production workloads because, we think they're too risky. Or things like, how do we actually do evolution of the language in a world where we have 12,000 packages, right? I think when we released Julia 1.0, we spent about 2 years working on various sorts of interfaces, improving various APIs, adding deprecations, and sort of dragging the entire ecosystem along with us. For those of you who are around, I think you'll remember, pages and pages of deprecation warnings with every new release. And I think the somewhat naive thought back in 2018 was, okay, we'll do that again at some point. We'll spend a year or two cleaning up all of the new things that we encountered, dragging the ecosystem along with us, and just having sort of this period where we go from 1.0 to 2.0. I think in the current state of the world where Julia is, I don't think that's feasible anymore. The ecosystem is too large. There's too many mature packages that we cannot all upgrade simultaneously. So I think there's significant interest in coming up with mechanisms to evolve the language in non-breaking ways and try to get some of these things that we thought might be in a 2.0 in a non-breaking way. So there's several items here that help with that. One is, can we use the compat annotations for syntax evolution? So say we want to change some syntax or remove some syntax because we think it's bad or confusing or what have you. If you declare a compat version that says, okay, my package is compatible with Julia 1.13 at the minimum, can we give you new syntax? So if you say my package is compatible with Julia 1.6, you get the Julia 1.6 syntax, but if you say my package is compatible with Julia 1.13, maybe we can give you a slightly different parser that disallows some bad corner cases in the syntax that we can't just remove because we don't want to break things, but that we want to discourage. Similarly, strict mode is sort of this idea that there's some corner cases in the language that are useful for interactive development or that are there for historical compatibility. But maybe as an organization who's maintaining one of these large-scale code bases, you actually just want to disallow that in your packages. So can we have an opt-in mechanism for people to say, I want to be a little bit more strict about what is allowed and what is disallowed in my packages? Export versioning, similarly, how in packages and potentially in base do you iterate on APIs in non-breaking ways so that packages that used to work with an old version of an API will keep working, but you can introduce a new API, and then once all of your users have moved on, maybe then you remove the old API. Other things that people are working on is more improvements to threading. I think threading is pretty good at this point, but we still, for example, don't run the test suite with it because there's still various known non-thread safe code in base. So stabilizing that, improving the performance, fixing all of those issues, I think is something that people are interested in doing in the near future. I think robust cancellation is a big one. There was a talk about it yesterday. There's various discussions on the issues, but Control-C has never worked great with Julia. It used to just crash Julia on 1.13. It basically doesn't work at all. So I think 1.13 might be the time that we actually look into fixing that, implementing some sort of robust cancellation mechanism, both for Control-C and for general cancellation. And again, there's a separate talk on that, as well as lots of GitHub discussion. And continued work on time to first X, time to first plot, time to first SIME, solve, what have you, as well as the new time to very first plot. So now that time to first plot is mostly okay, people have said, okay, now it needs to be the very first plot, so that includes precompile. So trying to improve that. That may be things like, okay, do we need to serve precompile files from the package service rather than having everybody compile it? Can we do further things around parallelization? That kind of thing. And then sort of part of the Julia C work, but not quite the same, is separate compilation. So can we compile modules separately? I think that's also of interest for Julia lowering and Julia syntax, all of these modules that are now written in Julia that used to be standalone libraries. Can we actually still compile them as standalone libraries even though they're written in Julia? Okay, and with that, we're going to have about 10 minutes of Q&A. So any Julia committer, please feel free to come on down. And while that happens, I'm going to start taking questions, and then I will assign those to whoever's here. All right, just raise your hand if you have a question, and Ranjan will run a mic to you. Yes, go for it. Yeah, just whoever raises the hand. Just you. I'll point in a general direction, and you just choose. Yes, go ahead.
What's the state of SIMD support in terms of how active users need to be to have it actually benefit them? Is it
of SIMD, SIMD, or
SIMD?
SIMD. So I guess I'll take that one while everybody's coming up. I think there's several answers to that. So I think obviously we're continuing to improve auto-vectorization support. So newer LLVM has a new auto-vectorization infrastructure called vPlan, which I'm not sure we enabled with the LLVM upgrade, but we have not. They have not enabled upstream, so we have not. We have not enabled it yet. We may enable it in the future. Thank you, Gabriel. So I think there'll be some auto-vectorization improvements. Obviously, there's also Julia packages for vectorization that are not standard Julia semantics, but enable use of SIMD. I think we've regressed a little bit on those, mostly because they're hard to maintain. So I think we'll need to think about in what way we want to maintain. I think we'll probably want to move those a little bit closer to core, so add some compiler extensions to make that a little bit easier. There's also things like implicit vectorization of library functions. So if you call sign, we'd kind of like to swap that out with a manually vectorized version of that, which LLVM does have support for, but now that all of the math intrinsics are written in Julia, that support doesn't apply automatically. So some work to be done to enable that. And then I think there's still a general interest in unifying the SIMD and SIMT programming models to be able to do ISPC style SIMT programming on vector lanes. But hopefully that can be done in a package with all of the compiler extensions that we've written. Yeah.
Thank you. There are 3 topics you mentioned that are of interest to me: task scheduling, garbage collection, and threading. Can you compare the expected performance of those 3 areas to other languages, especially Go, with version 1.11 and also with the improvements in version 1.12?
Sure. Who wants to talk about tasking?
So 1.12 specifically doesn't have too many improvements in comparison to 1.12. They kind of got bumped into 1.13 due to time. Go specifically does a couple things that we currently don't do that allow them to have very, very, very cheap coroutines, or Go routines it would be. So Julia's task, while close, especially if you compare them to like a straight up thread, like a P thread in C, we can go to my talk later today if you want to see about that. We're not as optimized as Go is. There's not really a technical reason why we couldn't. One of the things that Go does that allows them to be particularly good is they allow what's something called preemption, which we do not. Simply, it's a very difficult thing to implement correctly, and we haven't spent the time to do it. So hopefully with time, we will get to Go's performance. And the place where you will see a difference in performance actually is when you spawn hundreds of thousands of Go routines. If you're spawning just a few tasks, Julia in straight line code is faster than Go because we optimize slightly better of your normal code. So there might be a trade-off there, like it's how many tasks are you spawning per second, when is the trade-off? It would probably change on each benchmark, but yeah.
Will cross-compilation be on a roadmap at some point?
Yes.
Follow-up, when? I'm happy to test unstable things.
Cross-compilation is of interest, but it's one of these things that we'll get to when one of the core people who really needs it has the time for it. So I think Lilith mentioned that the way that Julia development works is that whoever has a need for it implements it. I think a lot of that work and the Julia C work has been driven by Julia Hub's needs for dyad. That will in the future include various controls hardware that needs to be cross-compiled to. So I think we'll look at it in that context, but there's no concrete timeline on that. So if anybody wants to work on that, you're welcome to. It doesn't just have to be the existing core people. We always welcome new contributors, but I can't give you a concrete timeline.
If anyone wants a concrete timeline and has a giant bag of money, that could make there be a concrete timeline.
It might also just be worth pointing out that CI is a great workaround where we have access to CI machines, or GitHub has access to CI machines that can do that. And so in lieu of cross-compilation, there are lots of machines available to do dedicated compilation.
Yes.
Could you say what someone might do to get involved in helping do cross-compilation?
Sure.
Yeah, repeat the question.
Yes, repeat the question. The question was, what could somebody do to get involved with cross-compilation and helping make that work? I think it depends a little bit on what you want to use cross-compilation for, right? One thing you might use cross-compilation for is just to make it easier to compile Julia. I mean, we heavily use cross-compilation in Binary Builder to produce binaries. So if you're interested in that, I think there's some technical work to be figured out around how to expose the difference between the build platform and the compilation platform in Julia, right? At top level, there's various conditional checks around what is the build platform. Somebody has to go through and look at those, see if those should be moved to runtime checks, or otherwise come up with a compilation model that supports that. If you're more interested in the embedded use case, then I think the first thing that needs to be done there is actually work on various embedded support libraries so that we can do things like code loading and targeting of the embedded devices easily from Julia. I think it's the ecosystem there is not mature. I actually think WASM is a pretty good target for that, just because it sort of has embedded characteristics without you having to have hardware and without your USB cable falling out and causing extra errors that you didn't anticipate. So I think for people who are interested in embedded, looking at embedded WASM, quote unquote, so WASM without the big runtimes and without the GC would be interesting. But in general, feel free to get in touch on the Julia Slack with your particular interest, and we can probably point you somewhere.
Hi, thanks for the talk. Is there any plan for supporting for two packages loading, two different packages loading two different versions of the same package?
All right, Jameson, you want to take that one?
Sure. I think the short answer is that there's support for it, but that it is a tricky user problem. We do it now even for the REPL, because if you have created a combination of packages that would not allow you to load the REPL or PKG, it can become really difficult to get out of that situation. And so we implemented basically a way that it can load the version of REPL as shipped with Julia alongside the version of REPL that you might be trying to change, or the same for PKG. The longer answer is there because when you do that, you then suddenly have two different states of the same package that aren't interacting with each other, and a lot of packages kind of want to assume that they're interacting with each other. So it's a both answer, kind of. And I'm hoping that at some point we can also reintroduce the reload macro so that if you have a package, you've completely changed it, revise is not sufficient to fully pick up all of the things that you've changed about it. You could tell it to load the latest version and mostly ignore the fact that there used to be an old version.
Do we have any more? We do not.
I think we're done. Sorry.
Okay.
So
I think the last thing I'd like to do is recognize our new committers. I think we have a couple of people. So if you got commit access in the past year, just come up and get a round of applause. I see 2 people, 3 people maybe? Yeah, just okay. We're done. Thank you very much. If you got commit access in the past year, come between here and here so that you're on the stream and get an extra round of applause. All right, Sam, anybody else commit access in the last year?
No, we haven't.
So this could be you next year. Got to contribute more. All right, I'll be back after the ad break for binding partitions.
Well, thank you to the core Julia contributors for the State of Julia 2025. Next, please don't go away, folks. Next, we have the sponsor talk by AWS. And AWS is a silver sponsor at JuliaCon 2025, and we deeply appreciate their support. So if the speaker from AWS could approach the podium and deliver the sponsor talk, yeah, feel free to connect.
Okay. Thank you. All right, thank you. Good morning, everyone. Thanks for sticking around. I'm Greg Piers. I'm a research scientist at the Amazon Web Services Center for Quantum Computing. I'm here in front of you this morning because AWS is very pleased to be a sponsor of JuliaCon this year. And I'd like to take this opportunity to tell you a bit about the Center for Quantum Computing, the hardware we're developing, and some of the software that we're developing to develop the hardware. So the CQC includes this lovely building on the Caltech campus in Pasadena. There's also a hub in San Francisco. And at the CQC, we do research on both hardware and algorithms, working towards fault-tolerant quantum computation in order to solve problems of scientific or commercial importance that are beyond the reach of classical computers. So I'll unpack that a bit. The idea of quantum computation is that we can use quantum physics in a certain way to efficiently solve certain problems that are intractable to ordinary computers, classical computers. One of the challenges with doing this is that quantum information is fragile, inherently fragile in a certain sense. So we go to great lengths to protect a quantum bit or qubit, which is otherwise very error-prone. For example, we put devices in dilution refrigerators, like the one whose guts are shown here, and operate them at a fraction of a degree above absolute zero. The particular devices that we make look like this. This chip is about centimeter scale, where our quantum bits are implemented in hardware using circuits using superconductors, so superconducting qubits. And I'll just highlight a couple things we like about this approach. These are integrated circuits, so we can take advantage of very scalable fabrication technologies from the semiconductor industry. We do the same sort of things to make one of these as any other computer chip. And we can also really engineer the quantum behavior of these circuits in detail, by which I mean that there's a very large design space in terms of what goes on this chip and what you can do with it. And there are just many interesting things you can do if you can think up how. Then fault-tolerant quantum computation is the idea that we can use error-correcting codes to combine many faulty physical qubits into a robust logical qubit. So in this illustration, this entire block here would be our logical qubit. We have a grid of white dots. Those are our physical qubits, plus some green dots, which are ancillary components to help us detect and correct errors. And we've also labeled two dimensions on this grid, dx and dz, because this particular scheme for error correction that's being illustrated uses redundancy in each of these two dimensions to protect against two different kinds of errors that a qubit can experience. So unlike a regular bit, which has one kind of error, it can flip, so 0 to 1 or 1 to 0. A qubit can also flip, or it can have what we call a phase error. But the important thing here is it takes many physical qubits to make a robust logical qubit, and this is in part because we have these two kinds of errors. So if we look at what it'll take to reach beyond classical computers, it looks like a lot. So there's this great survey by authors at AWS of applications of quantum algorithms with estimates for the computational resources they'll take. And one interesting thing here is that even for what people see as some of the most promising early applications, like quantum chemistry here, it looks like we'll need thousands of logical qubits operating for tens of billions of gates without an error. And elsewhere, it's been estimated that to get one logical qubit with error rates that low, using common approaches with superconducting qubits, you would need 1,000 physical qubits for one logical qubit. Or in other words, millions of physical qubits before you're solving these problems. So at AWS, we've given a lot of thought to scalable error correction architecture, and we've recently published about this chip, which we call Ocelot in the glamour shot here. There's also a link at that QR code if you want to read more later. But we believe this demonstrates a path to error correction with 90% lower overhead than what I just described, so 100 instead of 1,000 physical qubits. And we do this by engineering our superconducting circuits in a very specific way so that they have intrinsic protection from one of these two kinds of errors. And that error correction block that I showed earlier can be then much shorter in one dimension than the other, so reducing greatly the redundancy you need, the overhead. Still, there are about 10 physical qubits on the chip shown here, so there's a long way to go. To that end, we've been developing software tools to help us get there. One of those is a Julia package, devicelayout.jl, which we use for CAD, computer-aided design of our chips, to make both 2D layouts and 3D models for simulation from device schematics. And we open sourced this earlier this year. You can find it on GitHub. And it is the software that we use to design Ocelot and the chips we use for other experiments. If you missed a talk about this in the Quantum Mini yesterday, you can find the recording or find me later. And this here is just an illustration of a schematic produced with this package. We also developed PALIS for parallel large-scale computational electromagnetics. This is also open source on GitHub. It's not in Julia, but it is complemented by our package, where we can create 3D device models in devicelayout.jl and simulate them with package. And I have to wrap up. Before I do, I want to say we also use Julia for simulation of quantum systems. We recognize there's a great quantum Julia community that we hope to see grow. And some of the team contribute to packages in that ecosystem. There are, of course, many interesting software problems we face, Julia or not, in high-performance computing, data science, optimization. And our team is still growing, both research scientists and software engineers. We're especially excited to talk to people with Julia experience. You can learn more about some of our open positions at that QR code. And with that, thank you for your time.
Unfortunately, we've run out of time for questions, so we'll let the next session set up right now. Please do find Greg whenever you can if you're interested in working in both of these topics. And again, thankful to AWS to be a silver sponsor at JuliaCon 2025. Thank you.
Brandon, is there a reintroduction, or am I just going? I mean, I can introduce myself if you. Okay. Should we do it right now? I mean, it is 1 minute to 10. Exactly at 10 o'clock. If you start exactly at 10 o'clock, you're going to eat into my time. Well, I'll start talking at 10 o'clock. You can do the introduction.
Okay, fine. I'll start the introduction. Okay. It's my pleasure to introduce Keno Fisher, who will be talking about constants that are no longer constants.
All right. Thank you very much. All right, so for those of you who missed, I'm supposed to wait another 20 seconds. So how's everybody doing? Now it's 10 a.m. All right, thank you very much. For those of you who missed the State of Julia talk, my name is Keno Fisher. I'm one of the core Julia developers. Been working on Julia for more than a decade at this point. And this talk is about binding partitions, aka constant redefinition, aka structs work now, aka constants are no longer constant. What's up with that? If you want to follow along, I'm going to go through some of these slides pretty quickly. There's a QR code up there, and you can find the PDF version in the releases section of the GitHub repository. Okay, oops. There we go. How many people here know what revise is? Okay, all but 2 people. Great. So revise is the way that we have in Julia that lets you interactively apply changes that you make to included files or packages to the current session of your Julia process. So an example way that you might do that is this one. You have a file called struct.jl on the right, and declares a struct called point with 2 fields x and y. You create a new point called p-or-ig, and then you go and you edit it and add a new field called z. And now what happens? Well, in Julia 1.11, the answer is badness. You'll get an error, invalid redefinition. You probably can't construct it anymore because revise tried to add the new constructor for 3 fields to it. So even if you said you don't care about the error, you'll just keep using the old field. Your Julia session state probably was corrupted. And in general, this is one of the primary reasons that people have often had to restart Julia nowadays, because revise is pretty good at handling everything else. So how many people have run, of those who have used revise, have run into this exact problem? Okay, basically everybody. So I fixed this. Thank you very much. So this is fixed. So if you're using Julia 1.12, this now works. So if you add the new field, it basically works as you expect. It'll create a new type called point, and you can even still access the point that was created before you edited the struct, although it has this weird @world macro in there, and that's what we'll talk about. I just put a little gag in there. Okay, let's talk about bindings. So this talk is mostly about the internal representation of bindings and how Julia understands what any particular name that you refer to in your program actually refers to. There's a little bit more user-facing documentation on world ages and binding replacement that's in the docs, so I'm not going to duplicate too much of that. So this talk is mostly about internals. But to understand what's different in Julia 1.12, I think we need to start with what used to be the design in Julia 1.11. So let's say we have some symbol in our program, and we want to know what it refers to. The first thing that happens is that lowering decides whether it's a local symbol or a global symbol. I'm not going to talk about lowering here. There were various talks at other JuliaCons and this JuliaCon on lowering. But let's suppose that lowering decided that some symbol is a global. How does it know what that symbol actually refers to? Well, the answer is that inside the module struct, there is two tables, one for all of the other modules that you've called using on, and one that is a table that maps symbols to something called a binding. So on the slide here, you can see the definition of struct binding. It has a value in there, it has a global ref in there, it has an owner field, which is another binding, or rather, pointer to a binding. If you're not familiar with Julia, it has a type field, and it has some flags. Now, global ref is basically the same as a binding, except that you can have multiple of them, and you can have them even if they don't exist in the binding table. It's a little bit of a historical split. So in Julia 1.11, basically the only difference between a global ref and a binding was that you could never have a binding if it wasn't in some binding table. On Julia 1.12, this distinction is basically completely erased, and you can basically treat them interchangeably, and in fact, we may merge them internally in the future. So I put global ref on the slide, but I won't talk about global ref for the rest of this talk. But I know this can be a little bit abstract, so let's work some examples. So perhaps the simplest possible example, both of these tables are empty. You're not using any modules. You haven't declared any bindings. What happens if you look up a global variable? Well, you just get an undef error. Simple as that. I should point out that this situation basically never happens because you usually always have using base or using core in your module. So I don't even think we actually implemented the optimization for this case, but to simplify, in theory, everything is empty, you just get an undef error. So let's look at the simplest non-trivial case. I say const x equals 1, and my binding table gets a new entry for x. I get a new binding object that has value 1, type any, and the flag set to const. And again, this is the 1.11 design, and I've sort of shrunk down the representation a little bit because we'll have a little bit more of these on later slides. But the notation is the top entry in the green node, which is the binding, is the value, the middle node is the type, and then the bottom row is the flags, and the little arrow that comes out of the black circle on the top right is represents the owner field. So if you declare const, you have a single binding, value of 1, const flag set, owner field points to itself, and the type is any. Globals look very similar. It's basically the exact same, except the const flag is not set. Type globals, basically the same, except the type field is int rather than any. You get it. This is simple stuff. And please give a thought to me making all of these diagrams that I show for like 20 seconds apiece. Okay. Now, a little more interesting case, how does import get represented on Julia 1.11? So we're declaring a module A, we're putting a const x into it, then we're importing it, and what this does is it creates a new binding object in main whose value and type fields are completely unused, but the imported flag is set on it, and then the owner field points to actually there's some other binding over there, and then most operations on the binding in main, like is it const, what's the value of it, those kinds of things will actually get redirected to that other field over there. There are some differences. For example, you can't assign through imported bindings, so if you say x equals 1, that'll be an error. But for all intents and purposes, it's basically just a redirector. So it basically says, okay, look at this other binding over there. And this is, I say 1.11, but this has basically been the design since the start of Julia. So this applies up through 1.11. Even more complicated example, 2 imports where I have a module A and then I have a module B that imports it, and then I import the binding from module B. The thing I want to point out on this slide is that the import point, so the owner field points to the ultimate binding that gets imported. So the binding path of how it got imported does not get reflected in the data structure. So even though in main we imported from B, the owner field points at the binding in A. So it always, whenever you say import, it finds what is the ultimate binding that gets imported and points to that. Some corner cases, you can have globals that are declared but not assigned. They're basically the same as regular globals, except the value field is set to undef. Not that important, but I wanted to mention it for completeness. Okay, so if that was the only thing that we would have, this design would be fine. It wouldn't be that bad. The real trouble comes with using. So when you first do using of a module, in this case, I have a module X, module A, again has a constant X in it that we're exporting. So when you first do this, there's no representation of X in the module main because we haven't actually used it yet, and in fact, you could declare it to be something else later. So before binding resolution, all we have is the binding for X in A. It has the value 1, any, and the only difference to the regular binding case is now that the export flag is set. But now what happens if you actually look at X? Well, what will happen is it'll look at main, ask, do I have a binding for this? The answer is no, and then it'll go through all of the modules that I've called using on, ask, okay, module A, do you have an exported binding called X? If so, at that point, it establishes a new binding in main that pretty much looks the same as the import binding, except it gets created lazily. So it gets created the first time anybody looks at it, rather than on the using statement as it would have been for the import statement. And this is a lot of trouble, because I said when anybody looks at it for the first time, but like, what does that mean? Like semantically. And this gives you an insight into what the conversations are at the office, right? Like somebody will say something, this is a bug, and then it's like, but what does it mean semantically? So this is the question, what does it mean semantically? And the answer is, we don't know. So it was ill-defined semantically. So yeah, I will give some examples. Yes, ill-defined semantically. So before I give the example, what do I mean ill-defined semantically, right? Like obviously it happens at some point, right? Like at some point somebody's calling into the runtime and asks for the value of this binding, and then that binding needs to get resolved. And like obviously it happens. What I mean by ill-defined semantically is that in the abstract definition of the language, there's no, like we don't model as something that happens in the language binding resolution. It just sometimes happens at some point. And then this can cause trouble. So for example, something that resolves bindings is compiling a function that looks at the binding maybe. So this is an example that I like, where there's 2 loops that never run, but where the binding is referenced in the dead code in the middle of the loop. And the difference between these 2 examples is that in one example, the compiler knows that the loop never runs and never actually bothers looking at the loop body. And in the other case, the compiler doesn't know that the loop doesn't run, at least at the stage where it does binding resolution. And so it does look at X, and this causes a difference in the semantics, at least on Julia 1.11, because in the case where the compiler looked at it, you're not allowed to reassign it. In the case where the compiler didn't look at it, you are allowed to reassign it. And there's lots of examples like this. So basically, anytime the compiler compiles, and semantically, the compiler is allowed to compile at any point, is allowed to compile anything at any point. So semantically, basically, at any point in the program, binding resolution could happen. And since binding resolution has a semantic effect on the semantics of the language, just looking at the program, looking at the set of definitions without knowing what the implementation did under the hood, you cannot know what the program means. And this is what I mean by it's semantically ill-defined. Like, you cannot know what the program means without knowing what the implementation does under the hood and whether it peaked at some binding. There's other things, like in the past, tab completion accidentally resolved bindings. We fixed that by hacking it so that tab completion would bail out if it saw unresolved bindings. But lots of things accidentally resolve bindings when they don't mean to, and thus change the semantics of programs. Now, is it really that terrible? Maybe not. I mean, we got away with it for 15 years, so maybe people don't encounter this in practice. But people do, like, people file issues about this. There have been 4 or 5 issues filed about this, and it's very unsatisfying. Like, it bothers me to my core. So this is also being fixed. One additional point I want to make. This can change based on Julia versions, right? Like, yes, Stefan. Which runs? Okay. Yes. Okay, so for everybody, the correction was that there's a bug on the code. False iterates one value. Empty array replicates this behavior, though. So yes, with the slight correction, the compiler can resolve this, and it depends on what the compiler did. And also, it can change based on Julia versions. So you saw there were lots of array improvements in Julia 1.12. Those were at the codegen level, but if they had been at the inference level, the compiler might have figured out that empty array is empty and might have stopped resolving those bindings. So whether a binding was resolved could change between Julia versions, so your package could break just because you upgraded a Julia version, and that's obviously never great. Okay. So, how is this different in Julia 1.12? So we still have global ref, but I'm not showing it on the slide. But there's basically 2 other changes to the internal representation of bindings on 1.12. One is just semantic cleanup, making some of these cases a little bit nicer representationally. The other is that bindings are now world age aware. And the way that reflects itself in the definitions of the structs is that the using table now has a min world and a max world for every entry. The min world obviously gets populated when you write the using statement. The max world is currently, I think, always set to type max, although you could imagine that if you delete a using statement and you have revise active, it would delete it, although I don't think that currently is exposed, but that's just something that we'll add to revise at some point. So binding looks quite a bit different. So the type field is gone. The flags field is still there, but the flags all have different meanings now. But it gained 2 new fields, partitions, which points to a new kind of struct called a binding partition, which is basically a world age partitioned version of what used to be in binding, the type field, and what used to be represented in flags. And then there's back edges, which facilitates invalidation, although I'm not going to talk about invalidation in this talk, just because it's a big topic, and also interacts with the regular invalidation mechanism, so it requires some additional background. But those are the 2 new fields that are in bindings. So let's run through all of our examples again with the new Julia 1.12 design. So the simple constant has 1 binding partition. The kind of the binding partition is const. the restriction, so if you go back, there's a restriction field which is any typed. In this new schematic, the bolded thing at the top is the kind field of the partition. The thing below it is the restriction. So constants are represented as a single binding, as a binding object with a partition of type const, and with the restriction set to the value of the constant. Now globals look different from that, where the value is still in the binding, but the partition says this is a global of type any. So as you'll recall, in Julia 1.11, the value field in the binding was used for both constants and globals. In Julia 1.12, that is no longer the case. The value field in bindings is used only for the values of globals, the mutable value of globals, but constants are in this restriction field in the binding partition. The reason for that is that constants are partitioned across world ages, but globals only have one value across all world ages. They might not be globals in some of those world ages, but if they are, they all have the same value. Now currently it's disallowed to actually do this syntactically, so you have to actually explicitly delete the binding if you want to switch something back and forth between being a global, and there's still some bugs there, so it's disallowed. But that's basically the plan for how this will work in the future, is that there may be many world ages in which it is global and some world ages in which it isn't, but there's always one value per binding that a global variable, if it is so declared, refers to. Okay, so now the key new feature is that these bindings are world age partitions, so you can redefine them. So if you have something that used to be const 1 and then you declared const 2, that now simply gets represented as two chain binding partitions with appropriate world ages set, so that the min world of the second binding partition is the world in which you ran const x equals 2. So this is the simple representation of that. Import still basically looks the same, except that it got renamed to explicit, and that the import path is now explicitly represented in the data structure for import. So it no longer jumps all the way to the binding in A, it now goes through each of the bindings in turn. And the reason for that is that it needs to be able to invalidate the binding in main if the imported binding in B changed, right? Like there's lots of cases now where you could say, okay, actually the binding in B is no longer an import of A, it's now a constant, and you expect the binding in the binding in main to update accordingly, so we now need to keep track of the provenance of imported bindings. So that changed. Implicitly resolved globals, however, still kind of look like they did in implicitly resolved globals still kind of look the way that they did in Julia 1.11. And there's now a difference between the representation of things that get implicitly resolved to globals and things that get implicitly resolved to constants. So there's a whole mechanism of dealing with changes in explicit resolution, changes in implicit resolution, which is why we don't need to track this path. But basically, there's a kind implicit global, and it still points to the ultimately represented global. If it's a constant, then it instead is of type implicit const and has the value of that constant in its binding partition. The reason for that is that we allow things like this, where you implicitly use the same name from two different modules. And as long as they have the same value, we allow this. Now, in Julia 1.11, this just arbitrarily picked one of them. Whichever one happened to be first in this dictionary, that was the one that it got resolved to. And since bindings could never be changed, it didn't matter. But now we can't do that anymore because one of these might get changed later, and then we need to re-resolve the binding in main to be able to give you the appropriate error. And then putting it all together, this is sort of the complicated example, but I think if you understand this example, then you understand how all of these mechanisms work. So what we're doing here is that we're defining a module A. First, we're declaring one of these globals that doesn't have a value in it. We're using that module in main. Then we're changing the binding in A to be a constant. And then we're asking, okay, what is the value of that binding in main? So if we go through this from bottom to top, they both start out as guard. Guard is basically just a binding kind that says, okay, I looked up what this binding is, and there's no implicit import for it, so it's always undef. So basically, the very original case where there was no binding for it, that now gets represented as a binding partition guard. If it's not there, it would redo the implicit resolution and find out that it's guard. Then when we say global X, the binding in A changes to declared, but the binding in main doesn't change yet because it hasn't been using yet. Then when we do using this world H partitioned using table, the binding in A changes to implicit global. And then when we do const X equals 1, both of the bindings change atomically. The one in A changes to const, the one in main changes to implicit const, and you get what you would expect that X in main is 1. So a little bit complicated on the slide, but I think if you understand all of the separate concepts, I think this should be relatively easy to understand. Okay, so again, with the correction that false on the left-hand side should be the empty array, these now behave identically on Julia 1.12. And in fact, the concept of binding resolution as something that affects semantics is gone entirely. So whenever somebody asks, whenever any part of the system asks for a binding, it now gives it a world H, and it asks, okay, what is the value of the binding in this world H? And the answer to that does not have any hysteresis. It does not depend on what ran before. It depends entirely on the set of definitions that are visible in that world H. So this is now completely well defined. So you give me a Julia program, show me what all the definitions are, and I can tell you exactly which binding it will refer to. Whether or not somebody ran tab completion or the compiler or anything else, all of that is now well defined. Now that does mean that it is possible that the binding resolution changed in your packages, because we had to pick for all of the various cases one rule or the other for which binding to resolve it to in cases that used to be disambiguated by a binding being resolved. Now, we've tried to pick good cases, so in most of the cases you shouldn't see this, but it is possible. However, it was also possible for this to break just because of a regular Julia version upgrade previously, because the compiler might have started or stopped resolving something. So now that it is well defined, at least if your code works in Julia 1.12, at least with respect to binding resolution, that behavior will keep being the same in Julia 1.13, 14, and so on. So Julia version upgrades can no longer silently change the binding resolution of your bindings underneath you. So hopefully worth a little bit of pain to adjust your packages to this change. Okay, I'm running out of time, but there's, okay, so there's the whole list of things. I think we talked about each of these. Const import is a little bit weird, undef const is a little bit weird, backdated const is there only for compatibility and might be removed in 1.13. If you're interested about this, you can look in the source code, which has documentation on this. But I think we walked through the rest of these. So this is just here for completeness. The one last thing I want to talk about is another one of these semantic cleanups, which is latest world. So I think everybody is familiar with defining methods at top level, allowing you to immediately call that method after you defined it. But if you quote out eval something in local scope and then try to call it, that doesn't work, and you get a world H error. Now, when does this world age increment happen at top level? This is another one of these things that wasn't well defined, and in fact, the interpreter and codegen and inference disagreed on when this happened. It didn't really matter in practice because they all kind of agreed that if you defined a method, at some point afterwards, a world age increment happened. So if the only thing that respects world ages as methods, you can kind of get away with being imprecise about this. Now that structs and imports and usings and all of that also looks at world age, we needed to be precise about it. So I actually wrote documentation about this. You can look it up. There's a full list of things that raise the world age, and there's also an explicit macro core.addLatestWorld that will add a world age increment at top level if you need one, which is very rare, but sometimes if you're dealing with eval or something like this, you may need an explicit world age raise. And again, another one of those things that may have changed, but at least now it's well defined, and there's a mechanism that lets you control it. So hopefully all of this makes your life easier, and hopefully you enjoy using revise with structs. And I have 1 minute for questions. Lilith. Go ahead. Oh yeah, can we get the microphone to Lilith? And if the next speaker wants to set up while I'm doing Q&A, I think that'll save us some time.
How does this impact compile time?
Hopefully not that much. I've done a lot of work. Optimizing this. So the actual impact on compile times themselves is minimal, but it does obviously add lots of new sources of invalidations. So I've added a lot of optimizations to minimize that, and try to not invalidate things if it wouldn't actually affect the resolution of what the binding refers to. But obviously there could be some impact. So it should be well worth the trade-off, but it is possible for you to add new invalidations.
Cool. Thanks.
All right. Any other questions?
I think he does have one.
Yes.
So now that we're tracing the back edges,
yes.
How comprehensive is that, and would that open the door to automatic reference counting?
I mean, it traces the binding graph, right? Automatic reference counting would actually care about all objects.
Okay.
So there's no back edges on objects. It also doesn't trace through evaluation. So if you do, const A equals B, and then change B, A does not get updated. The thing that updates that is revise. So revise adds extra edges for evaluation, but the core mechanism in base only cares about bindings.
Okay, thank you.
All right. Thanks, everyone. Yep.
Good? All right. Audio good? Okay, cool, awesome. All right, good morning, everyone. My name is Sam Berklin. I'm a scientific software developer. I work with Julia a lot. I wanted to give a talk today that I called Understanding Your Struct Toolbox. This is sort of an introduction to things that I thought would have been really helpful to know just sort of working with structs when I was first starting out. And just for reference, the QR code does link to the slides, which are also available at that GitHub link on the title there. So I think when I was starting out, it's very easy that we sort of think about structs are just sort of fancy named tuples because we're able to stuff data into these sort of like named containers and access data within these containers using the dot syntax. Moving forward, you sort of start to understand that structs are a lot more fundamental to the language. Obviously, they're sort of the core of dispatch within Julia. They're how we get access to a lot of mutation in different objects without calling into particular C code. And if you're building something like a framework for other people to solve problems using your abstractions, those abstractions usually take the representation of like different kinds of structs. So they sort of specify the language in which you solve your problem. So if you're working with a lot of Julia code, I think it's important that you're writing structs and that you understand sort of the basic, like, nice to have things whenever you're working with structs. So the first thing I want to go over is like how we think about struct equality. So if we define this like very simple struct on the left-hand side, planet, where it has some like string name inside of it and then a vector of places inside of it as well, and we make two different instances of this, one named Jupiter with a place called red dot, and then another instance with the same name and the same place inside of it, and we try to assert that these are equal. The default implementation of equality will say that these are not equal structs because of the fallback for how we do equality between structs. So what we need to do is we need to do sort of a manual implementation of equality where we do this sort of field-wise equality and then we and all of these together is sort of the typical notion of equality that we're looking for. And then if we do this, you can see on the right-hand side, we try to do this assertion again and we see that these two different like instances of this struct are equal. And worth pointing out, anytime that you define a custom implementation of equality, it's recommended that you also implement a custom implementation of hashing as well. So the notion of equality that we want is usually like pretty standard. We want to do this sort of field-wise equality. So there is a very nice package called autohashequals.jl, which will do this for you. And all you have to do is you prepend this like @autohashequals macro behind your struct definition, and you'll get sort of these nice standard notions of equality and hashing implemented for your types. The next thing that we like to talk about is iteration over structs. So iteration is an interface within Julia. It's how we get this sort of like for x in y syntax to work in Julia. In order to just get that to work, there's one method that you have to implement. It's this base.iterate. Iterate takes two functions. Optionally, the second one's sort of optional. First one is what is the object that you're trying to iterate over, and the second one is the state. The state tends to be what is, for something that's already collected, it's like what is the index that you're trying to iterate over. And so when you iterate, what you do is you return, here's the current object from this step of iteration, and here's sort of the next state to compute what is the next object that I return. And so you iterate over the object this way, and whenever you're done iterating, you return sort of a sentinel value, nothing, to indicate that you were done iterating. And so if you do this, you get on the right-hand side, you just get the for x in y sort of syntax just works automatically. And so this is, I think, one of the first things people will encounter as an interface that allows you to stop working with leaky abstractions. If you're able to iterate directly over objects that are containers over other like containers of objects, you no longer have to think about how are things stored inside of the struct that I'm working with, because you can do things like iterate over it directly. And this helps people not have to dig into the details of how things are implemented and work more directly with the abstractions that you intend them to work with. Also, on the right-hand side, if you implement just like that one iterate method from the last slide, you can do things like zip together two iterators and iterate over them in tandem. So there's a whole host of things that you get out if you just implement this like one method that you don't get if you have to sort of, you know, manually reach in and try to pull out things that you want to iterate over. And just a quick side note on this as like an interface. I gave a talk on the idea of interfaces within Julia last year, and that is available at this link on the slide as well. So there was a talk yesterday about Julia's superpower kind of being the existence of this REPL, which is really nice for doing sort of interactive REPL-driven development. And I think in doing this sort of interactive REPL-driven development, it's nice to be able to inspect types in a way that's meaningful to the user in addition to something that's meaningful to the computer. So by default, when you show something in the REPL, it just prints a string that's meant to be able to be copy and pasted into the REPL to like build a new instance of that same struct, which is very nice if you want to be able to copy and paste that string and build the same instance of that struct. But in practice, you know, if we're working interactively, maybe we care a little bit more about other parts of the struct or other statistics. So if you want to pretty print your struct, you have to implement this sort of 3-argument show. The first argument to show is this sort of IO abstract type, which is a container with a bunch of different information about like where you're trying to display whatever it is that you're trying to show. The second argument is this MIME type, and if you're trying to implement sort of this REPL printing for your struct, you need to do the text plain MIME type. Then the last thing is, of course, like the struct that you're trying to pretty print to the REPL. And so what we do here inside of the show method is you sort of build a string of how you would like to print, to render your struct into the REPL. And here, what I do is I sort of prepend what the name is of the individual field within the struct before I print the value of that field, which is a little nicer if we're trying to not have to keep track of what are the order of arguments whenever I'm trying to build the struct. So here we can print planet 1 and you see that the name is Earth and here's the list of places, rather than having to remember that the first argument is going to be the name and the second argument is going to be the list of places. And likewise, with all of these show methods and with that sort of IO context that gets passed in, there are sort of conventions on things about like, am I printing this in an array? Should I truncate? How much should I truncate the types that I'm printing? Which gives you the like nice array printing there in the bottom right. This is very nice for interactive development, which lets you print sort of like summary statistics of like simulation results and things like that. So the final thing I wanted to talk about is the concept of finalizers. So here, this is a mutable struct where both fields are marked as const. And then we register this finalizer called say goodbye in the inner constructor. So whenever we exit Julia or whenever an instance of this struct is garbage collected, it will actually call that code say goodbye, and it'll like print this nice message saying goodbye whenever that code is or whenever that struct is no longer held in memory. So this is something that we're able to do with mutable structs. We're not able to do it with immutable structs, and it doesn't actually rely on mutation. So the important part about mutable structs is the identity, not the fact that they possess mutation. And this is very useful for things like C, FFI, if you need to clean up memory managed by other programming languages. So that's all I had to talk about. Thank you.
Thank you, Sam. If you have any questions, we have time for maybe 1 or 2 quick questions. There's one question.
Are there any tools you could recommend if you're creating your own custom structs to sort of validate that you've done all of the housekeeping that you need to around things like equality and hashing and whatnot?
Sure. So I don't have something to recommend offhand. This sort of leads into the idea of interfaces that I was talking about last year. If you wanted to say that all of the structs that I implement are going to implement a custom show method, all of them are going to implement their own like hashing inequality, you could write sort of like manual test cases to just like inspect the method table to see that those exist. I don't know of something off the top of my head, but using one of the various interface packages, like required interfaces, I think, is one of them. You should be able to specify what that interface is and automate that checking.
Thank you.
Is there a USB-C?
You can go here if you want, if it's easier.
Welcome to my desktop. So I was at the, what do you call it, panel for the HPC yesterday, and someone brought up the challenge of getting people to start using HPC more, or getting adoption there. I think that's really important. Does anyone remember SETI at Home? Berkeley Open Infrastructure for Network Computing, that sort of tool. Telling these stories is really important if you want to get the adoption stuff. So I'm going to show you something that's definitely not ready to be shown, but there's stuff here. And it helps tell the story of Julia, the evolution of it, the use of it in research. My name is John. I am with NumFocus. I am also the executive director at the Open Source Endowment. Happy to talk about either of those separate from this. So we've built a map. This is the Julia ecosystem. I can't move this around that much or it will break my computer right now. But you can see I probably chose the wrong colors, but you've got blues are people and the purples are repositories. And I haven't put any of the other nodes on here because that also will, there we go, break my computer. There are edges in here, so we're starting to see the relationships of the ecosystem. This is the sort of end state that we're going to try and get to make this much more easier to use. But what did we do to get here? And then I do have data in tables that is probably exciting. And it just got brighter. It sometimes does stuff that's very exciting. All right, so this is the map of open source science. Essentially what we're doing is connecting the people, projects, papers, and institutions in any ecosystem to one another. So we can see what's going on. We can see who's using stuff. We can see who's contributing to what projects. We can see what projects are being used to create economic output, and then we can use that to go tell a story to a funder or to a government to try and get things like the Sovereign Tech Fund and Sovereign Tech Agency built around the world. And so we did that with Julia, we being me. What I did is a query on GitHub, essentially. So we ingest a bunch of repositories. So we look for Julia repositories that have 10 or more stars, simply because we can't ingest, I think it's like 40 or 50,000 repositories right now. And once you ingest these into this database, you're able to explore one. Let's see if it will load. I'm tethered on my phone, which is back there right now, so it might not. Hey. And you can get a bunch of details about the repo. Many of these are probably not accurate right now. You can explore off GitHub, all that fun stuff. You can also extract DOIs. We'll come back to that in a second. We can also ingest publications. So a publication, we take the DOI, we bring it into the database. I think I have one of these preloaded. Once it's in the database, you have a whole bunch of information about it. Authors, institutions didn't work, etc. But you can see the citations, references, impact, and we can do a lot of stuff. Once the data is in this database, we can play around with it and get some pretty interesting insights. Okay, so here's that batch ingestion. So we search for Julia with more than 10 stars. We find 6,000 repositories. We bring them all in, and then we can extract all the DOIs from all of these repositories and then do an analysis on those DOIs. That analysis, apologies for the telegram, can take place in 3 levels because this is essentially a citation graph. It's a lot of data. So you can do the level 1 where you take your seed work, you have one DOI, one publication. From that one publication, you get all the authors, all the institutions, and all the topics. So we're essentially going from GitHub with a repository that has a DOI in it, the citing DOI, the reference, the canonical DOI of that repository, or something else. But hopefully we found the canonical one. Little side note, we can't use Zenodo right now because its API is very difficult to use. So we can only use reference papers, which kind of sucks. So we go from GitHub to OpenAlex with that DOI. If you don't know OpenAlex, check it out. It's a fantastic resource. OpenAlex categorizes publications based on a hierarchy that goes from a topic, which is basically one topic per publication. Sometimes there's 2, sometimes a topic duplicates across publications, but for the most part, they're unique to each publication. Topics are assigned to subfields, then fields, and then domains. So when you take your seed DOI, you get the authors, institutions, and the topics that that publication is associated with. Then you get the references, the papers that this seed DOI references, and the papers that cite this seed DOI, and you make little placeholders in the database. That's a really easy ingestion to run. Then we do a level 1, or a 1 depth, where you take that same data, and then you do this process, the authors, institutions, topics, with all the references and with all the citations. So now you've just exploded to several tens of thousands of papers, and with Julia it's actually a couple, I think it's 150,000, we'll see in a second. And then depth 2, I've not tried to run one of these because you essentially do that same thing again with the papers that cite the papers that cite the, et cetera. It goes on forever. So you're building a giant citation graph. So I did a depth 1 ingestion of the Julia repositories, the 6,000 repositories that we brought in. That resulted in this database with 155,000 works, 11,000 people. So these are the people that contribute to the projects from GitHub, and also who are the authors to the papers that are referring to those projects on GitHub. And then the 650 institutions, These are the institutions of those authors, because OpenAlex also has that data. So essentially, 650 institutions around the world are using Julia. That's fun. So with this data now, we get some fun tables. Julia is used primarily in the physical sciences. You can see 1,201 works there. And we can keep going down this. We go to top fields. So fields, there's a bunch more fields, not nearly as many as topics, you'll see in a second. Engineering, or medicine, engineering, social sciences, et cetera. I can share this data with anyone who wants to see it. Subfields, molecular biology, and so forth. And then topics, like I was saying, there's really one topic per publication. So what does this look like over time? Like this. So you can see medicine has been adopting Julia, or papers, more papers are being published that use Julia projects since its inception, et cetera. A lot of this data is fuzzy, but it's mostly, the trends are mostly accurate, and so forth. So I'll leave this up for just a second, so you can see it and we can see where we're at right now. And so the point of this whole tool is to help us tell the stories of open source software. Julia is a language that's evolving. It would be pretty neat to be able to see this tool out there more, or more tools like this. There's also projects like Chaos that do health metrics, which this tool can do, but I can't show it right now because it's not really implemented. But utility analysis, impact analysis, things like that across the whole ecosystem. And what can happen with this is we can put Julia and Python next to each other, and we can see where they intersect. And we can say who's contributing to both ecosystems. And then ecosystems can start to support each other and really weave a deeper connection and a healthier open source world. So with that, I just asked AI, Gemini in this case, if it would be possible to build Boink on Julia. And of course, it's very optimistic, so it says, yeah, you should just do it. But this is maybe not a crazy thought. If we need to tell stories of these projects, of the software, to people who don't understand the software, I'm very much in the middle of that. A lot of the stuff, I'm out of my element here. I can tell you right now, garbage collection for me happens on Thursdays. But if we need to tell these stories, we need the tools to tell these stories so that people can recognize why these tools, the underlying tools, why the software is important. And maybe something, I know Julia is great with distributed computing, maybe something like a publicly accessible distributed computing network would be awesome. I know Boink is very much used today. I've built a couple organizations around it. It's fantastic. It's exaflops of processing power. This is way off base though, so I'll stop here. If anyone's interested in learning more about this project or seeing any of the tables, let me know. If anyone wants to help build this thing right now, it's just me, and I am not very good at software, so would love help. Thank you.
Thank you, John. We have time for a quick question.
Thank you. This will be already very useful for me when I'm submitting for grants. I'm curious, the plot of papers over time, I was very surprised to see like 50 papers in 2012. Like, was Julia really useful back then?
So that's the fuzzy nature of the current database. There was a bug I did not catch when I was ingesting the DOIs. So it recognized some of the papers that were referenced by the early Julia papers as Julia papers. So it actually goes all the way back to like 1988. It's like, oh, well, that's not right.
I see, thank you.
Any more questions? Thank you, John.
All right, good morning, everyone. My name is Demir Akçur, and I'm a PhD student in civil engineering at Johns Hopkins University. Today we have our own first mini symposium, Engineering with Julia. So myself, Christopher Mohn, who is sitting right here, and Cole Miller, I don't know if he is here, bridge engineer from HDR Construction Company, have decided that we need to really promote Julia among engineers, so we have decided to have this mini symposium. And today I'm happy to present our first speaker, Rajiv Valeri, who will be opening first ever Engineering with Julia mini symposium.
I'll just use this. Okay. Does this work? Yeah, oh, cool. Okay, good morning guys. Today I'm going to talk about aerialvehicles.jl and sort of the incremental update that makes it possible to do cooperative payload manipulation, specifically with 2 quad rotors and trying to carry a single payload. I'll start with a bit of a recap on my talk last year. The flat equation quad rotor model is derived using a force balance on a rigid body. The quad rotor is a differentially flat system. For a differentially flat system, all system states and inputs can be expressed in terms of a set of flat outputs and their derivatives. In our case, the flat outputs are the position in space, x, y, z, and the heading, psi. We use position, velocity, rotation matrix, and angular velocity to describe the state of our quad rotor system. The dynamics are defined in MTK, at least initially. The quad rotor is a very well documented problem in controls and serves as a platform to showcase controls, estimation, and various other applications. To follow sort of trajectories that are designed, we use a nonlinear geometric controller. The idea behind this is similar to backstepping for those a little bit more familiar with control. It involves designing the desired dynamics for the quad rotor and then stepping back to cancel all the non-linearities to make sure that the dynamics follow what is desired as opposed to just throwing a PID on there. The advantages of using the geometric controller are that it accounts for the specific non-linearity of the problem, and the state decays to the desired value exponentially. As is clear from the illustration, it's really hard to achieve that level of stability even with an extremely fine-tuned PID controller. So this allows us to do some fun things, acrobatic maneuvers, like stabilizing for falling quad or having it track like a really tight spiral, much more effectively than a PID would, and it's a lot less cumbersome. This is the overall structure of the trajectory optimization process with the quad rotor using a geometric controller. It was presented at JuliaCon last year. So based on an array of sort of waypoints and corresponding time required for each segment that needs to be designed, the trajectory optimizer synthesizes a desired output, which the geometric controller uses, along with state feedback to synthesize the control to make the quad rotor follow the desired trajectory. The control generation and trajectory optimization has been done using dyad control systems, and the quad rotor model and the geometric controller is part of the aerial vehicles .jl library. So this was my presentation last year. Just a quick recap in that we have an autonomous rendezvous of 2 ground vehicles with varying dynamics. They don't have the same dynamics, and a quad rotor utilizing a polynomial trajectory following geometric controller. So the quad rotor hits 3 waypoints before landing, and it triggers a cooperation between the ground vehicles, at which point they start to receive the time to go of the quad rotor every second, and they just autonomously achieve rendezvous. There's no manual control. It all happens by itself. So building upon sort of a theme of cooperation, the heart of the demonstration today is being able to define multi-body models. So the whole system is sort of comprised of 4 rotor components, a rigid frame, a cable with n links, 3 for this demonstration, and a payload that all lay inside the world frame. They're all easy to understand and define independently as components. And to assemble the cooperative system, you just have to connect the frame of one component to the other. And as is evident from the simulation results on the right, it makes thinking about the control problem much easier. So in this case, I've leveraged the payload position and the orientation within the framework of the geometric controller, taking into account the physics that is sort of required and what the quad needs to do to stabilize it. And yeah, the geometric controller used is an incremental update. It's not exactly the same as what it was, but it gets the job done. Yeah, so we have a demonstration of 2 multi-body quad rotors that are attached to a single payload. It looks quite mundane when it operates as it should, considering the trajectories are snap optimized, which means they're extremely smooth. So they're quite boring to look at. So in this simulation, I've intentionally initialized the system adversely with a slightly heavier than usual payload to study the stabilization process. The payload is tasked to track a figure of 8. Even when the payload is initialized near horizontally to the cooperative system, the quad rotors manage to stabilize the system. And both these quad rotors use the modified geometric controller, and state estimation is not a thing yet, which I'll talk about a little later. But yeah, this is the theme of this year's cooperation. Takeaways, aerial vehicles can be used to perform a variety of tasks. A component-based multi-body model has been shown to be effective and intuitive. Cooperative payload manipulation leveraging the multi-body modeling framework has been achieved. For future work, multi-body modeling is highly experimental and unreleased, and it will be released into the dyad ecosystem of tools when it is. Next, I would also want to explore complex geometric payload manipulation and have corridor constraints, which makes things a lot harder than just being like the world's your oyster. State estimation, because it's hard to estimate where the payload is and what the orientation is. There's no sensors that do that instantaneously. And so building up a state estimation problem to find those states would be exciting. Some of the other stuff that I have going on is aerialvehicles.jl has wind models. You can plug in wind into the system and see how it does in something a little bit more realistic and not like a closed room. And finally, deeper integration with dyad for running analysis on some of these multi-body systems or cooperative systems and optimizing performance. Yep, that's all I have. Thanks.
All right, thank you. We have time for one question. All right, I do have one question.
Yes.
When you try to link, try to move the load with 2 quadricopters, right? Mm-hmm. Do you have any geometric constraints to prevent the collision between them in the models that you have created?
There is a way to do that. I do that manually currently.
Okay.
So I synthesize very smooth trajectories for the quad rotors to follow and enforce a manual offset, which sort of makes it so they don't collide, which is very ideal. I know, but usually some of these collision avoidance mechanisms are sort of an inner loop, which is when they sort of get close to each other, there is a control input that sort of triggers that moves them away. You can do that with artificial potential fields. There's a lot of ways of doing it, but that's not the theme of this presentation. I can add that in the loop.
All right, thank you very much.
Yep.
All right, so next up, we have Gabriel Connor Steenberg, who will present on poweranalytics.gl, user-centric power systems analysis in Julia. Gabriel is a researcher at the National Renewable Energy Lab. So the stage is yours.
There we go. Okay, I'm Gabriel Konar Steenberg. I'm a researcher at the National Renewable Energy Lab. One of my main projects there is this power grid modeling platform called Sienna, and I'm here to present on a simulation output analytics suite I designed for that platform called poweranalytics.jl. So first I'm going to give a brief introduction to what Sienna is, what it can do. I'll identify, I think, the gap that I found in Sienna that Power Analytics aims to fill and what the users need out of an output analytics package in this ecosystem. I'll then go into depth in terms of the design of the Power Analytics package. I'll then kind of abstract away a little bit and talk about the design principles and techniques I used to design this package. I'll talk about how it's being used right now, its status, and what I'd like to do in the future. And then I'll try to synthesize some takeaways for package designers. So first of all, what Sienna is. It's this open source ecosystem for power system modeling. So it's a collection of open source Julia packages that we like to split into these 3 applications. So there's Sienna Data, which is a bunch of data structures for modeling a power system, all the transmission lines, the buses, the generators, the loads, that kind of thing. And time series that can be used to drive these components, that kind of thing. Various input data parsers from industry standard formats and some exporters to similar formats. And we've got a library of test systems, all of that. The Sienna Operations, Sienna Ops application. This is where most of the simulation happens that I'll be talking about today. So you can kind of think of this as like a compiler or an interpreter from this domain-specific power systems modeling language to a sequence of jump optimization models that go out and call a solver and then return the results, and then the data flow gets managed as well. So this can be things like unit commitment, which is the problem of given some load you want to satisfy, how do you turn your power plants on and off to meet that load in a least cost way. Economic dispatch, so once you've committed units, what levels to drive them at to meet that load, again, in a least cost way, that kind of thing. And we can run various other simulations, but basically in the end, we have this HDF5 data set, very heterogeneous, very big, of the simulation output, and we need a way to analyze that. So that's what I'm going to be talking about today. We also have this third application, Sienna Dynamics, which is less relevant today. So at a very high level, very bare bones schematic, this is what a power simulation might look like. So we've got our package imports. We're going to load one of these test systems. You could also build your own system, of course. We're going to just modify one of the batteries in there, make things a little more interesting. And then we need to map components in this system to how they're going to be modeled in terms of the formulation for the optimization problem. So we do that with this template. We're gonna load a standard one, and then we're gonna set a specific model we want to use for that battery. Sienna has the ability to run multiple problems in a single simulation. So you could run a unit commitment and an economic dispatch and have them kind of chain together, and it would manage that information flow. Here we're just going to do a single model. So you set all that up, tell it how much to run, and then when you build it, it'll initialize this jump model, and then it'll run the thing. So once you've done this, you've got a big, like I said, heterogeneous HDF5 file with all the results for the variables and the parameters. There's a few ways you might think about to analyze this. You could use a third-party tool like SQL or anything you might find in Python or whatever. We really aim with Sienna to be friendly to users who are not sophisticated software developers. For many of them, learning Julia itself was already a pretty heavy lift. And so we really want to keep the additional languages to a minimum. So this is a Julia native solution. You could think of people writing their own analytics from scratch. We expose a data frames interface, so it could just be data frames manipulation. But this tends to involve a lot of duplication of work. There's a lot of common quantities that you might want to calculate that it makes no sense for people to all calculate themselves. It's also pretty bug prone and leads to pretty long, convoluted analytics scripts. Before this 1.0 release, we had an old version of Power Analytics that had a few hard-coded sets of calculations, but it wasn't quite fully featured like we wanted it to. It could do like curtailment, but not integration. It could do certain aggregations, but not others. So we wanted something more modular and fully featured. So that's what I'll be aiming to design, what I aimed to design and what I'll be presenting here. So we can kind of think of this package as having 3 main parts to the workflow. First, you're going to select your components using a component selector. Then you're going to compute metrics on those components, and then you can do some post-processing on the output of that. So here's those 3 parts again. The component selector lets you flexibly express what part of the power system you're going to be analyzing for a given query. This could be something like all solar plants in one group and separately all wind plants in another group. It could be something like all solar plants in the system, but only if they're larger than 15 megawatts rating, and we want them all to be grouped individually. It could be something like all loads in a particular geographic zone all clumped together, that kind of thing. And then a metric specifies what results you want to work with. It can specify arbitrary Julia code for computing secondary quantities from those results, and then it also knows how to aggregate itself across space and time. So this could be as simple as just looking up the power variable from the optimization problem results and summing up across everything, or it could be more complicated, like integration. This is where you want to measure what fraction of load was met with a particular flavor of generation, and that involves some more math, and maybe you want to sum that across those generators and average it across time, that kind of thing. And then that's going to output a dataframes.jl data frame, and then we embed a bunch of metadata in there so you can do post hoc further aggregation and plotting and that kind of thing on top of that. So now I'll go over each of those parts in greater detail. So precisely, a component selector is a lazy, partitioned, named, source-independent collection of components. I'll go over what that means. So at its most basic, here on the first line, you can see we're making a selector from this type, this abstract type, renewable gen. That's just going to capture all the renewable generators in our power systems.jl system. So you can see we can call get components with that selector on a system. It returns this iterator of components. You can see if we've got a slightly different system, we can use the same selector to get what that applies to in that system. So this can be useful for like multi-scenario analytics where you've got a bunch of slightly different systems with slightly different simulations, and you can use the same component selector for each. We can also see that this is grouped. So the default is to group each component individually. So you can see if we call get groups on that selector as applied to the system, we get a vector of all the groups, and it's just all the individual components. But that's configurable. So now we're going to make a selector from all the generators, but this time we're not going to group individually. We're going to specify this partition function, get prime mover type. And this is a power systems function that can be applied to a generator to return its prime mover. And you can see that if we just call get components, it's that same iterator again. But if we call get groups, you can see that they're separated into various types of natural gas generation. We've got some hydroelectric generation in there, some wind, some PV, that kind of thing. And then those groups are themselves component selectors. So if you get one of those groups, you can call get components on it, and you can see that it returns a subset of the get components of the top level selector. All right, more component selector stuff. So here we're specifying a filter function to further specify what we want to include at all in our selector. So here we're saying we want only the generators with rating above 15 megawatts and only those with a prime mover type of photovoltaic. And we're going to give that a name. Then we're going to do a simpler selector, just all the thermal standard generators, and we're going to give that a name. And then we can compose a selector from these sub-selectors. And when you do this, the groups come from the sub-selectors. So you can see cell 5 here has the 2 groups corresponding to its constituent selectors. Component selector was designed for power analytics, but it's actually available across the Sienna ecosystem now in case you might have use cases for this kind of functionality elsewhere. All right, moving on to metrics. So again, metrics are things that you can either look up from the results or calculate from the results that know how to aggregate themselves. And typically, these are per component selector. We provide a bunch of built-in metrics. So you can see we've got the ability to calculate the active power, we can do curtailment, we can do integration, we can do total cost, and then I'll show you later there's ways to construct your own metrics as well. So here we're going to take the calc active power metric. This is an instance of a struct, but it's callable like a function. So you put it there, you put the component selector there, and you give it some results, and it'll calculate the thing. So here it's just looking up the active power variable from the optimization problem, and then it's aggregating according to the groups in that component selector. So here it's summing up according to all the prime movers. That's configurable, of course. So you can see we're looking up that the component aggregation function for this metric is sum, but we could make a new metric built from that old metric except changing that aggregation function to mean, and you can see that we get a table of the same shape, but now it's averaging across the generators in each of the groups rather than adding. Here's how you can define new metrics. So this really shows that we can run arbitrary Julia code here. It's not limited to just looking up results. We've got this function here that takes a results set and a component, and it'll look at the time series of results for that component and compare the battery output power variable to some arbitrary threshold. So this is just going to give true if it's charging faster than a certain threshold and false otherwise. You can see then that we bundle that into a metric, and then we call it just like the metric on the previous slide, except on this selector composed of the only battery that happens to exist in my system, and it'll return this data frame with the results of our custom metric. So very extensible. The dataframes.jl data frames that the metrics output have a ton of metadata embedded in them, which lets you do some neat post-metric aggregation and plotting. So here on the first line, we're getting a big long data frame of all the active power across all 755 time steps in our month-long simulation. But then we can aggregate that time down. By default, it just aggregates down all the time into a single row. And this is done with the aggregation function specified by the metric and embedded in this table's metadata, dataframes.jl metadata. You can specify different time aggregation to that aggregate time function. So here at the bottom, we're specifying day of week. So then that first row is going to be all the generation that occurred on Monday. The second is all the generation that occurred on Tuesday, etc. Another thing you can do with data frames metadata is some nice plotting. So this is mostly just to show that this is doable, and I'll talk about later how we intend to have a more user-friendly interface to this plotting functionality. But here you can see that we're getting that data frame, and then we're looking up in the metadata how many components were aggregated together to form each column. So we can add that to our legend here. So we've got this nice hourly plot aggregated by hour of day of the various types of renewable generation that's occurring in our system. You need not try to read all this, but this is just to say that there's a bunch of other features. We've got some easy results loading routines that work for multiple scenarios. We've got computation of multiple metrics at a time and putting them in a nice little summary table. So I'd encourage you to check out our tutorial online. I've got a QR code at the end of the presentation. So that's the package. I'd then like to take a step back and talk a little bit about how I designed this package, what design principles are at play. And I think the primary one is that we really need this to be a simple, fully featured, user-centered interface. And that is enabled with Julia language features. So in terms of the user-centered design, first thing I did was took one of those existing, very manual analytics scripts in Julia, and I was like, how can I simplify this? So in the end, I was able to reduce the number of lines of code in that script by 2/3, from almost 300 to just about 100, and it does the same thing. At the same time, I've really had to focus on ruthlessly eliminating complexity from this. So software designers have asked me again, why not SQL? Why not something? Why reinvent the wheel? Again, our users don't know SQL. Our users sometimes just learn Julia just to be able to use Sienna. So it's really important that there be a solution in this kind of Sienna design language that they took the trouble of learning that works just for them and is designed to be simple just for them. That said, there is kind of an isomorphism with SQL that I'll show later in terms of the fully featuredness of this. Why not a custom tables.jl type to do all that custom metadata stuff? I have considered this, and we might be moving to this in a future design, but for now, people are already familiar with dataframes.jl, and even the slight changes to a like similar interface but a different type seems like unnecessary confusion for the moment if we can make an existing thing that the users are exactly familiar with work. In terms of performance and power, component selector, as you saw, very extensible. You can even define your own subtypes of that abstract type if you want to. It's all transparent to the user. They just need to know about component selector and make selector. Metrics, we saw that you can make your own metrics with the existing types, and you can also subtype metric if you need a different way of computing these under the hood. In terms of performance, we've got this big data set, big simulation of the entire eastern interconnection of the United States, so this giant grid with hundreds of thousands of buses and thousands of generators. I'm running 3 analytics across various, still thousands of generators, subsets of those generators, and the whole thing takes about 1.4 seconds after compilation. So pretty good performance on the largest grid we have. And then on the next slide, I'm going to show that the isomorphism with SQL to do fully featured analytics is there. And in fact, we provide a little bit more power than SQL. So here I've given a table where I've manually computed the component groupings and the component filter function and the timestamp grouping, which Power Analytics does for us behind the scenes. And if we had a table that looked like this in an unpivoted format, then the big long nested SQL query there at the top is roughly equivalent to the general Power Analytics call on the bottom. Julia language features used to design this, lots of functional stuff. So the functor pattern in terms of callable metrics. Metrics in general are pretty functional. So you can see here we've even got this function compose metrics that takes multiple input metrics and a reduction function and creates a new metric that's like the function composition of the constituent metrics, and this is used to define some of our built-in metrics, and users can use this as well. Lots of multiple dispatch, of course, behind the scenes. That's how the component selector extensibility is working. There's lots of subtypes of that under the hood, but the user completely doesn't need to know about any of that. That's how the metric computation works under the hood as well. And of course, the compilation for performance, being able to run arbitrary code in each of these analytics and have it be fast due to compilation. Right now, this is being used at NREL for a few regional studies. I've got a map here of the regional technical assistance projects that we're currently planning and are likely to use Power Analytics in. We're also using this for some extreme events research, and this is a published package, open source 1.0, ready for the community to use as well. Things I'd like to do in the future. I'd like to make the component selector composability a little more fully featured. I'd like to support set operations like set union and set intersection. I'd like to make it a little easier for users to create their own metrics. We've got some performance work to do, I think, some type stability issues that lead to longer compilation times than I'd like. And then maybe one of the biggest ones, I'd like to give the same makeover to our Power Graphics package, which is meant to support plotting in the Sienna design language. And then I've just briefly got some takeaways for package designers. This was my first Julia package design experience, and I learned some things from it. So first of all, I think it worked really well for me to meet my users where they were and ruthlessly focus on simplifying the syntax, simplifying how they need to interact with this package to make it very easy to use. And then I think it worked well for me to work in terms of this theory of abstractions. So I've got the component selectors and I've got the metrics, and those are like objects with a theory of what they do, rather than this kind of collage of features. Things are kind of grouped into those intuitive abstractions, and that really helps, I think, conceptualize the package. And then finally, of course, you should have fully featured documentation that describes in detail how everything works, but at the very least, you should seek to communicate to your users what the package can and can't do, so everyone's on the same page about that and the expectations are managed. I'd like to acknowledge a bunch of my coworkers here. First and foremost, Sarab, who kind of first started this project and secured a bunch of funding for it. A bunch of people helped with design and code review. Akrivi wrote that tutorial that I had a screenshot of. Lots of collaborators here. Here's a QR code to check out the documentation website. It's got a bunch of reference there. It's got the tutorial I mentioned. It's got a link to our GitHub, that kind of thing. And I'd be happy to take any questions.
We have some time for questions if there are any. If not, you can always, yeah, okay.
When you refer to simulations, how do you perform simulations? Is that because you get data from something else and you extrapolate, or what exactly do you mean by that?
Yeah, so simulations are like, we have a system with like a time series of load. So like this is the load that we need to meet, and we're simulating how to turn the generators on and off to meet that load, that kind of thing.
Is it because you want to, I don't know, supply some kind of level of capacity for, I don't know, a specific, I don't know, city or I don't know, something like that?
Yeah. Basically, the way that particular problem works is we want to exactly meet the load, no more, no less, respecting the constraints of the power grid and doing so in a least cost manner.
And I assume the simulations take into account, I don't know, different features in your, I don't know, plant or factory or whatever you call it, I don't know.
Yeah, for sure. So we take, this is very configurable, and there's no one simulation. It's kind of whatever you wanna do. But yeah, we can take into account features of the power grid, features of how the generators themselves work, all sorts of things. I've been developing separately from this the ability to dispatch against market bid prices, so like time variable prices that compete in a power market, that kind of thing.
Any more questions? Okay, give me a second.
Hi, thanks. It's interesting to see a discussion on power system analytics here. I don't see much discussion on, let's say, the shadow prices or just dual variables of the constraints or the simulation model. So I'm wondering if that's part of the analytics where the metrics that users are defining, or is it a feature?
Yeah.
Request?
So the simulation certainly outputs those duals, and so they're there for metrics to grab. I believe our total cost metric does grab a dual, and in general you can certainly define metrics that key onto duals.
Cool, thanks.
Any more questions? If not, you can always find our speaker during the lunch and ask him many more questions. So
I've got stickers, and I've got a completely different presentation later today, if anyone's interested.
All right, let's thank the speaker again. And now I would like to invite Romeo Valentin, who is going to present us a talk on algorithms for validation of dynamical systems. He's a PhD student at Stanford Intelligent Systems Lab.
All right. All set up now. All right. Yeah, welcome everybody to this talk, my talk today on algorithms for validation of dynamical systems. Thank you for the introduction. It's true, I'm Romeo Valentine. Yeah, and I'm part of the Stanford Intelligent Systems Lab. Here's my beautiful group. And maybe you know, some of you might know our professor, Professor Michael Kokendorfer. You can see him there over to the right, kind of. And one thing that Michael has done over the years is write a bunch of books which are actually using Julia as a core part of the books. So Michael wrote a book on algorithms for optimization, a book on algorithms for decision making, and now our lab is releasing a new book. It's currently kind of in the publishing process, algorithms for validation. And one of the really cool things about these books is that actually they have these algorithms and they do the math and they do the motivation for them, but actually instead of giving pseudocode implementations of kind of the different algorithms in these books, it's always actually an implementation in Julia. With the idea kind of that Julia actually is a really good representation of pseudocode, and so usually you can kind of go into this book or these books, kind of take the algorithms, copy them into your code, and run them for the most part. Okay. And so before we continue, I also want to thank actually the authors of the book. So I didn't write this book, but my colleagues at my lab did. Michael, of course, but also Sydney, Anthony, and Robert. I don't know if you can read it there. In the right of the book. So Robert was here actually also yesterday giving a talk on using Julia for teaching. Maybe some of you saw him. He's unfortunately already gone. But if you have a chance to talk to Robert about these things, I can wholeheartedly recommend it. All right, so algorithms for validation of dynamical systems. So what is a dynamical system for the sake of our talk today? Here are two examples of kind of very simple dynamical systems, right? So when I say dynamical system, I mean we have some system that we kind of roll out in time, we kind of step forwards in time. So we have some system environment that we have a pretty good knowledge over the system dynamics, or at least some kind of simulator that lets us kind of do this rollout. And then we have an agent or a controller, you could say, maybe some PID controller, maybe some data-driven controller, and really any black box controller that kind of does something here. And then maybe we have an observation model, which might be noisier or something like this. Yeah, and so here are two examples of dynamical systems. For example, we have the pendulum, a very classic kind of one-dimensional control problem. On the right, there's a kind of a more interesting problem, a collision avoidance system. So that's kind of very near and dear to our lab, right? So here the goal is to kind of fly the airplane, and you encounter another airplane on a collision course, and the idea here is to kind of avoid a collision with the other airplane. So these are two simple examples, but actually the topics in this talk and this book really extend to a very wide range of dynamical systems. So you could, for example, think about having maybe a stock market trading bot there. So you have the dynamical system, the stock market rollout, so to say, at every time so you make investment decisions. And you usually want to keep some kind of safety property true. So for example, your portfolio shouldn't go to zero. Maybe you have a control problem in a power plant on a chemical reaction network, right? And you want to kind of control the temperature or something like this. Yeah, and so in the end, for us, it's kind of all the same. And what is interesting to us now is how can we validate the systems in kind of these safety critical applications, let's say like a power plant or like a collision avoidance system. In particular, in the setting where we have kind of black box controllers and maybe black box environments. So when you have kind of very white box controllers, maybe you understand a lot about let's say the PID controller that you're using in the setting, or you have kind of a very good state space analysis, then you can maybe make some really, mathematical and well understood argument that will kind of help you convince yourself that you have a safe system. But it turns out that kind of in the current day and age, more and more people are using these kind of black box models, let's say data-driven models, to do these kind of control designs, let's say. And then, for example, one example where this can come up is, let's say you build actually this collision avoidance system, and in our lab we have something like this, and then you come up with like a great kind of planning algorithm, and you try to make it fast using some neural network, something like this, and then you go to the regulator and you say, hey, I want to put this into the airplanes, maybe the United plane or the Delta plane that you all are gonna fly home later this week with today. And then the regulator says, okay, hold up, we cannot just put anything willy-nilly into the airplanes that civilians use. So the regulator, you can try to do a lot of analysis, but in the end of the regulation, usually what the regulator asks of you is to give them a probability of failure, let's say catastrophic failure, that your system during the rollout will have some kind of, let's say airplane collision. So I want to ask you all to give me kind of an estimate. What do you think is the FAA's statement, one failure in so and so many hours is kind of the accepted tolerance in the aviation business? So maybe it's one failure in 1,000 hours, in 1,000,000 hours, in a billion hours. What do you guys think? What's that? Million? Yeah. Yeah, so I heard million. That's kind of true. So usually something in 10 to the 7 to 10 to the 9 hours. So, similar order of magnitude, let's say. So we can look here, for example, at just as one example of the kind of Del A certification spec. And so here we can see the probability that they ask for kind of a catastrophic failure to occur is one failure in 1 billion hours. So that's very little. And now a little side fun fact. Now you can actually go ahead and you can kind of count how many hours of commercial flight there is every day, let's say in the US or maybe in the world, and you come up with something like 100,000, 200,000 hours of flight every day. By itself, a really interesting number, I think. And then you can see, okay, so how many days of operation do we need to kind of get to 1 billion hours of flight? And it turns out that it's, approximately 10 years of commercial aviation to get kind of to this number. So if everything works, we have, everything is FAA certified, and then we have approximately one catastrophic airplane failure in 10 years. Now we can kind of think, is that true? I would say it's maybe off by 1 order of magnitude. But I think it's actually very, very impressive that the FAA kind of, can even achieve numbers in these kind of realms. Okay, problem is now we are the engineers, right? Maybe we're all engineers here, and now it's our burden of proof actually to show that our system has a failure rate of 1 in a billion. Well, that's pretty tough. So one thing you can try to do, of course, is you can just kind of roll it out for 10 hours, 100 hours, 1,000 hours, 10,000 hours, your company goes bankrupt, get some more investment, 1,000,000 hours. And even if you have no failure until then, the regulator will still say, okay, 1,000,000 hours, there's still no failure in 1,000,000 hours. We're looking for, something even greater here. And so this is kind of the core challenge that we're trying to address with these algorithms for validation. So really, we're gonna talk about kind of 2 things today, and I hope it gives you some nice ideas maybe for your own work. So one question will be, okay, how can we actually find failures, even if they're kind of very rare, but how can we still try to make our system fail somehow, and then kind of understand how these failures occur, and then also how can we estimate the probability of failure over kind of the entire system without having to roll out, let's say, 1 billion hours, and maybe being somehow more sample efficient. Okay, so the little example we're going to use today is just a little controller lying around. So this is kind of a very classic control problem. So we have here, the car pole controlled by some neural network controller that we trained in Python, let's say. And so I want to point out a few kind of interesting things here, what I mentioned before already. So sure, we're in Julia, we're at the JuliaCon here, but actually this talk, let's say, is more about Julia as a way of implementing very nice algorithms. It's not so much about, let's say, the efficiency and so on, because actually the simulator, it's not run in Julia, it's some kind of black box simulator. You don't need to know actually how it works. This is some Python call interface through the OpenAI gym. And then also the controller, similar thing, you know, you have a black box controller, you don't really understand maybe how this neural network works, you don't understand the failure regions of it inside somehow. And so you need to deal with it in this kind of black box setting. Great, so now we're kind of starting to roll out some trajectories here. Maybe we can resample another trajectory. Okay, looks pretty good. Let me get another one. Okay, looks pretty good to me. And so yeah, the most kind of obvious way to try to find failures, as I described, is just through kind of very naive direct falsification. So I'm showing this example more as kind of a didactic example to understand how the code works, or the algorithms work. Okay, we have just some statement here, is failure of some specification. So we say, for example, you know, the pendulum is not supposed to fall over. And then our whole trajectory, so we always, you know, make a statement about the entire trajectory. Then we have our struct, which we can dispatch on to kind of do the falsification. And then we have a very simple algorithm, okay, m times, let's say 100 times. You know, we do a rollout of the system, and everything is nominal noise, nominal, you know, control, everything. And then we just see if we found a failure. So this is kind of, you know, the approach of we're going to try to roll this guy out a billion hours or 10 billion hours or something. So let's see what happens. We can run it here. Oh, empty list. So we found 0 failures. You know, maybe that's expected, but so this is a little bit like going here, you know, and resampling this guy a bunch of times. And now what we actually want, you know, we can basically resample this many times, but what we want is we want to sample a failure. So let's click the sample failure button. Ignore the warning at the bottom. Aha. Let's check it one more time. Yes. So this is what we're interested in. How can we get a case like this where we actually have found a failure, even in a setting where the failures are quite unlikely? So this is the first thing we're going to talk about, and then we're going to talk about overall failure probability estimation. Okay, so to do the kind of failure finding, one of the ways that the book proposes, let me hide this for now, is through optimization. And for optimization, we kind of need an objective function. And it turns out that we can make a very nice objective function by kind of formalizing the idea of the specification and then going straight off that. So the specification here is something like, okay, we want to always, you know, at every step of the trajectory, we want to have an angle between minus 12 and 12 degrees, let's say. And in Julia, we can use this really nice package that Robert wrote, signal temporal logic, and then we can write it, you know, very nicely, very Julian kind of in this kind of spec. And I just want to note that in this kind of framework of signal temporal logic, there's actually many other nice things we can do. So there's always quantifier eventually until we can specify certain time ranges. You can kind of aggregate conditions with like an AND operator or operator, or have kind of a bunch of, you know, a bunch of temporal logic operators. And then we can use this, we can use this in our objective function for some kind of optimization. So now we want to do falsification through optimization, and the idea here is, how about we take the specification we just said, we're gonna kind of, you know, smooth it out a little bit, so we have this row operator. Okay, it's just kind of saying how much are we, instead of just saying yes we are or we are not in the spec, how much are we in the spec, and then we're going to make it a little bit smooth by saying the always quantifier, we're going to actually replace it by a softmax. And there's kind of this automatic translation that you can do, and this package will do for you to kind of turn the specification, which usually just gives a true or a false value, to turn it into a continuous value. And then you can just plug it here into your optimization objective. At the same time, maybe you say, okay, I also want to find failures that are at least somewhat likely. Maybe they're not, you know, very likely, but let's also put the likelihood of the failure into the objective function. And then you just say, okay, we want to optimize over our initial state, over the observation noise that we see at every time step, right? Then we have a variable here, we do a rollout, and then we kind of measure for the rollout how much is our spec violated and kind of how likely is it. Great, and so this, we can put this super nicely into Julia. So here we're using the kind of SciML optimization.jl with the optim.jl optimizers. Okay, anyways, and then we make a nice optimization function We can even ask for automatic differentiation using finite diff if you don't have kind of the gradients available. And then you optimize over this U. In this U, we just unpack it to be our initial state and our noise at every step. Then you just roll this guy out, and then you measure, the term that we just discussed, and there's your optimization. And so I think one thing that's really amazing here is kind of if you factor this idea correctly, and I think this book really, one of the main values of the book is this kind of really clean factorization of this problem. Great, then you have the objective function, you define some struct to kind of dispatch on again, let's not get too hung up on it. And then you have the falsification algorithm again, so similar to the one we had before. Okay, we kind of shuffle around the parameters a little bit. We make our optimization problem using the optimization function from above. And then we can just sample trajectories by always getting a new initial condition, the U0, and then just solving it with our optimizer. This will give us the noise trajectory. Then we can use the noise trajectory to get the actual kind of trajectory. And then in the end, we just filter again for failures. So if you ask me, this is a really beautiful kind of, concise way to write down what we're trying to do here. So let's try it out. Okay, we're gonna, get our structure, and then we can just run this guy. Takes about 10 seconds. So we're doing 3 falsifications now. Oh. One more time. Come on. Suspense is rising. We're getting there. Okay, there they are. So we find actually, 3 out of 3 successes in getting optimized trajectories that are the failures. And so we can also look at them. So here's what they look like. Wow, very nice. And you can kind of see also, you can go through them and you can kind of see how these failures come to pass. And so I don't want to spend too much more time on this, but one interesting thing here you can do is you can also kind of now investigate actually how these failures come to pass. So we can, let's see, plot the noise on the right-hand side. So this is the nominal noise distribution for the angular and the angular rate noise. Okay, and then here it looks a bit confusing, and if we zoom out a little bit, we can kind of see the noise that the optimizer has kind of found. And so we can kind of go through it and see the noise at each time step, that the optimizer shows to kind of get this guy to fall over. And of course, once we're here, let's say, there's no chance anymore. So this is I think a really powerful approach to kind of do just a basic optimization to find failures for these things. Of course, these failures are still very unlikely, and maybe you can have a better optimizer to get better results here. And so in general, this kind of very simple optimization is one approach, but in the book actually there's many different methods that are laid out to do more complicated variations on this, to do kind of failure finding, let's say through reinforcement learning methods, adaptive stress testing, so having kind of an agent that tries to falsify your system and kind of learns stuff about the state space, or multiple shooting methods, reverse shooting methods, and so on. So the book has kind of a wealth of algorithms that are all very clean, very nicely factorized, and kind of built on this basic idea here. Okay. Yes. So that already gives us kind of one of our 2 goals, right? So our goal was we are here, we're going to the regulator, we want to show them our amazing new product, and they say, okay, can you make some statement about the safety of the system? For example, what do failures look like? Can you find some failures? In this way, we have kind of shown one simple way to find failures, even in this kind of black box setting. And now the other thing we wanted to talk about is kind of failure estimation, failure probability estimation. Okay, so again, kind of the very naive way, which is quite similar to kind of naive way to find failures, is basically we're just going to do many rollouts and count, how many failures we find. Right? So mathematically, what do? We just sample trajectories from the nominal probability distribution, and then we just check every time, is the specification true or false, and then we have our super simple algorithm where we just do a rollout a bunch of times, and then this time, instead of filtering, we just compute the mean, but same, let's say. And then we get our estimate. But of course, this is exactly this issue that we discussed, that now to kind of, let's say you hypothesize that you have a failure rate, 1e minus 6 or 1e minus 9 or something like this. And of course, you don't want to roll out many, many, many times. And especially if your experiments are maybe more expensive. So here, one rollout is quite cheap. But for example, in our lab, this has been kind of tried for work where people are drilling into the ground to find certain minerals, let's say, or have kind of other expensive, maybe medical experiments like this. And so going off of this idea that we saw that we can kind of investigate what failures look like by looking at the failures that we can find and kind of trying to characterize them somehow. What we can do is this really nice thing called importance sampling. So importance sampling here is, again, just kind of the first somewhat nice algorithm in this direction. And how it works here is you say, okay, instead of sampling noise from the nominal distribution, what if I have some extra idea of actually what type of noise will lead to the failures? And instead of just rolling out, a regular, I'm going to roll out according to a more, designed distribution, which we denote here Q. Okay, and then maybe you can find failures with a much higher kind of rate because you know where the failures occur. But now, because we actually want to get probabilities, we need to make this kind of weight adjustment here, which kind of relates the nominal trajectory probability to this kind of proposal probability. And this is actually kind of mathematically justified. And so doing this, you can use way fewer samples if you know kind of a lot about where the failures occur. And nonetheless get this value of, let's say, 1e minus 9, but using only 1e minus 5, or let's say 10 to the 5 samples, something like this. So that can be super powerful, and again, we can have a nice, very clean implementation. We have our struct to dispatch on. We do our rollouts just like before, and now we just do this kind of weighting computation here, which just relates the probabilities of the trajectories to each other. We have again our kind of counting here, but this time with this weighting factor. It all is good. And then here's one example from one of our other works from our lab, what this can kind of look like. So here we try to estimate the probability of failure, once through kind of direct estimation and once by having kind of good proposals and using importance sampling. And you can see the direct estimation has a very large amount of uncertainty, which you can kind of imagine, and only very slowly kind of goes down. And the fit proposal, the importance sampling kind of goes down very fast, and it's very stable here. And so this can be super powerful, especially when experiments are expensive or simulations are expensive and so on. And of course, one caveat here is that you actually need to have a very good idea of where you should put your proposal distributions. And so I'm not going to go into detail on that, but again, in the book, there's many different ways how you can kind of learn where good proposal distributions are and kind of propose, very, very sensible suggestions. All right. Yeah, okay, then you can also do really cool visualization. I don't know if we have time to go into it too much today. Maybe for another presentation. 10 more minutes? Okay. So actually, there's more trajectories here than I was expecting. Let's ignore for now the red trajectories. So one last thing then we can talk about is, so we have seen that we can actually find failures in our agent. Maybe it's somewhat surprising, or maybe not, I don't know. Maybe if you're in engineering for enough years, you're not surprised. And now we can try to understand kind of actually how these failures occur, right? So we were already looking at the noise trajectory, let's say, that leads to our failure, but maybe we can also try to understand actually what about the agent went wrong. And explainability, it's like a huge topic, and I can't even begin to scrape the surface on this, but the book talks about it at least to some extent. And one nice thing we can do is this thing called policy visualization. So actually the agent in the cartpole environment only has two options, go left or go right, so that's very convenient. And then we can make this kind of plot here, which is, let's say, a state space plot, which tells us, okay, we're at some certain x, so this is the location left, right, which shouldn't matter too much in the cartpole example. We're at some certain velocity, and then we have here the theta and the theta dot, the rate. And then we can see actually that this policy is quite linear, and if you think about it for a while, it makes sense. And then you can go around and looks fine, but then if you go a little bit over here, you see that something very strange happens, which is that, sorry, maybe I wasn't clear about the colors. Yellow means, let's say, go left, and blue means go right, something like this. Okay, and we go over here, and we see that there's suddenly yellow again. So this is very strange, because you would expect that kind of, this should be pretty monotonous in one direction. And what probably happened is that during the reinforcement learning training of the agent, you only see certain parts of the domain. You probably, at some point, do a very good job at kind of staying in the center of the state space, and you're nicely balanced all the time, and maybe you haven't been, tried enough. And so essentially, there's like no data. Oops. Oh my God. Essentially, there's kind of no data here. And so here, the agent does something, something random. And so then if we have enough noise on the model, we can see that eventually the trajectories are kind of being wiggled by the noise into this yellow territory, which is the disaster territory. And then you can see the trajectories, they go way out. Yeah, so that's just one idea, a very simple explanation. And of course, yeah, big topic, but the book also has some very nice chapters on that. All right, yeah, what else? Just really quick. So the book also has really great chapters on reachability analysis. So if you have actually a more white box model that you can query from Julia, like more in depth, you can use really great methods from the lazysets.jl package to get kind of a really beautiful, very crisp reachability analysis of your systems, let's say under some kind of bounded noise. There's a great chapter on kind of sampling failures according to their probability, right? So we can of course sample nominal trajectories, but what if we sample only failing trajectories? And there's a beautiful connection there to probabilistic programming using Turing.jl, which I can very much recommend to check out. Yeah, explainability, nice chapter, and runtime monitoring, which we didn't have time to talk about. Right, yeah, and so if I managed to pique your interest, I can recommend maybe go on YouTube, and there's actually the entire lecture series that Sydney gave at Stanford. It's all freely available on YouTube, so that's going to be Stanford AA228V, and I can highly recommend to check it out. There's also some beautiful animations that are in the lecture slides there. Wow. Okay, very nice. Yes, and then finally, of course, I can recommend checking out the book itself. Yeah, and that's it. Thank you. So maybe as my last note, I still wanted to say, I think one thing interesting here is you can see that if a company tries to stress test their system, what they can do is they put it out in the real world, but instead of giving it only nominal, boring trajectories, they give it the most hard-hitting trajectories possible, because that's how they get the info. So next time when you go to, maybe the latest self-driving car or the latest self-flying airplane, you can think about that. Okay.
Right, we have 5 more minutes before we break for lunch. So, any questions for the speaker? If not, I do have a question. So I myself work on research in the field of structural reliability. And it seems to me what you're doing is exactly reliability analysis for different dynamical systems. And I don't know if I'll trigger the right words for it, because I don't work with dynamical system myself. So I work with structures. I like them not to move, basically. But what you're effectively trying to do is do first passage reliability analysis just to get the probability of time till failure starting from some initial position, right? And because your physics are complex and they involve some chaotic physics in it, you're just trying to reconstruct the response surface of your dynamical system to accelerate the process. Yeah? That's what basically you're trying to do?
Yeah, so I think that's a very good kind of model of at least some of these algorithms, that you say maybe the model is black box or it's just too complicated for you to model properly. And so you basically try to build stress testing agents that maybe they manage to learn a lot about the dynamics, but sometimes what's enough is to learn kind of about the regions of catastrophe, let's say. And if you can kind of find those regions and model those regions using some algorithmic approach, then you have a kind of a very good stress testing system.
And do you find that you can do very good fit of your machine learning model on a dynamical system if it's even a chaotic, given like double pendulum, say? Can you do a good fit on it to be able to do this good reliability analysis with the response surface you're reconstructing?
Yeah.
Or is it not a feasible thing and you need to go very deeply into like satisfying very strict tolerances in your dynamical analysis in the first place to get the data set?
Yeah, so I would say, I mean, if you have a double pendulum, I would say you don't have a chance. Because, for example, you know, so I showed this optimization algorithm, and in the end, there's a lot of optimization-based techniques that we're using here. But of course, how optimization usually works, you try to think, okay, what little step can I make to kind of improve or decrease my optimization objective? But if you have an extremely chaotic response, the optimizer just has a really tough time. And actually already here, I found this, right? So you always roll out the kind of system and you have this card pole, and maybe previously you had a regime where you would kind of fall over to the left, but now because you've changed a little bit the noise, now already in the start, the card pole goes off to the right instead of the left, so actually everything changes. And this kind of time sequential thing has some chaotic, a glimpse of chaos, let's say, in there. Yep. And it's definitely a challenge for these type of algorithms, yeah.
Okay. Any more questions? Yeah.
Hi, great talk. Question about particularly the experiments with the agent and the reinforcement learning. One thing that I found very difficult is getting the agents to explore the state space in a productive way. Like the thing with sampling methods for like your control inputs is that you can't just have any random signal that's going to take you to some part of state space. It has to be like well designed to like get over the dynamics and take you where you are. Are there any, what's the literature nowadays when it comes to that? And is there anything in this particular package that could help in that journey?
Yeah, so first of all, I want to say I'm not an expert on reinforcement learning, but I can say maybe some things about it. Before I answer your question, I will actually say something else. So this is what we call the expert agent, and we train it in some REPL setting, and then we have this interesting situation where we have this going on here. And then we trained a second agent using so-called as a student policy. So basically you train another agent to imitate the expert, and we found that this goes away and the student agent was much more. Mm-hmm. It's fine. I think it's not too important. So we trained a student policy, and it was much more robust, which I think is, so this, I would say, one of the pieces of literature that I know is doing a lot of the sim to real transfer.
Behavior cloning, right? Is that what
yeah, it's very strongly related, yeah. Behavior cloning to get rid of this. Otherwise, you were asking about how to kind of efficiently explore the state space. And actually, I would say that these methods we present here, you can of course also use them kind of during training. So let's say we call this here stress testing or falsification, right? So you give it like a training run, a couple of epochs, then you have an agent, then you run this kind of failure finding algorithm on it, but you find a bunch of new interesting cases, and you put it back into the training data, and then you kind of loop this around, and now you can at least try to build a much more strong system. Well, what we're finding actually is noise at every time step that will lead you there. So we're not optimizing the state directly. We're optimizing, let's say, observation noise at every time step, such that the trajectory will go somewhere. Yeah, and then the initial condition also. But yeah, anyways.
In terms of complexity of that optimization, have you looked at like regions of initial conditions or putting distribution on the initial conditions? And maybe it doesn't matter that much for the pendulum, but in more complex systems.
Yeah, let me give me like 10 seconds here. Okay, I think we're out. Okay, that's fine. So you were asking about kind of reasoning about the initial condition, right? And so we have a probability distribution for the noise at every time step, and also a probability distribution for the initial condition. So you can, in the nominal case, you would just sample kind of initial conditions, and then also during the optimization, it's part of your optimization variable that you try to find kind of challenging initial conditions while maximizing their likelihood under the nominal distribution.
And what impact does that have on like the convergence or complexity of the optimization?
Yeah, that's a good question. So in this particular example with the pendulum or the cart pole, so obviously when you start kind of amazingly centered, it was very challenging to find failures. So one of the kind of reliable ways that I found when I made this notebook to like get some nice failures is to allow kind of initial conditions that are already like that the agent really has to like work already. So if you start in a very stable regime, yeah, it's the agent is kind of unfailable, I would say. Yeah. All right.
All right, I guess with that, we thank you, Romeo, for your talk.
Thank you.
And now we break for lunch for 1.5 hours. We'll see you back at 1. Talks. Yeah, thank you.
If it's not here, it's not here.
At this point of in your state space, you fail because your trajectory evolves, and before it reaches $1 billion, you fail. And for others, it doesn't. So you have a, and then you can do all sorts of variability analysis, like you can predict the variability and extra failure. I mean, I'm going to have a poster about that. Okay, yeah. What's the biggest goal? Fortuna and Jam. Okay. I actually wrote
Okay, we're continuing here and with the engineering with Julia mini symposium, and I'm happy to introduce the next speaker. You ready, or is it? That's not.
I think it's starting up again.
Oh, it takes a little time.
Oh.
I don't know anything about this system.
I don't know. Well, apparently you can see it back there. Should I? Okay. Oh, good job. Cool. That was good. That was shape.
It's Rajiv, right?
Yes.
Yeah. Here's Rajiv. Thanks a lot.
Does this work? Oh, cool. I'll be presenting a compilation of Julia code for deployment in model-based engineering workflows on behalf of my colleague, Dr. Frederick Carlson. So we'll begin by walking through the Julia compilation pipeline to set the stage. Then I'll cover how AOT compilation of Julia has historically worked, where we are now, and where we are headed. We'll then look at two demos, one that compiles a Julia-based executable for state estimation, and another that turns a Julia PID controller into a shared library that can be called from C. And finally, we'll discuss the current limitations of the workflow. Julia typically compiles just ahead of time, or JIT. The process starts with source code, which goes through type inference and optimization. This is followed by generating LLVM, intermediate IRs, then LLVM optimization, and finally producing native code for your target architecture, such as x86-64 or ARM. The point here is Julia isn't traditionally ahead of time compiled, but that's changing. So historically, you had two options to distribute Julia programs. One was to simply distribute the source code, which of course requires a Julia installation. The other was to bundle everything into a giant binary, so your source, compile code, Julia and LLVM compilers, and the runtime. So this gives you a self-contained artifact with full language features intact, but it was huge, multiple GBs, and not always relocatable. Yep. So now, and specifically in the near future, we're taking a more refined approach. We trim everything that's unreachable from the entry point. If there's anything we can't compile, like calls to eval or code with unbounded types, we complain. This means that we can guarantee that what you get is actually ahead of time compiled. For example, a hello world can now be under 1 MB, and we lose a few dynamic features like eval, but most of the language is still usable. What you're seeing on the left is our toy function. It generates a 2x2 matrix. If A is less than 0, then computes its sign. On the right, we're inspecting the method instance of this function using code warn type. what this shows us is what the compiler sees, the inferred types. This is useful because it reveals a few key things about ahead of time compilation. We can see here that all the types are fully inferred. This is important because in AOT, everything must be known and concrete at compile time. If there's any ambiguity, say from dynamic dispatch or eval, compilation will fail or generate inefficient code. So is this okay? Well, if your code is written in a way that the compiler can reason about everything statically, that's the deal with AOT compilation in Julia. If the compiler can see through your code all the way down to the types, you're good. Otherwise, it won't work. So part of the workflow becomes writing Julia code that's compatible, and that's a slightly more constrained subset of what the language allows at runtime. So let's look at two concrete demos. First, we'll create an executable for model-based state estimation. This uses equation-based modeling and standard Julia libraries. The second, we'll compile a PID controller library into a shared object and call it from a C program. So in the first demo, which is the model-based state estimation, what you're seeing here is a typical example from control engineering. We've got an equation-based model, in this case, the continuously stirred tank reactor, and we're going to build a state estimator for it. So this combines two powerful Julia tools, modeling toolkit for symbolic equation-based modeling, and a standard Julia package for state estimation, in this case, the static Kalman filter. So the source is available through the QR code. The key idea is to use standard Julia tools and compile this into a standalone executable. So it loads the data file and runs the filter. So this demonstrates how you can take something very high level and bring it all the way down to like a deployable binary. So we're working with a continuously stirred tank reactor, or CSTR. For those who aren't familiar, CSTR is a common benchmark system in control and chemical engineering. It's basically a tank where a chemical reaction takes place with fluid flowing in and out, and everything is constantly stirred to maintain uniformity. This kind of system is nonlinear and time varying, making it a good candidate for demonstrating state estimation. So we define the model symbolically using modeling toolkit.jl, and then call generate control function to generate Julia code for simulation or estimation. So from a high-level symbolic description of the physics, we are now producing concrete Julia functions that can be compiled and deployed. Once we've defined the model and generated the Julia code, we compile it into a binary. The workflow here is include the generated Julia code, discretize it, define the state estimator, and run the filter on measurement data. Here's what we get. The binary is about 3.5 MB, and when we run it, it finishes in 27 milliseconds, or that the actual filtering step just takes about 62 microseconds. So this demonstrates that you can take a symbolic model, generate and compile it, and run real-time state estimation in a highly performant way with a very small deployment footprint. So this next demo shows how a Julia package, in this case discrete PIDs, can be compiled into a shared library and used directly from a C program. So unlike the previous example, which produced an executable, this flow compiles the Julia code into a shared object file, and that shared library can then be loaded and called from C, making it easy to integrate Julia-based control logic into external environments without needing to run a Julia session. It's a simple but powerful way to bring high-level Julia functionality into low-level systems. So to make the Julia functions callable from C, they're annotated with C callable. So this macro exposes them to C-compatible entry points, which allows external programs to link against them, just like they would with any traditional C library. After compilation, the result is a shared object that's about 1.7 MB in size. That's relatively small and makes it practical for deployment in embedded systems or performance-sensitive environments. So the source code is, again, available publicly on GitHub, on the QR code shown. Once the shared object has been compiled, it can be loaded and used from a C program This is done by linking the C program to libjulia, which is Julia's runtime shared library. The compiled Julia code relies on this at runtime, so the C application needs to load both the PID control library and the Julia runtime. So this setup works today, but it's important to note that the binary is not yet fully self-contained. You will still need to ship libjulia alongside your application, but there's some manual configuration involved. That said, this is a practically functioning pipeline that shows how Julia code can be embedded and reused from C. So the same compilation and deployment approach works on resource-constrained platforms like the Raspberry Pi. The executable runs about 4 times slower on the Pi compared to a typical laptop, but that still leaves plenty of room for real-time or near real-time applications. At the moment, there's no first-class support for cross-compilation, so the recommended options are to either compile directly on Raspberry Pi or use an emulator. There are still a few limitations to be aware of. First, the Julia runtime is still required, so this only works on platforms Julia supports, like Linux, Windows, Mac OS, and common architectures such as x86-64, ARM v7, v8, and RISC-V. There's no support yet for real-time operating systems or deeply embedded targets like Arduino. The runtime itself is not yet trimmed, and cross-compilation remains an open issue. Also, these features haven't been officially released yet. They're still under active development. That said, all of these areas are still being actively worked on, and improvements are expected in upcoming Julia versions. So the natural question is, should this workflow be used today? And the answer is it depends. So for people who are deeply familiar with Julia and comfortable working with close to the internals, possibly building custom toolchain or debugging low-level issues, it may be worth exploring. But for most users, especially those looking for stable, streamlined experience, it's probably best to wait until this is officially released and supported. So to summarize, Julia code can now be ahead of time compiled into a relatively small binary or shared libraries. So most language features are preserved, though highly dynamic features like eval or unbounded dispatch aren't supported. These capabilities aren't yet available in a stable Julia release, but support is very close. This has practical implications for reducing the size of Julia FMUs and deploying Julia models more efficiently. And finally, if you have any questions, please feel free to reach out. Yep.
Okay, well, we have plenty of time for questions, I think. So are there any out there? Here, okay.
Hi, thank you very much for the presentation. When you compile those codes and put in the Raspberry Pi, did you try to measure something like latency or let it execute for a very long period of time to check for memory leaks or something like that?
Cody, do you have an answer for that?
So I'm not aware of any specific late testing, although Frederick probably did do some. I just don't think we have them on hand right now. But specifically for allocations, I know that he was using allocheck alongside this process to make sure that it doesn't have any usage of the GC either. And so we don't expect anything like memory leaks or GC pauses to be an issue.
Any other questions? There's one right here.
Regarding your first example, do I get correctly that you still use the trim functionality to compile it, right? So it's, in essence, the difference between them is just like who calls Julia isn't like main self-generated by Julia, or it's foreign from C.
Sorry, are you talking about the continuously stored reactor model?
Yes, yeah, that one.
So I didn't get your question. Sorry, could you repeat that?
So in that case, what you show is essentially similar to the second example. So it also uses Julia runtime, right?
Yes. So the first case is, or more to say, the second case is building a shared object file, and the first case is an actual executable. So
okay, so that's the only difference between them?
Yeah.
Okay, I didn't get it.
And I don't know, Cody, do you want to? Okay.
Oh, all right. One thing, it's not really a question, sorry, but if somebody is interested in this, we at ASML actually use it. So we have a talk today at 2:30 and tomorrow at 11:30, where we will talk in details like performance, interaction with the system, and so on. If you want to find them, I'm Yuri. You can find my talks. I'm participating in both.
Cool. Yeah, I'll find you.
Yeah, we try to use it in a real environment in the production. So I agree with your summary that it's not that like production ready if you don't want to invest in it, but it's possible if you invest in it.
Yeah, that makes sense.
Any other questions? Okay, all right. Well, let's thank the speaker one more time. The next presentation will start at 2 o'clock.
a whole lot, no. But I'm given a handful. Some best man speeches.
Okay, all right,
Valedictorian speech.
Well, oh, all right, nice.
And then some speeches, or some presentations at the office.
Yeah. Huh? I'm sitting right there with the posters on the left. But it's a little hard to see the screen. Like, I wish I should move over.
No, thank you. I mean, no, I think I'll be fine. I guess if you want to, I'll.
Just in case he has a meltdown.
Yeah.
Throw it on his face. There's some scribble on the whiteboard. That's what I need.
No eraser.
There's no eraser.
Well, maybe I can go grab some paper.
Oh, here you go.
Oh, there you go.
You don't want it in the recording, right? Not that it matters much, but hey.
Are you presenting on LVP?
Yes.
Ready?
Okay, we're starting the next presentation. This is Cole Miller, bridge engineer from HDR. He's doing a lot of Julia work.
All right. Hand calcs, calculations you can read and reuse. First off, I just want to say thank you to all those who helped me bring this package to life. A few names who helped me on the various Julia community channels are listed: Adrian Bramer, Matt Bauman, and Mose Giordano were some who consistently helped me with the questions I posted, and I don't know if I would have figured things out without them. Connor Forster is another I would like to thank. I took his Python course for structural engineers, and I would recommend it to any structural engineer who would like to learn Python. He's also the creator of handcalcs.py, which is an amazing Python package, and this package is an implementation of that package for Julia. I also want to thank the creator of and maintainers of laticify.jl. Handcalcs under the hood just calls laticify, and it does all the heavy lifting. Lastly, I want to thank Tim Holy for creating code tracking and revise. These packages provided the tooling for what I think is the most valuable part of handcalcs, which we'll get to later. So a little bit about me. I'm a bridge engineer in Dallas, Texas. I was first introduced to programming in college through MATLAB, and I quickly found I really enjoyed programming. Now I code somewhat regularly, mostly use VBA and Python. But my favorite language is Julia, and I've been using it in my free time for the past year and a half, and I hope to use it in industry. And I think this package could provide a valuable reason to do that. So I wanted to show it to you today. So a big part of being a structural engineer is documenting our calculations so someone can verify our work. I wanted to show you some of our current tools for doing that. Our main tool is Excel for documented calculations. I personally love Excel, and combined with VBA, it can be a very powerful tool. I think Excel's greatest strengths are that it's fast, it's easy to use, everyone knows how to use it, you can change it easily, and its reactivity is unmatched. The actual cells, though, doing the computation don't actually show the work being done, so we typically have to manually add in a cell to the right, documenting what the cell did. You can see an example of that in the image shown. The cell highlighted in blue is showing what the cell to the left is computing. It can be a little complicated to read for some of those longer formulas. Another tool that is used by structural engineers is MathCAD, and for some this is preferred over Excel. I think for some it provides a more readable calculation as well as including units with proper unit conversions. So it's a nice tool. And you can see an example of that in the image shown. And so here's a little snippet of what handcalcs can generate when working through Quarto. And the question is, can handcalcs become a useful tool when creating documented calculations? And I'm hopeful, but I think there's still some pieces needed for a better user experience. So here's kind of just a summary of what I think, how they rank against each other. And I would say in terms of readability, reusability, version control, and testing, handcalcs is like really good. And the areas of improvements would be like ease of use and reactability. So now for the demo of handcalcs. After installing handcalcs, as you would any other Julia package, all you need to do is call these two packages to gain full functionality. Most of you likely have revise in your startup.jl file, so all you really need to do is call using handcalcs. So handcalcs exports two macros where all the functionality stems from, handcalc and handcalcs. Think of handcalc as doing a single inline LaTeX expression, and handcalcs as a multi-line equation. I recommend using handcalcs. It inlines into Markdown, handles multiple expressions, and cleans up equations of redundant information. So here's a single expression example. Let's try to calculate the area of a circle. So the first line here, I'm just setting the variable d equal to 5, and that'd be like the diameter. And then in this next line, it's basically the equation of a circle, and all you have to do is put handcalcs in front of it, and handcalcs will render the equation shown. So handcalcs was able to show the equation defining area as a LaTeX expression, showing both the symbolic and the numeric parts. And yes, the variable area was also evaluated. So the number of decimals in that above expression may be too much, so we can change that. We can use the set handcalcs function and set the precision equal to 2. And now running that same line there, you can see now it's reduced the number of numbers after the decimal. So here's a multiple expression example. So here I'm just setting variables b and h equal to 5 and 15. When you have a multiple expression example, you want to wrap your equations in a begin and end block. So here I just have equations for ix and iy, and if we run that, you can see handcalcs is able to render both equations nicely. And yes, iy and ix are evaluated. You can also use strings to add comments to the equation. So here's just that same ix equation, and I've added in a string on the side there, and you can see that. And now handcalcs will render that string in parentheses to the right. Using semicolons are nice, so you can see, you can make the code more readable. In reality, it's just this. This is equivalent, and you can see it renders the same thing. So working with known variables, say we previously defined variables, assume these are constants, inputs, or previously calculated variables, we can render those out nicely. So recall the ix and iy variables we created. And then here in this last line, you can see I've specified columns is equal to 2, or calls is equal to 2, and color is equal to blue. Calls is equal to 2 is going to split the equations into 2 columns, and color will change the text to blue. And you can see that there. So when the equations are too long to fit on a page, you can use the length is equal to long. So here I just have some variables I'm defining A, B, and C. And in the handcalcs block, I've got just the quadratic formula. And then at the last line there, I've got length is equal to long. And you can see handcalcs renders it in multiple lines. So you can change the default settings similar to LaTeXify. Handcalcs has a way to change some default settings using the set handcalcs function. A number of these we've covered. Most of these you can use at the end of the handcalcs macro, as I've shown previously. And the set handcalcs function just allows you to set these as defaults instead of having to change the setting every time you use the macro. So we've gone through columns, SPA spacing, change the vertical line spacing between expressions. Length we covered, color, changing the color of the output. HM, this is for people familiar with LaTeX. You can change the environment from aligned, which is the default, to like align or other LaTeX options. HRender we'll cover in a little bit here. You can choose between equation, symbolic, numeric, and both. Precision, we saw an example of that. Changes the default number of decimals, or numbered after the decimal that are rendered. And not funcs, parse pipe, parse ifs we'll get to later. And disable is just, you can disable handcalcs, and everything that's in the handcalcs block will just run as if it weren't in the handcalcs macro. So setting the rendering format, like handcalcs provides a setting to change to a different rendering format. The choices are between equation, symbolic, numeric, or both. And so this is an example of the equation rendering. So you can use the set handcalcs function and set the hrender to equation. And when you run this here, you'll see it just shows the equation and not the actual result. But IX is still evaluated. Symbolic, you can use the hrender again to switch to symbolic, and that same equation, you can see it just shows the symbolic parts. And then numeric, similarly, it'll show the numeric parts. So this is really meant to be a setting overall, but you can use the set handcalcs function to turn the setting on, and then use it again afterward to turn it back to the default. So this package integrates with Unitful and Unitful Latexify. If you're going to use Unitful, recommend using Unitful Latexify as well. So an example of this, if I have A and B and I set them to 2 inches and -5 inches and run an equation, handcalcs will render the units inside of the equation, which is nice. And so you can use the pipe to convert output to a specified unit, just like you can in Unitful. And so an example of that, like let's say I had B is equal to 40 feet, T is equal to 8.5 inches. That equation A is equal to B times T. Unitful wouldn't promote that to a default unit, so you'd have feet inches. And you can use the pipe operator to change it to inches squared, and handcalcs will run that, and it will convert the output to inches squared. And you don't see all the, the pipe in the equation, which is nice. So the best part, function unrolling, the handcalcs macro will automatically try to unroll the expressions within a function. The expressions must have the following pattern. So a variable equal to a function call. This is recursive, so if you have functions that call other functions, it will continue to step into each function to unroll all the expressions. One issue that can arise for the functions that you do not want to unroll, consider the expression y is equal to sine of x, or y is equal to x plus 5. Both of these expressions match the format, variable is equal to a function call. And so they would therefore be unrolled. This would result in an error since these functions don't have generic math expressions that can be Latexified. So you'll need to use the not funcs keyword to manually tell the handcalcs macro to pass over these functions. And some of the common math functions that you will not want to unroll are automatically passed over. So here's an example of that. There's a function that's defined in the test handcalcs function package called calcix. The definition looks like the following. It's basically the IX equation that you had seen previously. So if we try and call that function with our handcalcs macro, we'll bring in the test handcalc functions package. We'll set B and H equal to 5 and 15 like before, and then we'll call that function with that similar variable equals function call. And you can see when handcalcs renders that, it actually finds the function, steps into the function and pulls out the relevant equations in that function. So the ix variable is evaluated, ix being the variable assigned in the handcalcs part. Variables within the actual function are not defined in the global namespace. And I guess there's a caveat. Return statements are filtered out of the function body, so keep relevant parts separate from return statements. So here's an example of a recursive unrolling example. There's a function defined in the test handcalcs function package called calc_eyes, and you can see calc_eyes calls calc_ix, and it also calls calc_iy. So if we try to call that, you can see the format there. It actually returns two variables, ix and iy, and you can see I'm pulling that out, ix and iy, in the handcalcs body, and handcalcs is able to take care of that. And so when this runs, handcalcs is able to find both of those equations within those functions. So it's recursive. So debugging function unrolling, if you encounter an error, you can use the showfuncs keyword. This will print out all the functions handcalcs stepped into. So for example, this same function call that we did just before, if you add the showfuncs is equal to true there, handcalcs will just print out each function it stepped into. There was no error here, but you can see the handcalcs stepped into all three functions. So unwanted function unrolling, so let's try to call sine and cosine. So I'm just going to set x is equal to 0. And then, so since we don't want to unroll sine and cosine, we'll specify not funcs is equal to sine and cosine. And so handcalcs will see this format, and it'll see that it's in the list of not funcs, so it'll pass over it, as well as the cosine one. And so then you'll see that it just calls the function call in there like you would want. So stepping over functions, so there's a default list of current functions that handcalcs macro steps over. Here they are, and they're listed in the documentation. And if you want to add functions to your specific project, you can use the set handcalcs function and use the not funcs keyword. Working with structs, so if you have functions, so I guess here's a side note, if you have functions that are outside of a package, you'll need to use the includeEt function from revise, as well as wrap the code in a module. So if they're not actually in a package, you'll have to follow these steps. So here I've wrapped the file in a module, and then here's just a simple struct, a rectangle struct with a length and a width, and then I've got the calc area for that rectangle struct and a calc perimeter. So if I were to bring this in, I would need to use that includeEt function and revise, and then in line 4 you can see I'm just initializing that rectangle struct. So if you recall that calc area function, let's see if we can call that. And then here's the line, handcalcs area is equal to calc area, and then I've got the rec variable in there. And you can see handcalcs is able to step into that and pull out the equations. So you can avoid that object.variable syntax by using the struct unpacking Julia syntax sugar. So like for this calc perimeter example, I've got the unpacking syntax sugar there in the function definition. So I'm pulling out the length and the width like directly. And so you can kind of get by with that object.variable syntax. So if I call that, you can see handcalcs is able to step in and render that function, or that equation. So if statements have two different formats. The default format will show here. So this is like a simple if statement, x is equal to 1. Since x is less than 5, we're going to be in that else branch. So handcalcs will render that, and you'll see that since line, since x is greater than 5, that's false. We're just showing that x equals 10 branch. And then the other option would be the LaTeX format. And so here's the same if statement, and you can just you can specify it with that parse ifs is equal to false, and you'll go back to the LaTeX format, and you can see how it shows it there. It shows both branches. So the benefit of using the default format is it works with function unrolling. So here's an example of that. I've got b is equal to 1. Since b is less than 5, we're going to be in the else branch. I'm calling that calc ix function. And when handcalcs renders that out, you can see that calc ix function has been unrolled. Whereas LaTeX format won't function unroll. And so you'll see just the function call itself. So writing packages, handcalcs was built with the intent to build packages with it. These packages do not need any dependency on handcalcs. So I just wanted to give a demo of this package I've been writing. AISC Steel is a package that was built as a tool for structural engineers. It has also been the package that I use to test the limits of handcalcs. It covers the steel reference manual that engineers use to design steel structures. Here's just like a little snip of the manual. The manual is just full of mathematical equations with a reference to those. And I've just implemented those in this AISC Steel package. So let's go through a basic calc that we would do using this package. We will use handcalcs to generate and display the equations. It's important to note that the AISC Steel package doesn't know about handcalcs. AISC Steel has no dependency or extension for handcalcs, but handcalcs is able to render out the functions inside handcalcs. For the example, we will go through calculating the bending strength of an I-shaped member. You can see an image of the shape there in the lower left. It looks like an eye. The image of the lower right shows what we would be after. What is the max load P that the I shape could take? So just like, I guess, some basic information of this calc, there's basic failure modes of an I shape that you'll have to watch out for when checking bending. The upper left is the failure mode that will occur if the other three do not. This is the theoretical maximum strength of the section. Then you have the flange buckling and the web buckling failure modes. Basically, if your flange or web is too thin, then your flange or web will buckle before you ever reach the first failure mode. So we classify the flanges and the webs first to see if there will be an issue. And then the last failure mode, the sketch in the lower left, is dependent on the unbraced length of the member. This is called lateral torsional buckling. Basically, if the distance between braces is too long, then the entire beam will want to buckle sideways and start to twist. So depending on the slenderness of the flanges and the webs and the distance between the brace points, the I shape will be governed by different equations. And now we'll show how to use handcalcs to only show the relevant equations. And we can use it to generate a nice report. So first, I'm just importing AISC Steel in the various submodules. This phi B is just like a reduction in the overall capacity. Typically just take 10% off as a safety measure. And then this line, I'm just initializing the W shape. This is a W10 by 12. It's basically just looking through a database and pulling in a bunch of parameters. And then LB is just the length of the beam in our case, and that's 10 feet. So we can pull out the parameters of the W shape with the unpacking syntax in Julia, and then we could show those in handcalcs, just putting those in the handcalcs block. And you can see I've got columns is equal to 4, colors is equal to blue, and that renders out nicely. And then first we want to check the flanges and the web. And so this function call is just a function to check those flanges. And you can see just it's pulling out multiple variables, and handcalcs is able to handle that. And you can see it unrolls all of the equations in that function. In this case, the flange is non-compact, so since it's not compact, we'll have to check that flange buckling in our case. Checking the web, it's similar. So if we just run that, we'll see the web is compact, and since the flange is non-compact and the web is compact, we're in the criteria called F3. So there's a lot of code here, but the first one is basically just the call to the first two functions that I showed, and it's gonna spit out F2 or F3. And then, so I've got this if statement showing if it's F2, I wanna do this. If it's F3, I wanna do this. And then looking at this part 1 heading and part 2 heading, this is pretty neat because you can dynamically change the titles of your sections. And so you can see F2 versus F3, they're different titles. And then lastly, in the hand calcs part, this will be the relevant equations that are rendered out instead of the F2. So running this, you can see it rendered that out, and it rendered out all of the equations there. And then next, we need to calculate the lateral torsional buckling. Here's just kind of an image of what that looks like. This would be a real-world example of what that would look like. So we want to avoid anything like that. And so here I'm just putting part 1 heading and just outputting that. So we get a nice title, dynamic title. And then this part 1 check, I'm not in F2, I'm in F3. So this part will be the thing that renders out. And you can see that there. Next would be compression flange local buckling. And you can see the failure mode there in the image. And then this would be like a real world example. And so very similarly, part 2 heading, it's nice and dynamic. And then I'm gonna show the relevant equation for F3. And you can see that there. And then lastly, for F2 or F3, I'm gonna pull the minimum of those 2 values and those render out. So there is a function that does the whole calc, and that's the calc MNX, and you could use that to be like as a check. I guess you could use hand calcs to render that whole calc, just using the one that does the whole thing, but it wouldn't be best for like a report. But it is great if you want to run it and just have a deeper understanding of the calc, and you can see that it runs all of what we showed earlier. And lastly, calculating the max load P. Now that we know our capacity, we can calculate P, which is about 8 kips, which is about 8,000 pounds. So reporting this entire document was created with Cordo and Cordo Notebook Runner, and you can use it to create professional looking reports like so. And that's just an example of the report. Thank you.
All right, thanks, Cole. Are there any questions? There's one in the back. I'm first. Oh, there's a lot of here. I'll go back there because I saw it here.
Hi, just a quick question. Do you think that using something like symbolics would help you to do the function tracing? Because it already has support for like registering functions and a lot of things that are already registered. And it is also compatible with LaTeXify.
Yeah, symbolics and how it doesn't work with hand calcs. Yeah, just the way hand calcs is the numeric substitution part, it actually needs that value of A. And when you set the symbolic A, now you can't have a numeric number there.
you can call substitute and you can give it a dictionary and it can do any substitutions you want.
You can call substitute, but I think still in main, like in the main global namespace, it's still a symbolic variable, symbolic struct. So the way Handcalcs works right now, it wouldn't work. So yeah.
Okay.
Maybe you can work on that more.
Yeah.
All right, there were some questions down here. Who would like to go next?
I was wondering how you capture basically the different operations when you unpack the functions, right? So in other words, if somebody wants to maybe only display a subset of the calculations in a function, how does that work?
So right now, what it's doing is, so code tracking will, if you supply the types, code tracking will give you the whole function body as a AST. And then I take that AST and I take out all of the equations. And then since I had to escape the macro to get the types, I then have to use eval for the function unrolling part. But yeah, that's the basics of how it works. I basically pull that all into an AST, I run it, I wrap it in a let block so none of it, escapes to the global namespace, and so yeah.
Wonderful. I mean, as a structural engineer, super cool.
Hi, thanks. Two quick questions. Just to be sure, when you said the precision is only for the printing, right? Internally?
Yeah, only for the printing.
Okay.
Yeah.
And the second one is there any chance for this to work in terminals or only in graphical interfaces like Jupyter or something like that?
Journals, you said?
Text mode, terminals.
Oh, terminals. Yeah, so it outputs a LaTeX string, if you know that package, LaTeX strings. So that's what it outputs. There is a potential that you could have multiple backends. So right now it's LaTeXify, but I know there's a typed LaTeXify version maybe in the works. So you could maybe have a backend there. So yeah, there's potential for it, I guess. Yeah.
Thank you.
Okay, thanks again. Let's thank Cole one more time. We're having a little trouble getting the screen display.
Did we use this laptop before?
In another room.
Look at your graphics property, see what it's putting on. Oh, it's trying to force 4K out. You have to go to graphic display properties and take it down to 1080p. Those settings can. Is that for both display?
It doesn't detect a separate display. It's on Google Slides, so we can
Okay.
Okay. Oh, sure, here we go.
We're just going to put it up on that one.
Yeah.
No worries, we got time.
What's the best way for you to get the songs from here?
Okay, good job, Benjamin. You passed your first test of the presentation. Let's hear about launch vehicles and Julia.
All right, thank you very much. Sorry for the technical delay. I'll be talking about ignition point reachability for aerodynamically controlled reusable launch vehicles. The basic problem is something that most of you have probably seen before from SpaceX et al. We have a reusable launch vehicle that has an aerodynamic phase, is descending towards a launch pad, then the engine reignites, and then it actually lands on the launch pad, sort of touching down softly. In this talk, I'll be talking about the phase of flight between supersonic retropropulsion, so when that cuts off to when the vehicle actually touches down. The interesting problem that we're investigating here is what happens if the engine doesn't turn back on again. And we actually saw this quite recently with the first flight of New Glenn, wherein the proximal failure of that vehicle was that the engine failed to relight and then the vehicle went aeroballistic and hit the water. Especially if we're landing on land, we would really like this to not happen into something expensive or important or full of people. So the problem that I'm going to be talking about in this presentation is where can we put that ignition point? Where can the rocket decide to relight so that it can still land at the end? And then once we have this volume for a given initial condition, we can go, oh, this part of it doesn't make sense because it flies into something expensive. Or this part of it is safer, type of thing. And still guarantee dynamic feasibility all through for any ignition point that's selected in that volume. There's three aspects to this problem that I'll be talking about. There's the underlying dynamics of the vehicle, there's the trajectory optimization that identifies feasible trajectories from the initial condition to the landing site, and then there's the reachability analysis problem that allows us to identify that intermediate position where we relight the rocket engine. So looking at the dynamics of the vehicle first, the vehicle is an axisymmetric reusable launch vehicle modeled in 5 degrees of freedom. We have translation, pitch, and yaw with an artificial damping term. To slow down the pitch dynamics. We have mass and moment of inertia dynamics, so the vehicle's moment of inertia changes as you deplete the fuel. It's linear in mass. And then we assume a constant center of mass as the fuel has been mostly depleted, so it doesn't change too much. Because it was easy and not ITAR controlled, all of the aerodynamic coefficients and aerodynamic data came from Kerbal Space Program. For the aerodynamic modeling, what we do is we look at it as a combination of fin and body contributions. Both of them are modeled using lookup tables. The body is very straightforward. The fins are a bit more of an adventure. The way that we deal with the fins is that the fin forces are actually calculated in the wind frame rather than the body frame, with the rotation fixed by our 5 degree of freedom formulation. Since what we do is we fix the rotation of the vehicle around its axis in the inertial frame, and then this forces the orientation of the fins to be one specific configuration. The interesting problem here is how do we command the lift force? The traditional way to do this is to say the angle that the fins are deflected to, because that has very direct meaning to the physical plant. But the problem is that you run into a lot of unpleasantness. So stall nonlinearities, they're going way up. This is strongly coupled to the angle that the body is at relative to the wind. It just becomes very unpleasant. So you end up with this highly nonlinear map to lift force. The solution that we have is that our control variable is actually lift force directly. What we do is we non-dimensionalize the lift force based on a lookup table as a function of the Mach number, and then multiply our control variable by that. We then apply a box constraint on the allowable non-dimensionalized force to enforce what is dynamically achievable by the fins to create a nice convex volume within which the fin actuation is feasible. We then calculate the induced drag coming off of the fins producing this using a lookup table drag polar. So that's the overall model. So I'll now talk a little bit about how we then do trajectory optimization over that model. What we do is we enforce initial and final state constraints that define the start and end of the trajectory. We apply a force limit so that the vehicle is never subjected to excessive aerodynamic forces, as well as min-max gimbal constraints on both the engine once it relights, as well as the controls. We have aerodynamic and state constraints consisting of a maximum dynamic pressure, a maximum product of dynamic pressure angle of attack, which essentially defines a maximum allowable normal force to the vehicle that could rip it apart, and maximum angular rate so it can't pitch over too fast, and a minimum field constraint. Constraints in green, which are functions of particularly fast aspects of the dynamics, are enforced in continuous time. The constraints that are in black are enforced in the discretized version of the problem. The way that we do continuous time is a constraint satisfaction that we enforce this is by using the underlying Diffie-Q solver and adding an additional state to it. What we do is we detect the zero is we introduce a nonlinear function of the constraint that adds up the penalty, and then introduce a callback that then detects the nonlinear transition to ensure that the solver captures this will. We then require that this additional state is zero as part of our ultimate underlying boundary value problem solve. Then we do time dilation to get from a fixed final time problem to a two-part free final time problem, so the two independent parts of the trajectory can have different times. And then we do an overall non-dimensionalization of the problem by a scaling factor. We solve this optimal control problem through a very standard successive convex programming approach over a multiple shooting transcription. I won't go into the details too much about how this works. But I will talk a bit more about how we did the implementation. So what we do is we break our overall trajectory problem down into 41 nodes with 42 individual shooting segments. And with the fully transcribed problem and the fully augmented problem, we end up having 19 states at each of those segments. So we end up with 13,000 non-zeros in our transition Jacobian. We then compute all of these in parallel using SciML sensitivity with automatic sparsity detection, automatic sparse forward sensitivity analysis. This is much the same mechanisms that Chris was talking about in his talk earlier today. This, on my laptop, would take about 30 milliseconds to solve. We then give this problem to a subproblem solver, which then solves the linearized version of the dynamics and ensures feasibility of the intermediate solution, which then normally takes about 15 milliseconds using Jump or Clarabelle. As an example of a trajectory that's produced here, this is targeting a minimum field objective. So you can see here that along this trajectory we're satisfying all of the state and dynamics constraints. In particular, something that I'm very happy with is how we just barely kiss the dynamic pressure maximum limit in the center in the left, the middle center left one. Okay, so then the last part of this is reachability analysis. So if we have some reference trajectory where the rocket was able to relight and it was able to land at the end of it, essentially the reachability analysis problem ends up asking how far can we move this point around and have it still be able to satisfy all of our constraints. The way that we do this is by taking a reference trajectory and then perturbing it. What we do is we randomly pick a direction of perturbation for the ignition point and then push it along it. And then we just do this repeatedly, building out a convex polytope of points that we've discovered that are sort of extremal. I will skip over the details of how we actually transcribe this into the trajectory optimization problem, so that I can show you an example of a polytope. So here we have the 3D version of all of the trajectories and the extremal polytopes. And on the left here, these are sort of the reachability trajectories, so the extremal points that we've discovered on the surface of the polytope as they work their way out to it. In terms of running time, each one of our trajectory optimization problems takes about 1 to 2 seconds, with outliers that weren't screwed over by the operating system of taking about 4 seconds. It took between about 15 and 30 successive convex programming iterations to converge, and those reachability results were developed out of 10,000 trajectories, which took about 4 hours. Okay, so in conclusion, I talked about the 5 degree of freedom reusable launch vehicle model with body and fin lift and drag. I described an approach to doing non-convex approximate reachability analysis where we're extremizing only a small portion of the state, thereby avoiding the curse of dimensionality. And some future directions that we're interested in are moving to a more realistic attitude control model where we actually have a nonlinear attitude controller. We're investigating an NDI approach to slow down the attitude dynamics in a physically realizable way. Using some of the new boundary value problem infrastructure in ordinary, or not DiffyQ, it's just DiffyQ, as well as doing higher level sampling direction selection. Okay, thank you very much. Any questions?
Yeah, thank you, Benjamin. Unfortunately, we don't have time for questions, so but you can catch him, I'm sure, right? He's around. And let's move on.
Hopefully this works for you. Let's see.
Yeah.
Okay, good.
Seems to be
Thanks.
working.
Looks like it's settled down. Alessandro, right?
It is.
Alessandro is going to talk about particle models.
All right, hi everybody. My name is Alessandro. I'm from the University of Pittsburgh. Before I start, let me say it's a great pleasure and honor to host JuliaCon here at Pitt this year. So I hope you're enjoying the conference so far. So today I want to talk about some of the work that me and my research team have been developing for about a decade now about different types of approaches that are really brought together by this idea of lattice modeling for quasi-brittle fracture. The package should be out relatively soon. It has this very uninspired name of Julia LDPM. I will tell you a little bit in a second. But so in general, we're very interested in understanding how materials degrade and fail over time. Particularly, I'm very interested in quasi-brittle, brittle and quasi-brittle material. And so the vast majority of the work that we do has to do with cementitious composites, so plain and reinforced concrete structures, fiber reinforced polymers, as you see here. These are some GFRP elements that are commonly used in structural applications. And then, of course, geomaterials, and we've done a lot of work with soils and flood protection in particular. So we're very interested in understanding how different scales contribute to degradation and failure, and particularly in being able to simulate and model numerically such effects over time. And the vast majority of what we do, the package really implements this lattice discrete particle model approach, which was originally developed by Dr. Gianluca Cusaris at Northwestern University. And so in brief, I'll give you a little flavor. Because of time constraint, I will just give you a brief flavor of what this looks like, but in general, given a three-dimensional domain, the idea is that we can saturate a three-dimensional domain with polycized spheres. For the specific application to concrete, then these spheres also represent the granulometric fraction of the coarse aggregate particles themselves, so that we have a so-called mesoscale representation of the material. Then if you take all these centroids of all these particles and you perform a Delaunay triangulation, then you obtain a very dense network of 1D elements. So all the edges of the tetrahedra that are obtained from the Delaunay provide you with this very dense network of elements. We call these the lattice elements. And so the general idea is that we schematize the three-dimensional behavior of the material, of the continuum, as a discrete interactions on these 1D elements. This brings a lot of interesting sort of advantages, particularly because all of your tensorial constitutive relation become vectorial at the 1D level of the lattice struts or elements, as we call them. So what this looks like, if you could zoom in detail into one of these lattice elements, then you have this line that connects two of the spheres. We build this centroidal tessellation around each sphere, which provides with the discrete particles that we assume rigid, on which we schematize the material behavior. Now, what this looks like more in practice is this. So each of these rigid particles is effectively the volume of influence of each of the spheres. And so this is what the idealization of the material will effectively look like at the mesoscopic scale. The idea is that, especially for concrete, this is really a direct representation of the fracture itself, because the fracture is governed by mostly the tortuosity that's induced by the fact that the particles have different sizes and orientations, and so you have this direct representation of that, of these fine-scale features that provides a lot of advantages when simulating fracture. I'll give you just a couple of examples now. As I said before, we use vectorial constitutive models, which means that the model generation is relatively more tame than when you have to describe fracture in a tensorial framework, because now you can enforce exact fracture energy release rates for mixed mode fracture, which means when you have mode 1, which is tension, and mode 2, which is shear fracture, then things become really complicated in a 3D sense, but in a 1D, at the 1D level of each of the lattice elements, you can really enforce very complex fracture models. So you see some of them here for tensile behavior, shear interaction with tensile behavior, where the different levels of compression basically provide more frictional resistance to shear fracture at the lattice element level, and so on and so forth. If you're more interested into the details, which I'm gonna have to skip, you can please refer to some of these recent papers that my group published. But in practice, I want to give you more of a flavor of what the simulations look like. Effectively, you have this very dense pack of particles. These are uniaxial compression tests, very common, very, very standard so for anybody who is a structural engineer or a civil engineer. And so what you see here is that effectively not only we were able to capture, you can very accurately capture the stress-strain response. These are completely blind predictions that you see here, but not only the stress-strain response, which of course is achievable by many types of models, but what is generally not as easily achievable when you're representing fracture is also the capturing of the fracture patterns, which is again at this scale, which is the mesoscale level of the coarse aggregate particles, is a very accurate representation of very complex fracture patterns, as you see here when comparing the experimental and the numerical results. Okay, so this is sort of a long preamble, but this is the capability of the model. I want to show you some of the things that we recently implemented and added to the model, where you, in the development of all this, of the Julia DPM package. Here you see some very nice representation of a simulated failure. We call this the hourglass failure, which is very well sort of predicted by the model. Now, we recently started working into extending this method to introducing rebar. Of course, when we talk about reinforced concrete, rebar is a very critical component. And so in order to do this, we devised this technique, which is slightly different from what is traditionally done. And we do this as follows. So we first place the nodes that pertain to rebar in the domain, as you see here, which effectively mimics how you cast the models, because you first lay rebar and then you pour your concrete. And then we still fill the space with this polycide sphere, exact same, but then now you have to use a constraint Delaunay tetrageneralization to make sure that your rebar nodes are still connected by the Delaunay, as you see here. And so you get this, again, very dense network of 1D elements, and then we restructure the entire method to understand what are the interactions with between the parts. Still, we perform the standard DPM tessellation, but now this is a little bit more interesting because it's a little bit more complicated. And so what happens is that now we have the coexistence of 3 different types of lattice elements. So if you look around each of the rebar elements, you have particle nodes, which represent the concrete, that interact with your rebar nodes, obviously. And so you have 3 types of nodes. So you have the concrete element, which is concrete to concrete node. Then you have some form of contact element or bond slip element, sometimes it's called in numerical modeling. And so you have, whenever a concrete node is connected to the rebar, so such as one of these 2 inclined members, that's of course a contact lattice element, and then you have all the steel elements, which are of course rebar to rebar. Once you do this, then you have obviously to apply 3 different constitutive behaviors, because the constitutive behavior, the response to mechanical deformation of these 3 different types is extremely different, and so you have to account for that. And in this case, I want to show you just the only snippet I'm going to be showing you about all the code is that one part I really like about particularly using Julia, but in general, I think some of this implementation is very elegant, is that we have separate structs, obviously, for the different types of elements, but then you can use multiple dispatch in your constitutive function so that you can effectively dispatch the correct function depending on the types of elements. Then just a couple of very, very quick results. So you can simulate, we are able to simulate and replicate very complex fracture pattern. This is a 4-point bending test under symmetric reinforcement conditions and non-symmetric forcing conditions. So you see here that this is a DIC, which is a digit image correlation that provides you with a strain map in 2D, and you see that, of course, we can represent such very complex fracture patterns particularly accurately. And here I have some sort of computational efficiency analysis granted by a lot of fantastic work. Particularly, the package uses linear solid sparse pack, JuliaDiff, some of the JuliaSim, and some of the automatic differentiation tools that are available in Julia, which was fantastic help in the development of this. And with this, I thank you.
Thank you very much, Alessandro. So unfortunately, we don't have time for questions. It's 10 minutes. So it feels like next year you need 30. So we can try to figure that out. But yeah,
Thank you very much.
Thank you.
And we're on to the next presentation. Here in the Engineering with Julia mini symposium. We're going to talk about point clouds. Right? Manuel?
Yes.
Manuel? What's your name?
Manuel.
Manuel. All right.
All right.
Go for it.
Well, yeah, welcome everyone. I'm Manuel. I'm a postdoc at Columbia University with Marco Ciametto, and I'm presenting our work on point cloud processing, the package pointclouds.jl, for working with data from airborne LiDAR scans. So we're not primarily like a geospatial research group. We're working on atmospheric boundary layer turbulence. So that basically means the interaction of the lowest part of the atmosphere with the underlying planetary surface. But then if you want to simulate the wind flow in a real urban environment, we need to have a representation of the underlying surface of the city, of the vegetation. And for that, we've been using LiDAR data, also because we want to be able to do these simulations for any city or rural location that we're interested in. And so we created this package that helps us find available point cloud data for any location, and then read that data and perform a number of processing steps to come up with the representation of the surface that we need for simulations, which in our case means like the terrain, the buildings, the vegetation density, and the surface roughness at the level of our computational grid. So first, for people who are not familiar with LiDAR data, so the idea of LiDAR is basically the same as with radar or sonar, except that you do it with light. And so for airborne LiDAR, you put a scanner and instrument on either a drone, helicopter, or an airplane, and you fly over the area you're interested in. And then the scanner, it shoots out laser pulses. The light travels to the surface, it hits the surface, gets reflected, and maybe even partially, and then you get multiple reflections from one pulse, and then using the speed of light and the position of the instrument and the orientation, you can reconstruct the points on the surface where the laser hit the surface, and then you get from one sweep, you get the signal like you can see in the middle, so a lot of points, some of them coming from the same laser pulse, and if you do this many, many times flying over an area, you get the representation like the one on the right, where you can see the buildings and vegetation, and you get a lot of this detailed information of the surface. And so in the last 20 years or so, several countries have started building out data sets that basically cover the whole country with really high resolution. So this is usually around 10 points per square meter, so you really get the structure of the buildings and trees and a lot of the details. And they make this data available online for free. So in the case of the US, as you can see, is slowly getting towards full cover, but very close now. And some countries like France also are planning to have full cover in the next years. And in some countries like Netherlands and Switzerland, they already went through several iterations, and they have the 4th, 5th version of this national data set. And yeah, so you can get this data, and they're really cool data sets. I also want to advertise a bit this type of data. And so the first task that Point Clouds performs is that it allows you to ask for, basically look for data sets for a specific location. So currently we're just doing it for the US data, but it's extensible for other data sets as well. So for example, if we take the position of the building that we're currently in, we can put the coordinates, copy those, say give us the tiles. We see in this case we get 2 tiles from scans that are a couple of years apart, and if we load the data from one of the tiles, we get that data. It's 1.5 by 1.5 kilometer, and 17 million points, so about 8 points per square meter. And here that's the intensity of the return, so the strength of the reflection for this area. So yeah, so this allows you to get the data for any location where this data is available. And then, so this data, it's laser scan data. It's usually provided in this specialized file format called LAS, or a compressed version of the format LAZ. And so the next task then is to read this binary data and make all of the available elements of the data and attributes available in Julia. So if we load that same, basically if we ask for the LAS data for the same location, and the pictures are a bit zoomed in into this building, but we see we get some metadata for the whole tile. In particular, also the coordinate system that it's saved in, because like, different locations are using different coordinate systems. And then for each individual point, apart from the XYZ coordinates, you get some extra information, such as the intensity of the return signal, which return it was. So if you have like 3 returns from a single beam, like whether it was the first, second, third. Some classification if the producer of the data already has classified some points as ground or vegetation or something like that. And some extra information about the scanner and custom data that can also be added. And so if you look at the pictures, you see that there's a lot of information about the spatial arrangement in that data set. For example, if you look at the returns, you see that the vegetation there and the sides of the buildings, they kind of light up. And so if you want to extract information for your applications, you want to perform a series of processing steps, a bit like image processing, except that it's not on a regular pixel grid, to get the data for your specific application and your specific information that you want to know. And for that also we have like some fundamental like, processing steps you can use. So in this very simple example, in the beginning when we load the data, we already say that it should filter out the points that have already been marked as noise, as bad quality. Then we reproject it into a coordinate system that's centered at this location and crop it to ±75 meters. So we get like this local point cloud to the left. And then we can get a raster representation of the data here, 400 by 400 pixel, using for each pixel the 7 nearest points to that pixel location, and then taking the minimum height. And this way we get a digital surface model for this location that includes the buildings but not the vegetation. And so depending on what you want, you can like, define your own processing steps. And the nice thing is you can just change the coordinates to which you apply this processing, and then you get the same output for like, any location that you're interested in. And so far we've mostly added like, some fundamental building blocks, and now we're also working a bit on building out more sort of specialized processing algorithms, such as for ground point classification, detection of individual trees, and so on. We also have a student working on that. But the nice thing is, with Julia, also using with the package ecosystem and because like integration with custom functions and package functionality works so well, sometimes you don't even need that much specific functionality, and you can already do a lot. And I really think it's a great match between like, Julia and point cloud processing, because you're usually working with millions of points, and you usually apply custom processing functions to all of these points. So the Julia model of ahead of time compilation and the interactive tools such as notebooks and REPL, it really allows you to iterate quickly and then also have code that once you run it for like, an even bigger area, it still performs well. So while it's still a bit like a young point processing tool, I think it has the potential, or Julia has the potential to become a really great tool for point cloud processing, not just within Julia, but also like across languages. And for some application, maybe it already is like one of the best tools now. And so yeah, if you're interested, look at the GitHub page. We also have a JOSS paper out now. And yeah, or ask me here at the conference, or Slack, email, GitHub, whatever. Thank you.
Thank you very much, Manuel. Yeah, we don't have time for questions. We're moving on, but it looked like that point clouds loved you, like a sticker or a bumper sticker, right, or something like that. That would be amazing. All right, we're on to the next talk. Oh, all right. Is it Michael? All right.
Sorry, I was not here earlier. I thought the session started now, so.
Don't worry.
Okay, let me get back to
enough, it's all wrapped around here. Maybe you can come back.
Oh, sorry.
Don't worry. I'll come down here and then I got
Oh, you want me to get it around the back?
That's all right.
Okay.
That's much better.
All right.
We got it.
Well, so hopefully it all works. Let's see.
Yeah, let's see. Don't worry. We got half an hour.
Main thing will be, can you see what I'm doing? Yes, excellent.
Michael, take it away.
Okay, great. I'm going to move this up a little bit. You guys can hear me, right? I assume? All right. Okay, so I'll get started here. We're running a little behind, I guess. So I'm going to talk about modeling of fluid systems in DIAD. If you don't know what DIAD is, that's not the topic of this talk. But a quick summary is it's essentially it's a modeling platform that we're building out, built on top of Julia. And if you came to our Lunch and Learn yesterday, you'd have learned all about that, but I'm not going to cover that here. I do want to call out my two co-authors, Venkatesh Prasad, actually Venkatesh Prasad Bhatt, I get that slightly wrong there, and then Avinash Subramanian. I put these superhero figures next to them because they actually, Venkatesh Prasad is responsible mostly for the first half of this presentation, and I would say Avinash is responsible for most of the second half of this presentation, so I'm just here giving it. Anyway, they did a great job, especially in the last couple of days, in trying to pull stuff together for me. So I'll cover some of our goals in putting this together. We wanted to accomplish a couple things. First, we want to be able to make libraries of reusable component models for fluid systems in DIAD, which is, as I said, our modeling platform, and that would work over a wide range of different media. We don't want to create a component like a valve that's just for air, and then another component that's a valve just for nitrogen, and another one that's just for oil, and so on. That's what we're trying to avoid. And so we can actually map this into two concerns. The first one is creating reusable models of media, and by media I just mean fluids, liquids, gases, things like that. So what I like about our approach is that the media libraries are developed entirely in Julia. That includes the development of them, the testing of them, and the visualization of them. And this allows us to support, the abstractions that we have allow us to support a wide range of different equations of state and different thermodynamic states. So, and I'll show examples of this, so you'll see what I mean. And then we want to be able to support sort of arbitrary collections of properties that we want to evaluate as well. And then on the other side of this, we have reusable components. So there's the model of the media, then there's the actual model of the components. So this is like valves, control volumes, spools, things like that. So there, what we want to do is create generic medium-independent components for, as I said, valves, volumes, pistons, things like that, and avoid re-implementing that same behavior over and over again just for different fluids, because it turns out that this behavior is pretty much independent of the fluid, with the exception of a few points, which is where our abstraction comes in. And we want to be able to adapt to different structural characteristics of the fluid as well. This involves fluids that have speciation, different species in them, or multi-phase fluids. And another thing I will talk about is how we infer what medium to use in a particular component model, and I think we have a nice system for doing that. So let's start with the medium model stuff. So this is, a lot of what you're seeing here are things that were developed by Venkatesh Prasad. So we're going to start with a simple example of an ideal gas, and I'm going to just choose diatomic nitrogen because it's the most plentiful thing in this room. So it turns out you could write a very simple Julia function to do this. If you wanted to calculate the density of diatomic nitrogen, it's pretty straightforward. It's just this relationship. And so you might think, well, this is kind of trivial. We'll see where this gets a lot more complicated in a minute. But I want you to all memorize this number because I'm going to show it over and over again. And the fact that it's the same number every time is proof that this system is working. So, if you want to check my work, you just quickly take your memory photograph of that so you can compare it. I just look at it and look for the last 4 digits, 6035. So you could take that shortcut too. There are a couple issues with this function. One is that it's highly specific to diatomic nitrogen. Another thing is that the function signature is kind of ambiguous. I don't know which of these two positional arguments is pressure or temperature unless I'm actually looking at the function signature. So I could reverse them and I get a very different number. You'll note it does not end in 6035. Okay, so let's improve on that. So we can create this abstract type in Julia, abstract medium. And we can say, well, let's just make it so that these density functions take 2 arguments. The first one is an abstract medium and maybe the pressure and the temperature afterward. And that way we can swap in different media for the first part, right? We think that might work. So the problem is these arguments are also still ambiguous. But this isn't going to handle speciation for reasons I'll explain in a minute. And if we then wanted to create a model, a specific implementation of this N2 though, using this sort of an approach, this is one way we could do that. The actual way that we do this involves lots of different attributes of these gases, but I'm trying to keep this simple here. So now, if we do this, we can say, well, for a given ideal gas and a given pressure and a given temperature, we can compute density like this. Okay, so that's a little more generic, doesn't hardwire in the gas constant, for example. And again, remember, the number ends in 6035, so it must be right. But you'll notice that the density function is taking the gas that we're interested in and then these two additional arguments. But we have to get into this topic. In fact, this will be a sort of recurring theme as I go through the media material. Nature's kind of complicated. It's not a linear system, as it turns out, and there's lots of complexities, and this is the first one, which is this notion of thermodynamic state. So it turns out, in the previous functions, we took pressure and temperature as the input arguments. Now, it's probably clear if you, like, from high school chemistry or something with the ideal gas law that we're not going to be able to compute the density from just the pressure or just the temperature, right? We need both of them. And you might think, okay, problem solved, pressure, temperature. But no, it's not that simple. It turns out that there are cases where even if you have the pressure and the temperature, that's not sufficient. So the classic example is something like a water-steam mixture. And I'll show a diagram that explains that a little bit more in a minute, but I think we all know that if you're talking about water at 100 degrees C or 0 degrees C, you don't quite know what phase you're dealing with, right? So temperature's not enough. It also, in cases where you have mixtures of ideal gases, for example, the air in this room, we need to know what the ratios of the different gases are in order to compute the properties. So here's a little bit of Julia code to kind of show some of this. The first one is we could define this notion of a thermodynamic state, and we could define one particular thermodynamic state as one that involves pressure and temperature. This works if you don't have any phase changes, so that's the thermodynamic state you'd use in that case. And then this is how we would write it. Now, we've gotten rid of the ambiguity thing now because we're creating this struct, and we can use keyword arguments to construct this, so we can always be sure that we're setting the pressure equal to what we think the pressure is and the temperature equal to what we think the temperature is. So we've addressed some of those problems here. We can calculate the density for a given media and a given thermodynamic state. And so again, the number ends in 6035, so it must be right. With the same approach, we can actually then define mixtures around this abstraction. So we have the next idea here is we can define a new kind of media, which is a mixture that is composed of some set of, some media vector, where each one of these is a medium as well. And you could define air in that way. So air is a mixture of many things, but primarily two things, nitrogen and oxygen. And then you might use a thermodynamic state that looks like this, PT and X. So I need to know not just the pressure and temperature, but I need to know the ratios of those things with respect to each other, which varies based on location, for example, and altitude. So we can then define our density function. It again has essentially the same signature, two arguments, what medium you're interested in and what thermodynamic state you're interested in, but you can see how we can use lots of Julia expression syntax here to essentially compute the density of the mixture in terms of the density of its individual constituents in a nice way. And again, it ends in 6035. So, and in this case, it's because I've chosen an air that's composed entirely of nitrogen here, and that's why it ends in 6035. Of course, if we were to take real air, it would not end in 6035. It's not wrong, it's just, it involves different gases. So, but you can see it's essentially the same sort of syntax for invoking this, what the medium is and what the thermodynamic state is. And this will become important when we get into the component modeling. So a couple things to note. This works for a mixture of any media. That you notice the type here of this vector is abstract medium, so you can pick and choose. And there's a couple caveats. One is that it's only applicable for non-reacting media. So if you were to mix two things together that were then going to explode, this would not apply. Okay, if they're reacting, then they're not independent of each other, and you'd need to do something besides this just simple weighted averaging for mixing. But we are making use of this sort of recursive calling here, where this density then calls another density, and you could even make mixtures of mixtures and so on. Not that you'd really want to, but it's just kind of neat that it would work. And this using broadcasting here is very nice because it just makes it so it's a nice succinct way of calculating the properties of mixtures. Now, I said that nature doesn't really cooperate with this whole modeling endeavor I've been involved with my whole career, and this is a perfect example of what I'm talking about. If the world were simple, diagrams like this wouldn't exist, but sadly, this is actually pretty typical. So this is water, but pretty much everything looks like this. Every sort of liquid gas combination looks like this. So what this is showing you here is that if you look at these red lines, I think I actually explained this here, let's see. So a thermodynamic state in this particular case is represented not by pressure and temperature, but by pressure and enthalpy. Enthalpy is the true sort of unique identifier of the state of this mixture. So the properties, one of the things I'll point out is there's several properties on here. You can see there's this red line. It sort of comes down here and bends this way, and then it goes across, and then it bends down like that. And these are complex relationships in pressure and enthalpy. You know, no straight lines here for the most part, except right here. And what's going on here is that you're going from liquid on this end to gas on this end. And so it remains at whatever the boiling temperature is for that pressure. And you can see at 1 bar, it's 100 degrees C, which matches, I think, everybody's basic high school chemistry. So this is why temperature isn't sufficient. All of these points here are at a given pressure and a specified temperature of 100 degrees, and yet these are all very different states for this system. And green is the specific volume or the reciprocal of the density, and you can again see it's not a simple relationship as it traverses this diagram. So, for two-phase fluids, the bottom line is that you need to use pH for the thermodynamic state and not PT. Oops, and I think I was executing a git command when I was editing my slides. An errant few keystrokes there. So, there are a bunch of properties of fluids that we need to concern ourselves with. There are things like specific internal energy, specific enthalpy, the ratio of specific heats, the specific heats at constant volume, constant pressure. That's really the derivative of enthalpy and internal energy with respect to pressure. Yeah, anyway, I won't get into that. The ratio of the specific heats. Sometimes you actually, in the case where you have pH as your thermodynamic state, you want to back out temperature, for example. So temperature is something you might want to calculate. And molecular weight is another common thing. So here's a nice little Julia hack that we used in the implementation of this. CP, which is this specific heat value at constant pressure, is actually the derivative of the enthalpy with respect to temperature. And so while we've implemented the enthalpy function, which is a complex polynomial, when we want to go calculate this specific heat CP, we can use the forward diff package to actually generate that function because we know it's the derivative of the enthalpy with respect to temperature. So there we go. It'll generate that and presumably generate it efficiently and error-free. So that's kind of a neat feature of Julia. And then we'll calculate the specific heat. It also does not end in whatever I said, 6035, but this is not the density anymore. And that's why. This is the specific heat. So, so there's specific heat. What's cool about doing this stuff in Julia is that we can, it traces through nicely with symbols. So if you use the symbolics package and you call these things, you get the symbols back out, right? So in the case of a mixture, this is this air mixture, and I'm calling this and I'm specifying the pressure and the temperature as symbols, and then the ratios of these two things in the atmosphere as constants, and all that just sort of gets worked out, and I get this relatively simple form for the density, right, in terms of the pressure and temperature for the mixture. And this is important because the next step of this is going to be building component models of these systems, and those component models are built on top of modeling toolkit, which needs these symbolic representations in order to solve the systems of equations. But staying with the Julia side for the moment, there's lots of cool stuff we can do in Julia in developing all this, and one of the things I'm trying to emphasize here is that for all of this stuff, we stay completely within the Julia world. We leverage all the cool capabilities in Julia. So for example, we can create a test suite that tests all of these things, right? And there's our 6035 again, captured in our test suite. But we can go through and create a bunch of essentially reference tests to make sure that all of these sort of known points match for our models so that we don't have any regressions in the future. So that's using Julia for testing. We can also do all kinds of visualization. This is also quite nice when you're developing these properties, to be able to look at them and to sort of eyeball them and see if they look right. Venkatesh Prasad, who's in the front row here, made me a very nice interactive web application that allowed you to drag the different the thermodynamic state thing around on a slider and update it, and I couldn't quite get it to fit into this presentation. So otherwise I would have a nice interactive demo. So it's a shame that I couldn't figure out a way to get it to work in here. It kept getting the wrong size and occluding parts of the plots, but kudos to Venkatesh Prasad for actually making that work. Okay, so that was the first half of that, which is how do we define these properties in Julia, and what, why is that cool, and why is Julia good for that? The second part is creating these component-oriented models. So what we're aspiring to do here is to build a model like this, right? So some model that involves a bunch of different, like valves, for example, or pipes with heating on them, and here's another valve, and some sort of sources and sinks for the fluid to go through, and so on. And so there's a couple things I want to point out about this. One is that you can sort of intuit as just looking at this diagram, the fact that if there's some kind of fluid in here, then presumably that's what's flowing out here, which is presumably what's flowing in here, which is presumably what's flowing out here. And since these are connected, that's what's flowing in here, and so on, all the way down the line. So we have this intuition when looking at something like this about the fact that these things must be working with the same fluid. Now, the thing is, that intuition and the way we infer this makes sense in the context of like these connections. It seems reasonable to infer that if something's flowing out from here, it's flowing through this as well. It's easy when you have two connectors on a component like this, that presumably whatever's flowing in here is coming out here. But I will point out that there are lots of components that you would have in fluid systems. Heat exchangers are a classic example, where you might actually have two different working fluids involved. And there you can't just rely on automatically inferring that. You have to actually have something that explicitly says, okay, the fluid that's coming in here is flowing out on that side, and there's another distinct fluid coming in from here and flowing out on that side. So you need to have some ability to specify some of these things explicitly, but for the most part, it's possible to sort of infer this information, and that'll come up in a second why we do that. But as I said, some explicit information is required. Now, in Dyad, which is this essentially domain-specific language that we use for describing interactions of physical components, one of the key concepts there is this notion of a connector. So here's the definition of a connector in Dyad. And this will translate down into Julia code, but I'm not going to discuss that process per se. I just want to describe the modeling here. So a couple things to note. There's this external opaque Julia type here, abstract medium. We can just basically say in Dyad, there exists a type in Julia called abstract medium, FYI. We don't know really anything about it. It's just that it exists. And then in connectors, you will typically have potential and flow variables. I'm not going to go into dynamic system modeling, but these are sort of analogous if you're familiar with the terms through and across variables or potential and effort variables. It's the same thing. And these are common across most engineering domains: mechanical systems, electrical systems, fluid systems, thermal systems. But what's interesting about fluid systems in particular is that they have this notion of streams, which are intensive properties of the fluid that's flowing through. So in this case, I'm just showing you enthalpy, which is needed to make an energy balance. And then in Dyad, we have this concept of a path variable. And a path variable is some variable that is essentially shared across some circuit in the system. So whatever kind of system you're talking about, in this case, we're talking about fluid systems, the idea is that if you have continuity through that thing to form a circuit, that every component along there, every connector in that circuit has this same piece of information on it. And in this case, it's the particular fluid model that we're interested in. So here's an example of a very simple component modeled using Dyad. This is a boundary component where we're going to assume fixed pressure and temperature conditions. So there's some port. These fluid ports are the means by which fluid components exchange information conceptually. So this thing is going to be connected to something through this port, but it's going to enforce the fact that the pressure at that port is fixed according to some parameter, and it's going to compute the enthalpy at that port. So when mass flows out of this component into another component, this is the enthalpy, the specific enthalpy of that fluid, and that is calculated based on this fixed temperature parameter. So essentially it's saying this is an infinite reservoir. Actually, these things are noted over here. This is an infinite reservoir of fluid that is at a certain pressure and temperature, and it's unperturbed by any interactions. No fluid pumped in or pumped out is going to change what the pressure and the temperature are. So it fixes the pressure and temperature, and it only needs to compute one property here, which is just the enthalpy. And the beauty of dyad, one of the things that if you see any of the material on dyad, dyad is for describing the structure of a problem, but it is not. It doesn't have anything in it about describing computations, how actual math is performed. That's all done in Julia. So it outsources all of the heavy lifting for computing or calculation of mathematical relationships to Julia. And so what that means is that you can just basically call Julia functions from within dyad. And that's what's going on here. We're just calling this enthalpy function that we defined earlier. So here's another component we're going to use in this example, which is a flow component. This sits between two things. So it has two ports, and it's between those two ports that this fluid is going to flow. It has some parameters you can see here. This is overly simplistic. Anybody who's done fluid flow in the audience will probably immediately recognize that this is a very naive model because it assumes fluid flow is linear, which is really never the case. But I just didn't want to get into the complexities of modeling the nonlinear case, so I just made it simple. And this is really describing the mass flow through the linear valve. So what it's saying is that, first of all, there's a statement here, continuity between the two ports. That's just saying that whatever fluid is flowing through A is also flowing through B. The next one is mass conservation. Whatever mass comes in through A is going to leave through B, meaning that there's no actual storage inside this valve. And then you have this constitutive relationship for the flow, which is just a pressure-driven linear flow rate. And then you have the fact that the properties on either side are defined. I'm not going to go into what the in-stream operator is, but just we need to define properties for different flow directions, let's just say, and how those properties are propagated. And then the thing is, the enthalpy is flowing essentially through this system. It comes along for the ride, but you notice we don't actually compute any fluid properties in here. We're just getting them from one side and passing them along to the other side, is effectively what those last two equations say. And now finally, this is the last component that I'm going to show you, the sort of fundamental component, which is a simple control volume. Again, it interacts with the fluid parts of the system through this fluid port. It has a bunch of characteristics. It has a volume. It has an initial pressure. It has an initial temperature. It has a time-varying mass, time-varying total energy, and a time-varying temperature inside of it. This is where the dynamics in my system are going to come from. We have some initial equations here. We have the calculation of the mass, the internal energy, and this enthalpy, all using different functions in Julia, right? So these are all based on the medium and the thermodynamic state. And I probably say some of this over here. Yes, we use three properties. We conserve mass and energy. We specify initial conditions, and it's a fixed volume, so there's no work term, but we could easily add one. Okay, here's our complete system. It's a boundary, a linear valve, and a closed volume. And at the highest level, we need to specify what fluid property we're actually dealing with. So we got three components. We choose which particular medium we want to be in this system at this level. We use this continuity statement to essentially inject that into our circuit, and then from there we can infer this across the entire system. So we only have to specify this in one place, which makes it nice and easy for the modeler. And we can infer it everywhere else. And this actually includes a regression test, which I used extensively in the development of this to make sure I wasn't screwing something up. And it includes an analysis that's going to perform a transient analysis of this model for 10 seconds and test the filling of this control volume. So what's happening is we're starting off in this system with a sort of 10 bar pressure in this boundary, and no, actually, yeah, and then, I don't know, I think I maybe missed a digit here somewhere when I did this, but I think this is actually supposed to be 100K. I think I messed it up when I copied it to the slide. But anyway, high pressure in the bound, on the boundary, low pressure, relatively low pressure, atmospheric pressure in the control volume, and then the valve allows the control volume to fill. That's what this is. And you can see what's going on there. And you can see I was right. It starts from atmospheric pressure. This is in pascals, and it goes to 10 atmospheres up here. And you sort of see that's the filling of it over time. Those are the results. So, so to recap, so as I said, there's sort of two dimensions to this work. One is, I have to say a lot of the stuff that we're doing in terms of the modeling of the fluid in Julia is inspired by the way it was done in Modia, which is another Julia package, which has a sort of common ancestry with some of this work. And these fluid properties are developed completely in Julia. It's very nice. Gives you, you have all the nice Julia tooling and libraries to do that. We can use things like automatic differentiation. We can leverage multiple dispatch so that we have a single function in enthalpy, densities, internal energy across all the different media that we use and across all the different thermodynamic states that we use. We do testing and visualization in Julia, so that's all fun and great for the medium side. On the component side, what I want people to appreciate is the fact that the medium itself is a sort of model in and of itself, right? And it's actually, it spans this system. So it's kind of snaking its way through all of these circuits, but we want to have the ability to build a system of physical components and then still have the ability to decide to use different media inside of there. So, so that's, we're essentially swapping different models of the media out. We're leveraging connectivity to intuitively propagate information about what medium is actually present in all of these places. And when you can author components, as a result, you can author components in such a way that those components will work sort of independent of what the particular choice of medium is. And I didn't show any examples of speciation or multi-phase stuff, but that'll be sort of, will further that work. But I just didn't, it was already quite a bit of material to cover. Anyway, so the point is that our goal here is to really develop a library of fluid components that can be used across a wide range of media. And the other thing is that ultimately, in this case, you just develop you can develop these property functions as you need them for particular components. You see that some components required 0 properties, some required 1, some required 3. So what you need to develop is really just the union of what all your individual components require. And yeah, only need to support thermodynamic states, you'll need the same thing. And the property evaluations are just invocations of ordinary Julia functions in the end. Oops, and that's not the slide I wanted to show. But anyway, there's a slide that says thanks, and I don't know why it showed that other slide, but I made a mistake.
Thank you so much, Michael. That was quite a half an hour. Yeah.
Yeah, I think yeah, I didn't go over either.
No, you did great. You did great. Like we lost a little time because of some technical difficulties earlier. So, but you helped us more or less make it up. So, thanks. Okay. Yeah, let's thank the speaker and. I think we'll move on because we have the keynote in this room, so we want to try to stay on schedule.
Sure.
I wanted to remind everyone, well, I just did, that the keynote is here at 4:10, and also there's the poster session is in Alumni Hall, which is across the street from this building. Yeah, it's at the across the street from the cathedral. Yeah, and that's at 6 p.m. So hoping to see you all there. And we're on to the last presentation in this Engineering with Julia mini symposium. Thanks to everyone for hanging out. We have Ronan, right? It's going to be.
Let's see. Okay.
Yeah, you're pretty close. All right, great. Obrigado. Okay. And let's get going. Satellite. Yeah, some cool stuff. Satellites with Julia, right?
Okay. Good afternoon, everyone. I'm very glad to be here at JuliaCon one more time. Today I'll talk about how we are using Julia to turn gains in our next satellite. I'm not going to present a new package or a new technology or a new feature. I'm going to present how we are taking those packages that we now have in the Julia ecosystem and integrating them to create a very, very good application. For those who do not know me, my name is Ronan. I work with the National Institute for Space Research in Brazil, where I am the mission architect of the satellites Amazonia 1 and Amazonia 1B, and also the technical lead of the attitude and orbit control subsystems. In the Julia community, I'm the developer of some packages like satellite to box, reference frame rotations, pre-tables, terminal pages, and some others. But just to recap, for those who missed my talk 2 years ago, Amazonia 1 is the first remote sensing satellite that was fully designed and integrated in Brazil. It's based on the Brazilian multi-mission platform, was successfully launched on February 2021. And Julia was a key technology during the development of the attitude and control subsystems. This was a project that allowed me to create satellite to box and some other things. Okay, since this was our very first project, we have to buy a lot of equipment with spares, because if you are integrating, and let's say it's our first project, right, based on the multi-mission platform, and something goes wrong, then we can use the spare part without have to waiting for the manufacturing or something like that, which will lead to many delays. But now we have, everything went fine. We did not use those spare equipment. So we have a lot of spare equipment, and we are taking those and building another mission, which we are calling Amazonia 1B. The attitude and orbit control subsystem, which I call it AOCS for now, it's exactly the same, but the payloads are different. Now we are using a higher resolution camera called MUX camera, and a GNSS-R receiver. So this is a picture of the satellite being integrated in our laboratory in Brazil. But before I'm talking about what we did, I need to get some, provide some background about what is attitude control. Attitude and not altitude is how an object is in space. For example, my cell phone here has one attitude. If I change it, so now it has another attitude. This is attitude, how something is positioned in a 3D world. But what is attitude control? To show this, I want to play this footage of Amazonia 1 right after the orbit injection. So this was recorded by the launcher. And the satellite is being injected on orbit. It will open the solar panels. And the system will start to change its orientation so that the solar panels here point towards the sun. This is attitude control. You change the orientation of the satellite to do what it has to do. In this mode, we need to point the solar panels towards the sun. During the routine mode, it needs to point the camera towards the Earth, so it gets the image. But how do we control the attitude in the multi-mission platform? Actually, in most of the satellites that use the same design use a very similar diagram as I'm showing here. We have a control reference, where I want to point, and we have a attitude estimation. We compared both, and then we got an error, an attitude error. This error we sent to a controller, which in this case is a PD controller, proportional derivative, that generates a torque signal that we send to the reaction wheels that change the satellite attitude. This attitude change is measured by our sensors, in this case, star trackers and gyros. The information is then sent to an attitude estimator, and the loop continues. So pretty simple how we control the attitude here. But the question is, okay, we have those things called reaction wheels. How reaction wheels change the attitude of the satellite? In this picture here, we can show the reaction wheels in the multi-mission platform, right? So are those wheels here. It happens by a the conservation of angular momentum. If you spin something in the satellite, we only have internal torques, so the angular momentum must be conserved. Hence, if you spin something in one direction, the rest of the body will spin on the other direction to conserve the angular momentum. This is a very nice video that a student at INPE did, recorded, called Mateus. This is, let's say, something like a satellite mock-up. It's spinning around one axis, and on top of here, there is a motor with a mass attached to it. Oh, sorry. So it's spin, and the Mateus will turn on the control eventually, and you'll see that the device will more or less stop here. So what it did, it starts to spin that mass to incorporate the angular velocity. So it's very simple, right? If you control those, the velocity of those wheels, we can control the attitude of the satellite. This is how we do. Okay, moving forward. Among many things you have to do to design an attitude control subsystem, one of the most important steps is to obtain a good set of parameters, the control gains and the filter parameters. In Amazonia 1, we use a very known software to do this, using what normally control engineers do. We assume a linear dynamics. We assume that everything is linear. If, under this assumption, we have a very large theoretical background to work with, and we select the gains under this assumption, take those gains, put on a highly accurate simulator, check if everything is okay. If it is okay, fine. If it's not, we repeat. So just to show, this is the design, considering that everything is linear and so on. When we take, so sorry for the labels in Portuguese here. This is the pointing error. This is the time. We are applying a step signal here, so and each curve is the pointing error. It should follow that step curve here. So when we, and each curve here is one project, a set of different gains. When we took those gains and put on our simulator, the result was completely off. Why? Because there are many nonlinearities in the systems. The most impactful was, of course, the reaction wheel torque and angular momentum saturation. Since it is a motor, we have the maximum torque it can output, and if it starts to spin too fast, it cannot spin anymore. So it will not provide torque anymore. So we have those nonlinearities that are very, very impactful. That's why we see those differences here. So the process was like a trial and error. We try try a set of gains that complies with our requirements, with stability requirements. We go to the simulator, if it's good, okay, and that's why we have a lot of projects here. But in the end, we managed to do things correctly. That's why we are seeing those kind of pictures. This is a picture from the south of Florida, I think, took by Amazonia 1. You can see we have a very sharp image. Let's say the satellite is 700 kilometers above the Earth, and we are taking a picture in a way that we can see, I don't know if the, oh yes, we can see a road here, we can see a boat here. So the satellite is very stable, okay? So we know that the gains are correct. But INPE is a research institute. One of the things we need to do is to improve things, find better ways to do our process, and so on. So I decided to see if we can use Julia ecosystem to improve the way we are turning the control gains for our new mission. Because even though the system, the OCS is exactly the same, the satellite is not. So we have a different inertia. We have to obtain new gains for this new mission. So we developed an application integrating those tools, Modeling Toolkit, Control Systems, Mach-E, and Satellite to Box. In Modeling Toolkit, we obtained a simplified model of the satellite. We can design the gains
for each axis individually. And we decided to try to make the simple model we can without sacrificing the accuracy, because since we want to make a kind of real-time project, I will show what I meant by real-time project, we would like that it can run fast. Unfortunately, I cannot show to you the entire model, what we did, but I'll try to make a simple version here, so you understand what we did. The first thing is to remove everything we don't need, and the sensor dynamics is not necessary to obtain the control gain, so we just remove all those sensor dynamics here. And using Modeling Toolkit was a very nice experience. It was the first time that I used Modeling Toolkit for something in the project, because for a control engineer perspective, you just need to take those blocks, find the inputs and outputs, what the parameters are important, and then connect everything. It's very simple, very easy. So, for example, for the proportional and derivative controller here, the input is the proportional signal, the derivative signal, and the output is a function of those two inputs multiplied by the parameters here. The proportional and derivative gains are declared here as parameters because I want to chain them so that we see the modification in the output. The reaction wheels, okay, this is a very, very, very simple model. I just take a input torque and create here an output torque, which is the input torque clamped between two limits. The model we use is way more complicated, but this is what I cannot show you, unfortunately. But was much more complicated, but you understand the idea here. For the attitude dynamics, we receive the net torque from the reaction wheel, and the output is just a state variable. So we have the acceleration, the angular velocity, the position, which is the attitude here in one dimension, right? And we write those equations here for these dynamics. The inertia here must be a parameter because since we are doing it by each axis has its own inertia, so we need to change this. And finally, we need to take those blocks and connect everything using another model. We call it here one-axis satellite simulation, something like that. And we have those three components, the PD controller, the rigid body dynamics, the reaction wheel model, and then we just write the equations related to this diagram here. For example, the input to the controller is the error signal between the reference and our current attitude value. So we have this for the position and this for the velocity. The output of the controller is the input for the reaction wheel. So the input for the reaction wheel is the output for the PD control, and so on. So it was very easy. Modeling Toolkit, this kind of design, it's very good. Finally, you build the system here. By the way, I'm using here the version 9 of Modeling Toolkit. I know there is version 10 with a lot of improvements, but I didn't have time to update. But obtaining this system here, you can use the differential equations to integrate everything. But if you do something like this, you have something running in the terminal outputting numbers. It's not fine. Of course, we can have some kind of auto-tuner and so on, but I would like to make something more interesting, more easy to see, to understand. So I decided to build a graphical user interface. I'm not good at building graphical user interface, but thanks God we have Maki, which was amazing. I could do this very easily. I want to show you what we have. Let me run here. The first thing, I need to select the axis that I want to analyze. Let's see, the z-axis. I also need to select the solar panel position because in this model, our solar panel is quite big, so it has a little bit of flexibility. And this can perturb the attitude, so we need to consider it here. Let's use 0 degrees. Okay, so you have this GUI here. I don't know, oh, you can see. On the top part here, we have the classical control information, which we are obtaining from the control system diagram, the board diagram. We look to this information to check if our project is stable enough, given our requirement. On the bottom part here, we have the time response. This is obtained by taking that modeling toolkit model, running the differential equation solver, and obtaining the answer. We have some information here to make my life easier. And then we have the sliders to change the parameters. At this point, I was very afraid because if every time I change this slider, I will update the model, send to the differential equations, obtain the result, send to Maki to update the plot. If it takes like 40 seconds, 1 minute, it will be unusable, right? But I was really amazed when I saw this. It's in real time. So it was so easy that I do not even consider to use an auto-turner because I can use our expertise just to obtain good gains. For example, here, I do not want to saturate too much here. I do not want some overshoot here. Okay, the gains are turned here. I press save figure, since it's a Maki window. The figure got saved here, and I can copy to my report because I have to report everything that I do. And everything works fine. To use that, remember that I said when I was using the first approach, the result we obtained here was completely different from the simulator, because this saturation here. Normally, we do not want to saturate the actuators, but if we do not saturate the actuators here, like this, the system is very slow because the reaction wheels do not have a lot of power. The torque is in millinewton meters. So it's not a possibility here. That's why the nonlinearities here must be considered during this phase. Okay, I'm running out of time. Fine, but this was the project. What about the satellite? So we designed, this was the real design for one axis of the Amazon 1B. We took this design, we implemented it in the computer, and we performed we call it the satellite in the loop simulation. We have the satellite, we have this equipment that simulate the orbital dynamics and so on, and everything was working as the satellite would work on orbit. And this was the result. It's not the same, of course, because it's almost impossible to replicate these initial conditions, but we can see this part here. Here, the system in the design tool goes from 0 to 30 degrees, which is the same angle difference between here and here. The time span here is the same time span here. We can see that, of course, here we have initial velocity that we do not have here, so this is a little bit faster, but the satellite is pointing to the reference without overshoot in a very similar time. So the design was spot on, and it allowed me to obtain the gains in just one try. I obtained the gains, I sent to the computer, we tested, and everything was fine. So our conclusions, we developed this tool to turn the Amazonian 1 control gains. This shows how amazing the Julia ecosystem is right now, so that you can take those completely different packages and integrate them in very nice applications. We have 4 modes in the satellite, 3 axes per mode, 2 parameters per axis, and everything was obtained in less than a day after I coded this application. And the results with the satellite in the loop simulation was spot on. It was very interesting to see. I sent to the Julia Space, how can I, here. I sent to the Julia Space organization in GitHub this repository called Satellite Attitude Control Design, which is the model I showed here, the simplified model, not the one we use. Unfortunately, I cannot do that. But the simplified version with the Mackie GUI and everything, how we connect everything, the observables and so on, so you can check out if you like. Okay, that's what I want to talk. Thank you very much. I'm open to questions.
Thank you, Ronan. That was great. Are there any questions? Yeah, I'll come up, bring the mic.
Yes, thank you. How would you compare your experience of using the well-known commercial control system tuning software to Modeling Toolkit? What are the areas of improvement for Modeling Toolkit? And have you started looking into Dyad? And will that be useful? Thank you.
Yes, it will be very useful. I like programming, so I'm very happy to write code. But a lot of people in my institute do not like it. It's like a graphical user interface to plug things in. And Dyad is reaching this point. I saw a lot of talks about Dyad, and it's very good. I'm really looking forward to analyze it and how we can add those kind of, because this was a very successful applications of Julia and Modeling Toolkit in analyzing satellite dynamics. So now it's time to explore the same things in other areas like thermal control, or add more information, more data here to increase the accuracy, something like that.
All right, any other questions?
Yeah, I was just wondering why a GUI must why a GUI is the tool of choice for tuning some parameters, mostly I see GUIs used as exploring some parameter space, trying to understand the problem of choice and so on. But I rarely see that some parameters are picked using that way, right? Because, I don't know, I would expect some optimization function running over the space and picking whatever is the best value. So I was just interested in why it's done like that.
Actually, the idea to create this GUI to see the gains was just a proof of concept. And it became so easier to turn the game that we just use it. But it's not that easy because we can have some kind of cost functions, but we have some stability requirements. Yes, we can obtain this, but it's not necessary. We saw this, it worked beautifully, it fits within our design constraints, so why complicate?
All right, any other, okay, coming back. All right, here we go. Nice, I like it.
Thank you. Regarding visualizations, what are the next features you would want to see in the Mackie ecosystem to take full advantage of Satellite Toolbox and your other tools? And I'll also ask the opposite question. Are there additional features needed in Satellite Toolbox to take better advantage of Mackie?
Regarding the first part, I cannot answer because I do not use too much Mackie. I use Mackie a lot, but not all the features it has, so I cannot answer. For the second question, in the Satellite Toolbox, not in the Satellite Toolbox, but there is another package called Satellite Analysis, which I am using Mackie a lot through extensions. So there are a lot of things to do. For example, computing access analysis. We have a plot, we have a mission, we have a sensor. How many times a day a satellite will pass through that point? How many times it will take to see this point twice? So this is something I will do. I did a little example, proof of concept. It works fine using another package called Meshes together with Satellite Toolbox and Mackie. So in the next months, I'm looking forward to make more integrations between geomachy and satellite analysis.
Hi, hello, very nice talk, very inspiring, I would say. In that regard, I'm wondering, like, if using Julia, for instance, with your Brazilian team, help in somehow to either expedite the process, like accelerate it, or also, I don't know, create some kind of community or enthusiasm, or, you know, this is a great tool, it's kind of free, open source, like, is it, people were happy about it, like, people change very easily. Can you comment on that?
Yes. I was a very early adopter of Julia. The first version of Julia I used was 0.2 because I was very upset of having to rewrite my entire PhD thesis in C due to a very slow computation. So I learned about this language that's supposed to solve my problem, and I start to write a lot of functions related to satellite that does not exist. Today, we have such nice environment that Julia became very, I would say, popular at INPE. So we are using Julia to analyze the telemetry of the satellite. We are using Julia to design the LCS. We are using Julia to design our next version of the embedded software. And the way everything is connecting really helped us to make all those tasks more efficient.
All right, well, I think this wraps up the Engineering with Julia mini symposium. So thanks to all the speakers, including Ronan, and all of the participants.
Thank you very much.
test. E the adapter, so there's the adapter. I'll probably put something up real quick before you just to show where the tester connection there. Oops, sorry. Oops. Alrighty, good evening folks. Welcome to the sort of evening keynote for today. We're gonna sort of get things started real quick here because our keynote speaker has a flight to catch here soon. I just wanted to make a quick announcement first, and that's that we have a sort of poster session with some snacks at 6 p.m. in Alumni Hall, Connolly Ballroom. So not the Connolly building, but Connolly Ballroom and Alumni Hall. So you can see right here, I don't know if you can see that very well, but where my little cursor is right here, that's David Lawrence. There's Cathedral of Learning, and then just past Cathedral of Learning is Alumni Hall. And so we'll be in the ballroom there at 6 p.m. It isn't a full dinner, it's sort of light snacks, but we hope to see you there to talk with our poster speakers and chat with each other. With that said, I'll go ahead and introduce Professor Alan Edelman, and he will introduce our keynote speaker for us.
So I just found out 3 seconds ago that I'm introducing my colleague, John Urschel, but John's very easy to introduce. He's a man after my own heart. He likes to do mathematics, and he likes to do it with Julia, so what's not to love? So John is a graduate from a school in the state. He's a graduate from Penn State as an undergraduate, and was also a graduate student and earned his PhD at MIT, and I feel lucky that he was in some of my classes back then, and I feel lucky that he's my colleague right now. So some people think that one of the interesting parts of John's biography is that he was a professional football player for the Baltimore Ravens. I don't know how to play football. Nobody else at MIT knows how to play football. They don't even know what the game is. So nobody seems to be aware of this or even care. But other people seem to think this is interesting. So without further ado, let me introduce you to John Urschel. Oh, there he is.
All right, great. Okay, that was a very nice introduction. I'm not sure I've ever had one quite like it. Okay, and I never will again. So what I'd like to talk to you all about today is an interesting math problem, a pretty cool math problem that it has a pretty long history going back all the way to sort of, the start of modern computers. And I'd like to talk about the history of the problem, some recent progress, and actually how, Julia has really helped with a lot of that recent progress, okay? So, okay, Alan did a great job introducing me, but I'll say a couple things about myself. I'm an assistant professor at MIT Math, and really, as far as research goes, I really like matrices, and anytime there's a matrix somewhere, you'll probably find me there. So numerical linear algebra, matrix analysis, spectral graph theory, and I'm also a Julia user since 2016 when I took random matrix theory with Alan. And my sort of approach to Julia may be sort of quite different than many of you. I've enjoyed going to lots of talks and learning about different things. I'm sort of I'm a greedy Julia user. I care about doing math. I want to solve problems. And I find Julia is an amazing tool to help me do that. It's a language where, coding really feels like, close to mathematics. And there's something I want to be able to do. I just sort of Google around. And what do you know? There's a package for that. There's a, package for some random matrix theory thing I want. I wanted to do something over GF2. There's a package for that. And so if you've ever, helped create or maintain one of these packages, I thank you. Now, to the problem I want to talk to you all about today, well, it's a math problem, and I thought to warm us up, why don't we warm up with a math problem kind of like high school, college style. So this might feel a little bit like the type of math problem you might have seen in high school or college. So here we go. So imagine you're making rice, and so there's good grain, there's okay grain, and not so good grain. And you're taking like combinations of the three of them. And so the problem tells us if we take 3 bundles of the really good stuff, 2 bundles of the normal stuff, and 1 of the bad stuff, we're getting 39, I don't know the units, but we're getting 39 something of grain. And then we do this 2 different ways, and we get different amounts of grain. And really what we'd like to know is if I just use the really good stuff, how much grain am I going to get out? Or if I just use the normal stuff, how much grain do I get out? If I just use the bad stuff, how much grain am I getting out? And to, some of you, hopefully, if you sort of make some assumptions about how, the grain is made, you might think of this kind of like a linear algebra problem. And you could represent this using the matrix on the right-hand side, where the first 3 columns represent our 3 variables. The last column is representing sort of the amount of grain we're making. And maybe we want to solve these 3 equations for these 3 variables to see how much each one would make. And yes, the left side is very old Python. No, so the left side is actually representing what's on the right with sticks. So 1 vertical stick is 1, 2 vertical sticks is 2, sideways stick is a 5, and if you have 2 to the left and to the right, it's different numbers. So this leftmost column reads 1, 2, 3, 26. So that's my bottom row. Middle column is 2, 3, 1, 34. And then the last column is 3, 2, 1, 39. And so I'm representing these numbers with sticks, which might hint at how old this problem might be. It's very old Python. Okay, so how might you solve this? Well, in school, I think many of us learned this algorithm called the elimination algorithm. We take multiples of 1 row and subtract it from the other rows to remove values and create zeros. And we do this over and over again. So for instance, here, what you'll see is happening is the second row is being scaled by 3, and then we're subtracting 2 times the first row from the second to create a 0 in that leftmost middle entry. And again, this is being done on the left with sticks. And you can do this again to now put a 0 in the bottom left corner. And then you can do this again to put a 0 in the sort of bottom left middle corner there. And now with something like this, you can go back and now you can solve for the variables successively. And the answer you get out, in case I know you all were dying to know, is that 1 bundle of the really good stuff yields 9 1/4 of rice. The normal stuff yields 4 1/4, and the not so good stuff is only 2 3/4. Okay. So this is an example of Gaussian elimination in a very early form. So this example actually appeared in the 9 chapters on the mathematical art, dated about 200 BCE. So, like I said, very, very old Python. And really, it has some differences. The example I showed you is pretty suggestive because no negative numbers show up, nothing strange happens. The method can look a little different than the modern elimination method we learn in school, but really in spirit, it's about the same. And yeah, so this was many, many years before Gauss was even born. Okay. So now let's talk a little bit about what do I mean by the elimination algorithm or Gaussian elimination or an LU factorization. I want us to think back in our brains. What I mean is I want to factor some n by n matrix A as the product of 2 matrices, L and U, where L is lower triangular and U is upper triangular. And the way I can do this is by, at each step, taking my first row and subtracting multiples of it from all the other rows to create zeros in the top, in the sort of first column. And this can be represented through a rank 1 update, which you'll sort of, can you see my cursor? No. Which you'll see as the B minus XY transpose over alpha. And the idea is we do this over and over again. Eventually we get a lower triangular times an upper triangular. We solve this system, and this allows us to solve any arbitrary linear system, okay? And not every matrix has an LU factorization. For instance, if you have a 0 in the top left, that could be a problem. You might need to permute your rows, you might need to permute your columns. And the issues that show up aren't just a 0 in your top left entry, but really, when you have some entry in your top left that's pretty small. So you could imagine, having a 0 there is a problem for a computer because you're trying to divide by 0, but in fact, dividing by something small can be just as dangerous. So imagine, you have an epsilon in your top left, you're going to get some LU factorization where the entries start looking like 1 over epsilon. And now, I know I'm in front of an audience where I don't need to convince you that this is scary, but okay, I'm a mathematician, I'm in a department with lots of pure mathematicians, and the moment I say, I'm thinking about error and Gaussian elimination, I get stopped immediately. They say, hold on. Is Gaussian elimination not an exact algorithm? You're just adding, subtracting, multiplying, dividing. Gaussian elimination is exact and exact arithmetic. So I know you all know better, but please just act like you don't. So why don't we compare? So let's open up Julia. We'll use linear algebra. And I'll take a 1,000 by 1,000 0-1 matrix and just length 1,000 0-1 vector, okay? And let's see how exact arithmetic versus floating point arithmetic does, okay? So first, I'm just going to run one once. I'm not going to tell you how long it took. I want to avoid pre-compile time. And now, how long do you think it's going to take in Julia to solve a 1,000 by 1,000 linear system? Any guesses? I did it on this laptop. Let's see, it took, pretty close. Not too far. So it's very, very fast. That's the easy thing to know. Now, using rational big int, how long is it going to take me? It would take me about the time of this talk. It would take me about 40 minutes. And, well, how big is one entry of the exact answer? There you go. The division symbol is right around there, if you're looking for it. And then you might say, well, okay, it took me 40 minutes, but I got the exact answer. How much better should I feel about myself for having the exact answer? And sadly, the answer is not that much better. The thing you compute is accurate to, 10 to the minus 13. So somehow, exactly computing things for Gaussian elimination is not really a strategy for success. So we really need to do things in floating point arithmetic. And in floating point arithmetic, we really understand how error propagates in Gaussian elimination pretty darn well. And this has been known since Wilkinson in the 60s, one of the sort of godfathers of numerical linear algebra. And what he figured out, okay, this notation looks a touch complicated, but the idea is I want to solve AX equals B using an LU factorization. The answer that I get is a solution to almost the right problem. If this big matrix E I'm writing down was 0, I'd have the exact answer. How far off am I? How big is this E? Well, it scales like n, the dimension of my problem, times u, the unit round off in double precision, about 10 to the minus 16. And then it scales by the size of the entries in my L and U. And so really what this means is that for an LU factorization, if I compute L times U and those numbers don't get too big, I'm happy and I know that I've got a pretty good answer I can trust. So really the game when it comes to this elimination algorithm is to just say, how can I rearrange the rows and rearrange the columns of my matrix so that when I do this LU factorization, entries stay small. Entries stay small, I'm happy, I know error is small. Reasonable enough? Okay. So how do people actually choose to permute their rows and permute their columns so that entries stay small? Okay. So there's 3 popular strategies. I'd say the most popular. The first is complete pivoting. This is to say, the pivot that I choose, I want it to be the biggest magnitude entry in my entire matrix. Rook pivoting sort of says, no, I just want it to be the biggest entry in the first column and the first row. And partial pivoting says, I just want it to be the biggest thing in the first column. And so for context, if you look at LAPAC, the standard is partial pivoting. So this is what / command calls in Julia in MATLAB. This is what linealg.solve calls in Python. So you're using Gaussian elimination with partial pivoting. Gaussian elimination with complete pivoting is sort of a famous, more stable, sort of more theoretically popular algorithm. This was actually von Neumann's favorite. This was actually the standard technique around the 40s. And then rook pivoting is pretty modern. The idea is it's supposed to be some Goldilocks between these two strategies, okay? And for this talk, I'm going to focus a lot on partial pivoting and complete pivoting and sort of the parallel stories that have shown up in these two areas over the years. Okay. So now we know what Gaussian elimination is. We know about some of the choices and strategies people use. Okay, I showed you an example in Julia, but computers haven't really shown up so much. I said it's 80 years of computing, and okay, I'm not counting 200 BC as computing, as close as that looks to Python. What I'm going to consider computing is what happened around the late 1940s. And so at the Institute for Advanced Study, John von Neumann and Hermann Goldstein, they created what was called the IAS machine. And this was one of the first stored program digital computers. Which one was the first, which one was the second? This seems like a very sensitive topic. IAS claims it was actually the first. Other people claim this is not the case, but it was one of the first and very early on. And so they have this machine, and what they want to do is understand, can we do anything with this thing? Can we compute with it? Can we give it a problem and trust the answer we get out? So they really wanted to study rounding and computation. And the very first algorithm they wanted to understand was Gaussian elimination with complete pivoting. And unfortunately, they did not program in Julia in 1947, but yeah, hopefully, some of their acolytes have learned their lesson. And okay, von Neumann, for those of you who sort of know about this famous mathematician called the Martian, unfortunately he died quite young, but Goldstein in a sort of part memoir, part book about computing, said that they chose this topic intentionally as the very first paper they wrote to really understand how to do computations on a machine, because they felt that solving a linear system was absolutely fundamental. And in the paper, they actually failed in their goal. They managed to show that Gaussian elimination for a symmetric positive definite matrix under complete pivoting was numerically stable. So you can think like some version of Koleski is numerically stable. And in the paper, they felt that Gaussian elimination in general should be stable, but they felt that proving this was beyond the tools that they had at the time. This is roughly what they said in the paper. Okay. So then around the 1960s, Jim Wilkinson comes along. And okay, Wilkinson, a Turing Award winner, really revolutionized numerical linear algebra and parts of numerical analysis as well. And in the 1960s, he produced error estimates for Gaussian elimination that looked like the one I showed you before. He was the first person to recognize that this thing is actually stable as long as entries don't get too big. And he recognized the dependence on what we'll call the growth factor, which I wrote before, but you should think about as the largest entry in L or U. For partial pivoting, the algorithm which is implemented and we all used, he showed that this quantity can be exponentially bad in the worst case, and that this bound is tight. For complete pivoting, he produced an upper bound using a pretty clever technique that says we're doing much better. It's n to the log n, which still gets big, but gets big gracefully. But he didn't believe this. He thought, no, this is absolute nonsense. This algorithm should be completely stable. The entries of L and U should never get bigger. Well, for complete pivoting, the entries of L never get bigger than 1. The entries of U should never get bigger than, let's say, n, for an n by n matrix. Okay? And to illustrate what can go wrong in partial pivoting for this sort of catastrophic matrix that Wilkinson was describing, okay, let me use linear algebra again. I'll just make n 100. And now what I'll do is I'll just define the matrix that Wilkinson was talking about. So to show you what it looks like It has ones on the diagonal, minus ones below the diagonal, and ones in the rightmost column. And when you do Gaussian elimination with partial pivoting to this matrix, what happens is the entries in the rightmost column double at every step, while the rest of the matrix stays the same. And so that means the entries in the rightmost column are getting exponentially big, and bad things start happening. So for instance, if I just take some x, some random vector, I want to choose x so I know what the actual answer is. I compute my b, and now I just want to get my x back and see how well I do with the backslash command. I'm getting, this is not a very good answer. Just outputting 0 is almost equally a good guess. So somehow something has gone really wrong here, even for a 100 by 100 matrix. For people who, are really sort of like numerical, really initiated into numerical analysis, this is around the time I get a question around, well, okay, but how ill-conditioned is the problem? And the condition number is not bad. It's like 45, which is pretty acceptable for a 100 by 100 matrix. Okay, so now what I'd like to talk about is really, I've set the stage about the history of this problem. What does the modern story about Gaussian elimination look like? Okay? And really, the modern story takes two very different looking tracks. On one hand, you have partial pivoting, where we know what's the worst thing that can happen. And the question really becomes, how rare is this bad thing? There's a bad thing. It can really bite you. Is it very, very rare? Is it just a little rare? And the study and sort of research that has gone on is around understanding whether we should just not worry about this because it never happens, or to understand why this problem is actually not much of a problem at all and easily dealt with. So average case analysis is the idea that, okay, if I take some average looking matrix, this will never happen. The growth factor, how big the entries get, won't get too big. And then there's this idea of smooth analysis that maybe bad things can happen, but even if a bad thing happens, it's very, very brittle, meaning that even just moving a tiny bit away from a very bad thing, all of a sudden leads to something where there's no problems. On the other hand, for complete pivoting, we don't even know if something bad can happen. I mean, okay, certainly we know things can't get too bad based off Wilkinson's proof, but really there, the search is to understand, do the lower bounds and upper bounds, do these match somewhere, and where do they match? The upper bound says something looks like n log n, which does get pretty big as n gets big. The lower bound says n, and these two things are embarrassingly far away. And so understanding where does the truth lie, and where in this band, and how do we get there? Okay, so I'll start with partial pivoting. So for partial pivoting, this idea of an average case analysis was really championed by Nick Trefethen in this paper with Trefethen and Schreiber, also in his book, Trefethen and Bao. They sort of numerically studied the growth of random matrices, and an observation really started to sort of occur. Alan observed this as well, that for partial pivoting, it seems like the largest entry of your matrix really scales like root n with high probability. I won't say the precise version of what people conjecture, but this is roughly the spirit. And recently there's been good progress to show that this quantity is at most polynomial, but okay, the techniques of this 2024 paper, it's a very long paper, it's very technical, and oh no, that's not good. Ah, okay. It's keeping us on our toes.
Comes right back on.
Okay, perfect. Perfect. And here's an example of a picture that shows you that, really this is the truth, and you can even see this behavior, when you just run a couple lines of Julia code. this is just a histogram. I take 100,000 samples of the growth factor of and rand n by n, for different powers of 2, and you can see, when n is 256 all the way up to 2048, really this scales like root n. Like, this really does seem like the truth, although this is incredibly hard to prove, I believe. Okay. Now, a different approach says, well, instead of saying, I take some random matrix, why don't I try to find some Goldilocks approach? Thinking about worst case is far too pessimistic to say, what's the most dangerous thing that can happen. But saying what happens on average also is pretty soft. Like, what really does average mean? Okay, this is a quote of Allen's that, it's a mistake to say that a random matrix looks like any old matrix, because, the distribution of a random matrix, I don't know what the distribution of matrices that we deal with or that Julia gets on a given day, but it certainly doesn't look like a random matrix distribution. And so perhaps an even better way to try to understand what's going on is through an idea of smoothed analysis. And smoothed analysis in a nutshell says, I'll let you pick any matrix you want. It can be as bad as you want. It can be, the worst thing in the world. And what I get to do is I get to take whatever you give me, and I get to just sprinkle on a tiny bit of noise. And the idea is that if I just add a little bit of noise, everything is going to be okay. And in fact, people have been able to prove that without pivoting, this certainly holds. And with partial pivoting, this should be even more true. Though somehow the actual pivoting strategy, the fact that you have a greedy algorithm, makes it harder to actually say anything concrete. But as a numerical experiment, here's Wilkinson's matrix. I add a little bit of perturbation, this horrible thing that just hurt us. If I just add even 10 to the minus 16 level sort of perturbation to this matrix, already the largest entry drops from 10 to the 30 to 10 to the 18 for that 100 by 100 example. And it just gets better by then. And this is without pivoting. Pivoting should only help you. But still, despite sort of being able to see exactly what should happen on a computer, despite Julia telling us this is the behavior, actually proving any of the things I'm showing you has proven incredibly difficult and incredibly elusive. So somehow we can really see the truth of what things look like, what should happen, but actually being able to say anything with math is really, really hard. On the other hand, if I move to complete pivoting, it's the complete, well, not the complete opposite, but computers are not really telling us what's happening. So in the 60s and 70s, 80s and 90s, people were trying to prove this conjecture for small values. They were unable to actually improve the upper bound of Wilkinson in any sort of meaningful way, and so they focused on small cases. And then Nick Gould in 1991 managed to find a 13 by 13 matrix with growth factor 13.02 using Lancelot, the optimization software. Allen, a year later, found a nearby matrix with the same growth factor in exact arithmetic, but since the 90s, really not much had moved for quite a long time. The idea is we know that this conjecture that Wilkinson made in the 60s is barely not true, and we have pretty much no improvement to the upper bound. And recently, Allen and I, and also Allen and Ankit Basain and I, have gotten quite interested in this problem. And we tried to sort of bring math and also Julia to bear on this problem in the hope that something fruitful would happen. And in fact, the first thing we did is we managed to show that this conjecture that Wilkinson made in the 60s, or Wilkinson and Cryer, that this is actually not true for just most values of n, and they're off by at least a multiplicative constant. And in fact, the way we managed to do this was through a combination of mathematical theorems and using nonlinear optimization through JUMP and IPOpt. And so the idea is we use jump, calling IPOpt, to try to find locally extremal matrices. And then we proved math theorems that allowed us to take these extremal matrices in floating point arithmetic and prove that they must be genuine examples, and then to interpolate those to construct matrices that have large growth for all values of n. So this lower bound, a crucial ingredient was really using IPOpt, which was made, quite easy, at least for me, through jump. So I'm very appreciative for the existence of jump. Then about a year later, we set our sights on the upper bound. And for the upper bound, I'd like to say a couple words about the idea of how we improved Wilkinson's idea. And okay, I've been to a lot of optimization talks here, so I thought, why don't I show you a little bit of a flavor of what the upper bound looks like. It's an LP type argument, and then I can tell you a little bit about the spirit of how you improve this, and then also how using jump and using Gurobi and other things sort of helped come up with the right clever mathematical proof. Okay. So for Wilkinson's proof, what he does is he bounds the products of the pivots of Gaussian elimination using Hadamard's inequality. So I'll let the pivots P1 to Pn denote the entries that I'm using to remove rows at every step. And the point is, the maximum growth factor, you can really think about the biggest entry in the bottom right corner of your upper triangular matrix. And so we're trying to maximize a ratio of P1, which is the pivot of the 1 by 1 matrix, divided by Pn, the pivot of the original n by n matrix. And this extra constraint I have is something called Hadamard's inequality. It bounds how big the determinant of a matrix can be. If you haven't seen it, don't worry about it too much. What you can do is you can convert this to a linear program by doing a log transformation. And amazingly, the simple structure of this LP makes it really easy to solve. So I can write this LP as a matrix inequality. So I'll write it like this. And the amazing thing is that this matrix on the right, on the left rather, is lower triangular. So it's easy for me to take the inverse of it. And it just so happens that when I take the inverse of it and I apply it to the vector corresponding to my objective, I actually get something non-negative. And so the point is, if I take this inverse, apply it to my objective, and I actually get something non-negative, I know it has to be the solution, and I'm done, I've solved my LP. No software is needed, you can just do this with pencil and paper. So this is very, very nice. Now, our idea to try to do better than this is a pretty simple one. The idea is, when you're doing Gaussian elimination, what are you doing? You have a matrix, and every time you're adding a rank 1 matrix to it. And you're doing this over and over again. And so in Spirit, when you do Gaussian elimination, really only one of two things can happen. Either you get some matrix that has really big entries from adding a bunch of rank 1 things, or you have a matrix that has really large rank. And when I mean really large rank, I mean sort of like numerical rank. The main singular values, it has many singular values that aren't too small. One thing to notice is that you can't actually have both. Because if I started with some matrix, maybe all its entries were at most 1, I add a bunch of rank 1 matrices to it. Maybe I add, log n of them or root n of them. Then when I'm done, either the entries aren't too big and it has pretty high rank, but if the entries are really big, the rank needs to be pretty small because it's essentially only the perturbations that I added that make the entries big, and so the rank really has to be mainly those things. And so this trade-off allowed us to prove a sort of tighter version of Hadamard's inequality to try to come up with a better linear program. So we get some more complex linear program that looks complicated. We have a constraint for every choice of K and L, where you can imagine K is the size of your matrix, and L is how many steps of Gaussian elimination you look, and you want to apply this inequality to that jump. So we get this improved linear program from this idea, and then the big question that I found myself asking myself for quite a while is, okay, what's the optimum? Is this actually going to give us anything better than Wilkinson's original bound? You can do lots of things, and somehow mathematically you don't get an improvement out. And so the big question is, do we get an improvement? And if so, how do we prove it? And the answer is, well, I use JUMP. I use, I use a linear programmer solver. I use one that works very well and scales up to pretty large values. And then I just look and see what constraints are tight. And so I made plots like that, where the black dots are telling me the constraints that are tight, and the rest are telling me these are ones that are never really achieved. And then I just say, well, okay, well, let me just try to use those in some clever way. And what do you know? The observation that really I should only care about the constraints on like this right part of the triangle and this line going out was exactly the inspiration that we needed to find a really slick and really clever proof. The proof uses an idea involving taking this finite dimensional linear programming problem, converting it to a continuous one, and applying LP duality in a way that really doesn't look like LP duality. And it all looks very clever, and I have to say, it feels like one of the cleverer proofs, you know, that I've come up with. But really, the cleverness comes from, you know, from JUMP telling me, this is the answer, this is the technique, this is the idea, and from this sort of thing pops out. And so from here you get this improved bound, and this is the first improvement to Wilkinson's upper bound since 1960. And okay, I could show you a little bit about how the proof goes, but I think I might spare you the details unless, you know, if you have a question you're dying to know, you can know. But the main thing I'd like to say is that, okay, where we're at now is we have this fascinating, you know, math problem that, you know, really started in the late 1940s, and still we do not fully understand in either of these tracks. And I think, you know, computing power, I think sort of like seeing what the landscape of this type of problem looks like is really a tool that can bear fruit. And so I hope you enjoyed the lesson on an old problem, and I hope you, you enjoyed learning a little bit about Gaussian elimination again. I'll stop there. I'm not going to show you this part, and I'll just say thank you. So. Yeah, so I stopped a touch early. Unfortunately, I was invited to come to JuliaCon. I was a little bit of a late addition, so I was only added about 2 weeks ago, I think. And my son has a dentist appointment that I promised I'd take him to in the morning, so I am running to the airport at 5, but I'm happy to take questions till then.
Yep. So do we have a few questions? Somebody over there?
Yeah, while someone's asking a question, the idea is you convert all these things to sort of continuous, you convert all these things to continuous constraints, you do some integrals, and then you find that you can't do better than a certain amount, and you do some duality. Yes?
First, thanks for a really beautiful talk. Second, so it seems that, you know, sort of the hard thing is starting with pivoting algorithms designed by numerical linear algebraists and then proving something that's general about them. In your experiences in doing this, have you gained any inspirations about how you might go the opposite direction? That is, starting from an intuition about what you can do sort of theoretically and use that intuition to design novel pivoting algorithms?
Great question. I would say maybe less what I've been able to show theoretically, because it's very, very little, and I would say it's very little for most of us. But what I've gleaned experimentally is that, okay, partial pivoting is, very, very good under just tiny, tiny perturbations. And in fact, randomized partial pivoting is probably just guaranteed to work with, say for, exponentially small chance for any instance. So that randomized works incredibly well here.
Any other questions? Oscar?
Any thoughts on non-pivoting methods, like with random multiplications as preconditioning?
Yes, so there's been some really interesting work on this lately. So one thing you could do is you take some matrix you don't want to pivot, just hit it on the left and the right with some like random orthogonal matrix, and this will work well. So in fact, Laura Grigori and Jim Demmel, and maybe there was a third author who, if you're here or watching, I apologize, proved that this will do pretty well for you. But okay, generating a orthogonal matrix does take some work, and I would be happier if, for instance, you could show, because I think it's probably true that even if you hit it on the left or the right with some like random butterfly matrix or something that you can generate a little quicker, that you can also apply very quickly, I think this should also do the trick, and you just shouldn't need any pivoting. Yeah, but that's a great question.
Alrighty, I think you have an Uber to get to, so everybody give a huge thank you to Dr. Urschel, and I will see you all at the poster session here in about an hour.